Alberta. So, first time in Chile, so you are very welcome. El segundo invitado internacional es Gary Sick. And Gary has become my friend since we met in 2015 in China. And he's been very important, in making this activity true. Estará también con nosotros la doctora Alejandra Espinosa, que pertenece a la Escuela de Medicina, el campus de San Felipe. Tamara Sáez, who is going to be the woman chairman of this symposium. Y pertenece a nuestro laboratorio, digamos, de fisiología cardiovascular, que es el laboratorio que organiza esta actividad. La doctora Samantha Thomas, también de nuestra universidad, de la Escuela de Nutrición. El doctor Wal Elredi, que es bioingeniero y que también pertenece a la Universidad de Valparaíso. El doctor Carlos Escudero, del Laboratorio de Fisiología Vascular de la Universidad del Biobío. El doctor Bernardo Krause, del Instituto de Ciencias de la Salud de la Universidad de Bernardo Higgins. El doctor Javier Palacios viene del norte, pertenece a la Facultad de Ciencias de la Salud de la Universidad Arturo Prat del Estado de Chile. El doctor Jaime Riquelme, de la Facultad de Química y Farmacia de la Universidad de Chile, y quien habla. Este es el programa, es un programa bastante interesante, donde hay distintas, digamos, líneas de investigación y cuyo eje central fundamentalmente es el corazón. Así que, bienvenidos a este sexto simposio, y dejo a Tamara para que dirija esta actividad. Tamara.
Buenos días a todos. Muchas gracias por venir al sexto simposio desde las Ciencias Fundamentales a la Arena Clínica. Desde la Arena Clínica o desde las Ciencias Fundamentales a la Arena Clínica en Medicina. Ahí sí, sexto simposio 2025. En este sexto simposio nos acompañan, como ya dijo el doctor Díaz, diversos expositores. La mitad de ellos, digamos, trabajan en diversas áreas que no sean brazos, y por ellos, por ejemplo, el doctor Gary Sick, que nos acompaña desde la Clínica Mayo, y desde el área de las investigaciones de gestación, como la doctora Sandra Davich de la Universidad de Alberta. Entonces vamos a comenzar en esta mañana con la primera exposición, que es el doctor Gary Sick. Voy a dar la introducción en inglés para presentar al doctor Gary Sick. Primero le voy a comentar quién es el profesor. Él es doctor, PhD, del Departamento de Fisiología y de Ingeniería Biomédica de la Clínica Mayo en Rochester, en Estados Unidos, y presentará mecanismos de defensa de la vía respiratoria, mitocondrias como blanco terapéutico. So now I'm going to switch to English. I'm going to introduce Dr. Gary Sick. He's a PhD professor, distinguished investigator from the Department of Physiology and Biomedical Engineering from Mayo Clinic in Rochester, United States of America. We are very happy. It's an honor to have you here every year. Thank you for coming back to Chile one more time. And it's an honor for us to have you here. So thank you. And please, we are ready to hear you.
Buenos dias. First of all, I want to apologize. I'll have to speak English. I try to learn Spanish with Duolingo, and it keeps sending me back. I did. Oops, you want to, I can't get it. That's it. Thank you. So I'm sure all of you in the room have experienced the suffering of acute inflammation of your airways anytime you had a cold, but certainly we were aware of this during the COVID pandemic. RSV still infects us all the time, flu does, air pollution, all these things cause acute inflammation of the airways. This is distinct from chronic inflammation that might be associated with asthma, COPD, chronic bronchitis. The effects of inflammation are mediated by pro-inflammatory cytokines, regardless of whether it's acute or chronic. The one that we study is tumor necrosis factor alpha, TNF-alpha, although we've looked at interleukins as well. It's characterized by airway smooth muscle hyperreactivity, and I'm going to show you an example of what that means. And also remodeling of the airways, smooth muscle cell proliferation, a clogging of the airways, difficulty in getting air into your lungs. This remodeling actually increases the ATP consumption and the cost of doing business, the tension cost of the muscle, and this leads to increased reactive oxygen species formation, which triggers another cascade of events. Now, the distinction between what is normal homeostatic pathways versus pathologic pathways is where we're interested, because you have to have a normal homeostatic response to heal yourself over a period of time. It's when it turns into something that's dangerous and pathologic that would be more like asthma. So our general experimental design, we use normal human airway smooth muscle. We acquire this from patients that are undergoing lung resection surgery, typically. These are patients with no history of smoking, no history of airway disease like asthma and COPD. We then take the smooth muscle layer out of the 3rd to 6th order bronchi, and we can either use this as strips or dissociate single cells. The human airway smooth muscle cells that are dissociated are cultured for 1 to 3 passages, not beyond that, then serum deprived, and then we look at the phenotype to make sure they're smooth muscle cells by the expression of smooth muscle actin. They're then treated or not with TNF-alpha for varying periods of time, so most of the contractile responses I'll show you are within 12 to 24 hours, and the molecular responses are earlier than that. So this shows the response of airway smooth muscle to acetylcholine at various concentrations. The grayer traces are controls, and the TNF-alpha are in darker traces, and the muscle was treated for 24 hours. And I hope you can see the dramatic increase in the contractility of the airway. This is an example of hyperreactivity. So it's reacting to acetylcholine, to muscarinic stimulation, and it's a greater response. And this is occurring within 24 hours. Now this, in the past, had been attributed to a calcium mechanism, that you had an increase in the evoking a calcium response that triggers the contractile response. So we looked at the calcium sensitivity in permeabilized airway smooth muscle. Here we make holes basically in the membrane so that we can control the calcium levels that are activating the contractile response. So here's the normal contractile response in controls, and here's TNF-alpha, so matching what happened with muscarinic stimulation. Then we looked at what is calcium sensitivity, and we defined that as the effective dose or concentration of calcium that evoked a 50% contractile response. Controls had 5.9 PCA, so as you go right, calcium concentration is increasing. This is a PCA. And the TNF-alpha was 5.5, so we had to have more calcium to evoke the same contractile response. This is not calcium sensitization. This is desensitization of the airway smooth muscle. So that was a novel observation because most people had done their studies looking at the calcium response at a PCA of 4, and they noted a difference in the contractile response at a PCA of 4 and said that was calcium sensitivity, and it's not. So that raised the question, what was increasing the force by the smooth muscle? Very simplistically, we thought the force is related to the number of contractile units contributing to the force. So we looked at the concentrations of myosin, heavy chain, and actin. These form cross bridges that generate force. In both cases, we saw a pretty marked increase in the concentration of myosin and actin, an increase in the number of contractile units within airway smooth muscle. So this is our working model for the contractile response of airway smooth muscle. It's pretty complicated, so we can measure the cytosolic calcium. We know that the calcium activates the myosin light chain kinase through calmodulin, and that causes phosphorylation of regulatory light chains that allows cross-bridge formation. This is calcium sensitivity. So although we see an increase in calcium, cytosolic calcium, the sensitivity is reduced. So that really can't explain the hyperreactivity. Instead, we think we see a recruitment of additional contractile units through polymerization of both actin and myosin that occurs very rapidly. So we've actually looked at these responses after just 3 or 4 hours, and we see an increased contractile response. That leads to cross-bridge formation, cross-bridge cycling, the consumption of ATP, and I'm going to show you that in a second. And also, very important is the tethering of the contractile units to the membrane in order to generate force. These things will sit free-floating within the cell and doing nothing until they tether to the cell membrane. So to measure ATP consumption, we use a system that is regenerating ATP in real time. I don't know if you can see it, but as ATP is consumed to ADP and inorganic phosphate, we can reconstitute ATP with phenylpyruvate. That forms ATP plus pyruvate. The pyruvate is then used to oxidize NADH to NAD, and what's important is NADH is fluorescent, NAD isn't. So if we stop flow in a cuvette while the muscle is contracting, these are permeabilized airway smooth muscle, then we see the extinction of the NADH signal, and that's directly related to the amount of ATP consumed. So in real time, we can measure both force generation and ATP consumption in airway smooth muscle. And a number of years ago, we did a study where we looked at the ATP consumption in relationship to the force generated. We changed the force generation by exposure to different calcium concentrations, and a direct relationship between force and ATP consumption. So then we looked at ATP consumption after TNF-alpha exposure. Here's the force again. This is controlled, not exposed. TNF-alpha exposed for 24 hours. Then we looked at ATP hydrolysis rate, controls, and here is the change in TNF-alpha. And you can see this peak occurring. So it takes some time for the cross bridges to actually tether to the membrane. That's how we interpret that. Looking at the difference in ATP hydrolysis rate, there's a pretty marked increase in ATP hydrolysis, the rate of ATP hydrolysis, that reflects the increase in force. And if you look at the tension costs, the amount of ATP consumed per unit of force generated, the tension cost goes up. And one unique thing about smooth muscle compared to other muscle types is that tension cost is relatively low in smooth muscle. But after acute inflammation and TNF-alpha exposure, the cost of doing business, the cost of generating force increases. Now, changing directions a bit, increased ATP consumption, there must be some mechanism to generate more ATP, and we looked at mitochondrial volume density in airway smooth muscle. Here we've labeled mitochondria with MitoTracker green in this particular case. The MitoTracker comes in different colors, so you can use the color you want. This is MitoTracker green in controls and in TNF-alpha. Now, one thing you can see just by your eyes is that this is highly filamentous mitochondria. After TNF-alpha exposure, you get fragmented mitochondria. When we did imaging with confocal imaging, 3D reconstruction to look at the volume density of mitochondria, we see that the mitochondrial volume density increases just after 6 hours of exposure to TNF-alpha. That corresponds with our measurements of ATP consumption increasing very abruptly. After 24 hours, that is still present. We looked at the O2 consumption rate in airway smooth muscle cells using the seahorse respirometry system. I won't go through the mechanisms of doing that, but after 6 hours, the maximum oxygen consumption rate per cell, that's how you normalize, is per number of cells in the respirometry system of the seahorse. There's an increase, but only after 24 hours. But we saw mitochondrial volume density increase, so we've normalized for mitochondrial volume density, and when we do that, we see a decrease even after 6-hour exposure. So the O2 consumption per mitochondrion is reduced. But we think that is an adaptive response to reduce ROS formation, because as you increase O2 consumption rate in mitochondria, it's at the expense of generating ROS. And to look at that, we use mitosox labeling and fluorescence, and there was a very marked increase in ROS formation, measuring it with mitosox. We've also done this biochemically, see the same result, but this allows us to do it per cell. And if you normalize that per mitochondrion, you can see it's still elevated, but that is mitigated to a large extent. And again, that would be consistent with reducing O2 consumption per mitochondrial volume, and that would mitigate ROS formation. So the ROS, what it does in the cell, we've been very interested in the unfolding of proteins that might occur and the evoking of an ER stress response. That does it through a mechanism where BIP or actually dissociates from sentinel proteins because of the unfolding of proteins by ROS, and activates one of these sentinel pathways. In airway smooth muscle, it activates in a targeted fashion IRE1 alpha. By phosphorylation, it's serine site 724. IRE alpha can have either a protein kinase activity, it autophosphorylates itself, actually, and it can also have an endoribonuclease function. Here we looked at production of phosphorylated IRE1 alpha across time after TNF-alpha exposure. We see a progressive increase up to 12 hours, and then it wanes a bit after 24 hours. When we looked at IRE1 alpha phosphorylation after exposure to TNF-alpha, and then looked at the impact of using a chemical chaperone, PBA, to refold the proteins, we actually reduced that response to IRE1 alpha, again indicating this is an unfolded protein response. The protein kinase activity of IRE1 alpha, we think, mediates Krebs phosphorylation. And Krebs phosphorylation is a transcription factor. It's ubiquitous, and it does a lot of things within the cell. But one thing that we know that it does now is that it targets PGC1 alpha expression. And PGC1 alpha is a master regulator of mitochondrial biogenesis. And so The increase in mitochondrial volume density is due to the increase in mitochondrial biogenesis that occurs by activation of the PGC1 alpha and downstream pathways. To do that, we use a chip assay to ensure ourselves that CREB was actually targeting PGC1 alpha. So we identified in silico potential targeting promoter regions that pCREB could bind to and then activate PGC1 alpha expression. We did that with a chip assay, and after TNF alpha exposure, the binding to these promoter regions was increased, and almost certainly because of the increase in IRE1 alpha. I say almost certainly because I'm not sure, but it's consistent with that. When we looked at PGC1 alpha expression after TNF alpha exposure, there was an increase in expression of TNF alpha. I'm not of TNF alpha, of IRE1 alpha. PGC1 alpha then mediates mitochondrial biogenesis through targeting mitochondrial transcription factor A, TFAM, and the NRFs. There's NRF1 and NRF2. We were interested in NRF2 because it has quote, antioxidant function. And in both cases, we saw that TNF alpha exposure after 12 hours increased TFAM expression and also increased NRF2 expression. Now, in addition to the protein kinase function of IRE1 alpha, it also has an endoribonuclease function. And the canonical pathway for the ER stress response is that increased phosphorylation of IRE1 alpha triggers the splicing, the alternative splicing of XBOX protein, which is the transcription factor. And the spliced XBOX protein is very important for a number of things that it can do within the cell. But one of these things is to target mitochondrial fragmentation, which I showed you increases. So here's the time course of the changes in splicing of XBOX protein. Again, it peaks fairly early, 6 to 12 hours, and then declines after 24 hours. We did the same kind of analysis using chip assay to regions that we had identified in silico where XBOX protein could bind to the promoter region of CDK1 and CDK5. These are cyclin-dependent kinases. These are kinases that mediate phosphorylation, and one of the targets of these CDKs is DRP1. And DRP1 phosphorylation mediates the fragmentation of mitochondria, the remodeling of mitochondria within the cell. So again, we can look at fragmentation. We do that by confocal imaging. We binarize the images and then reconstruct in 3 dimensions. We spend way too much time doing this kind of thing. It's very laborious, time-consuming. And we calculate a complexity index. This shows you the algorithm that we use for that. The lower the MCI, the index, the more fragmented the mitochondria. And what my eyes can see, the computation tells us that the cells become, or mitochondria become more fragmented. This fragmentation is probably due to injury, damage to the mitochondria. One of the things that DRP does is targets damaged mitochondria and basically squeezes it off to prepare it for mitophagy pathways. And here we use MitoTracker green we use 2 different forms of labeling of mitochondria. One was a transfection procedure where we transfect for a labeled lactate dehydrogenase so that we label mitochondria with that. The important thing is that that labeling does not depend on a membrane potential of the mitochondria. The MitoTracker green and red and whatever depends on a proton gradient, so a membrane potential of mitochondria. And that's how it gets distributed. If mitochondria are damaged, they don't have a mitochondrial membrane potential. And so we looked at the difference in labeling between the two as a reflection of mitochondrial damage. There should be a perfect relationship, but there isn't. So we can see the two labeling techniques. The merged image, we see a lot of yellow, which would be the two are co-labeling, but we see a separation of the two. We also looked at mitochondrial membrane potential with TM or M, and to induce this, we use FCCP, which is a proton ionophore used in the seahorse technique, and it's meant to disrupt the mitochondrial membrane potential. So we could induce depolarization of the mitochondria and look at the changes as well. So the extent of damage and the extent of depolarization of the mitochondrial membrane are correlated. And what this does is the damage induces a mitophagy response. This would take me a whole nother lecture to go through this. But with damaged mitochondria, you recruit a protein called PINK1. PINK1 then mediates phosphorylation of parkin. Parkin is an E3 ligase that mediates ubiquitination of proteins within a cell. Two proteins that are targeted by this pathway. One is Paris, and Paris actually puts a brake on PGC1 alpha expression, so it's a transcriptional inhibitor. If you reduce Paris concentrations, you actually take your foot off the brake and you increase mitochondrial biogenesis through PGC1 alpha. The other target is mitophusin-2, and I, again, don't have time to go into the details on mitophusin-2, but it's in concert with DRP1, it's mediating fission and fusion of mitochondria. Anyway, we do see an increase in PINK1. This is in the mitochondrial fraction with TNF-alpha, and as our positive control with FCCP, this proton ionophore. We also see an increased expression of parkin, the phosphorylated parkin within the cells, again with both TNF-alpha and FCCP. And we see an increase in ubiquitination of proteins after both TNF-alpha and FCCP. Now, very interesting to us, this also induces lysosome formation within the cells. Here we've used a lysotracker and mitotracker combined, and so it increases the formation of lysosomes, again, very important in the mitophagy pathway. And as I said, two of the proteins that are targeted are Paris, and here you can see the ubiquitination of Paris. So this is ubiquitinated, so we do a co-immunoprecipitation to look at proteins that were ubiquitinated. And Paris is one of those, so the unbound actually goes down. So the Paris that exists within the cell are bound to ubiquitin. And this looks at mitophusin-2 and the same story with mitophusin-2. So a lot of work looking at the pathways that mediate changes in mitochondria within the cell, but also coupling that with a contractile response and change in the contractile response. Now, I'm able to come to Chile and do this because everyone else stayed home and does all this work. And I've got a great group of people. So many of them have been with me for years. Young-Soo Han right here has been with me for 30 years, and he's actually been here to Chile and twice, right? Yeah. And helped set up the ion optic system that you have here. Anyway, and I'm supported by a lot of grants. Thank you.
Thank you very much
Yep.
for your presentation. It's great. Preguntas de la audiencia. ¿Sí? Roberto.
Yes. Hi. Thanks for your presentation. Very good. Okay, again, thanks for your great presentation. So I would like to ask about the UPR response.
Mm-hmm.
So you checked the IRI1. I was wondering if you were able to check the other pathways,
Yes,
and
please.
if they are activated or not, or if exclusively like only the response of IRI1 alpha The one
So our
activated.
evidence is that they're not activated. It's selective activation of the RE1 alpha pathway.
Wow.
So the problem we have with PERK, it's also autophosphorylated, and we don't have an antibody for autophosphorylated PERKs, but we can look downstream of PERK activation, and we see no change.
Okay.
So we can say the cascade isn't activated. ATF6 is the other pathway, and we don't see any cleavage of ATF6. That doesn't mean it doesn't exist. We just can't detect it. So we think it's a selective activation of that pathway.
Wow. Thanks.
Oops, sorry.
Good morning. My question is about the long-term effects of these changes if sometimes, or if you say that on the beginning of the presentation, I didn't hear that, sorry. But is there long-term changes that maintained with some infections and in the acute way that you can see in the long term, sorry. If the changes in the ASMs maintains in time, if you have seen in this way, so
Yeah.
is this some acute effect? So in the long term, it maintains.
I understand your
that?
question. We do have access to airway smooth muscle from asthmatic patients. And when we've looked at asthmatic patients, we don't see the acute response. It's not as prominent. So what I think, that tissue is very rare to get. And what I think is happening is that this is reflecting resilience. It's a homeostatic pathway. It's what would happen in you and me, non-asthmatics. But in asthmatics, whatever the disease is, has caused a lack of resilience, so they don't respond in a homeostatic way. At least that's our initial evidence. So in a few cases we've gotten tissue from asthmatic patients, we don't see the same responses. The hyperreactivity is not as pronounced in that tissue. Even though they talk about hyperactivity, the clinicians, because they test the muscarinic response to diagnose, we don't see that at a unitary level. What you do see is cell proliferation. And so one of the pathways we've become very interested in is cell proliferation and how it couples to this. Normal, when we get exposed to acute inflammation, we don't have that much cell proliferation, thank goodness, because otherwise we would clog the airways. But asthmatics have that problem. So it could be a long-term response is to increase the number of cells contributing to the contractile response to try to lessen the burden on the initial airway smooth muscle cells. That's a hypothesis. But now, when we trigger ER stress, we target the cyclin-dependent kinases, CDK1 and 5, but we also target cyclin B1. And cyclin B1, combined with the CDKs, is very important in cell proliferation. So that might be a molecular mechanism for that to occur. Again, it would be good to compare controls normal versus asthmatic.
Okay, thank you.
¿Hay alguna otra pregunta? Si alguien tiene alguna pregunta que me gustaría que pudiera traducir también, a lo mejor que pueda. ¿Sí? Pues sí, se desea. La última pregunta.
Ya. O sea, bueno, yo quería preguntar si es que habían cambios en el largo plazo en las células musculares lisas, básicamente eso. Si es que algunos de los cambios se mantenían en el tiempo, si se podían observar algunos de estos cambios, si es que perduraban o no, por ejemplo, con los aumentos de mitocondrias TNF-alfa, que sí. Eso. No, sí, creo que respondió bien a mi pregunta. Gracias.
Thank
All
you
right.
very much.
Thank you.
Ok, so, ahora vamos entonces a presentar a nuestra segunda invitada. Voy a hacer entonces la presentación primero en español y luego voy a presentarla también en inglés. Bueno, ella es la doctora Sandra David, ella también es PhD, es profesora distinguida, es la directora del Instituto de Investigación en Salud para la Mujer y Niños de la Universidad de Alberta. Ella pertenece además al Departamento de Obstetricia y Ginecología de dicha universidad en Canadá. Nos presentará hoy el tratamiento antioxidante dirigido a mitocondrias en la placenta y su impacto en la salud cardiovascular y la descendencia. Ella además, debo contarles que fue mi profesora de mi postdoctorado, así que estoy feliz además de tenerla acá. Y ahora I'm going to switch to English to introduce the next speaker. It is a great honor, and I'm so proud to have Sandra David here. And my alma mater here. This is my alma mater university. Thank you for coming, Sandy, to this university. Sandra David, she's a distinguished professor, director of the Women and Children's Health Research Institute. She also belongs to the Department of Obstetrics and Gynecology from the University of Alberta in Canada. She was my postdoctoral supervisor, so we know each other very well. And I'm very happy that she's here. It's a real honor, and I'm very happy to have the opportunity to listen to your work one more time. Thank you.
Buenos dias. Good morning. It's such a thrill to be here and see Tammy having her own professor now here in this university. Roberto is my postdoctoral fellow as well, so it's wonderful to be here. And I look forward to getting questions and meeting all of you in your poster sessions tomorrow. So my talk's going to switch a little bit more to a higher level to look at, could we do something about developmental origins of health and disease? And if you don't know what that is, I hope after today you will have an appreciation of it. How the fetus develops in utero can have a major impact on key organs as it's developing, and that includes the brain, the heart. I'm going to focus on cardiovascular, that this will increase the risk and the susceptibility to cardiovascular disease later in life. And Time magazine, lay public, shows how the first 9 months can shape the rest of your life. And I think that's a good analogy to use and to think about. And then we're not just made up of our DNA. It can be altered throughout gestation and early life exposures. So this was championed by Dr. David Barker, who showed way back in 1989 that there was an association between low birth weight and risk for coronary heart disease. So if the lower birth weight, you have greater risk for cardiovascular disease. And this is not extreme changes in birth weight, so it's an inverse relationship. But yet, it's not listed in either the American Heart Association, the World Health Organization. Go to your guidelines in Chile. You probably will not see developmental origins as a risk factor, and yet it should be, in my opinion, and hopefully I can convince you of that today. You can see smoking, hypertension, physical inactivity, all those risk factors. We now have preeclampsia as a complication of pregnancy as a risk factor, but this is about maternal health. What I'll be talking to you about today is the offspring and the impact on offspring. So I would champion that developmental origins should be on this list. Greater than 30% of pregnancies have complications, such as growth restriction, preterm birth, preeclampsia, diabetes. But you don't even need those complications. You can have things like women going into pregnancy obese, so poor nutrition, undernutrition. Many things can alter the in utero environment. And we need to be understanding that as we look at the future generations, but also as we treat our patients today. And I'll show you some data for that. So there needs to be an understanding of mechanisms and potential intervention strategies to improve the outcomes for vulnerable populations in order for this to actually get on the list one day in these organizations. So there's many factors that modulate fetal development. You have genetic, of course, nutritional, but placental insufficiency is a big component of what affects the fetus. But all of these, and many of these, can lead to fetal hypoxia. So it's actually the reduction of oxygen that is kind of the first line of complications that can occur in the fetus. And there's many conditions that can create a prenatal hypoxia environment. I study preeclampsia, which I won't talk about today. We're going to go right into fetal hypoxia, but you can see a number of conditions can affect the in utero environment, resulting in fetal hypoxia. So what we've been looking at is the fact that we have a prenatal insult that can result in programming early in life, as early as fetal development, that can ultimately lead to cardiovascular disease. This has been championed now for over 40 years, but there's a lot that can happen in between. So a lot of people are not really sure what to do with the information of developmental origins. So we've been using animal models to provide proof of concept, define mechanistic pathways, in order to develop prevention and intervention strategies. And you can see here that throughout the life course, we are all at risk for chronic disease. Eventually, if we live long enough, we will all have some type of chronic disease in life. And this would happen if you had a complicated pregnancy, you have a steep rise in this chronic disease. But if we can do early intervention strategies early on, you can change the trajectory of this chronic disease later in life. And this intervention can be done at time of plasticity, where it's actually the intervention can make the greatest difference. So if you look at the placenta and all the options that can be there, what you have is a suboptimal in utero environment that can ultimately result in hypoxia. You got oxidative stress happening, and the mitochondria being the primary source, which follows along from the previous talk of the mitochondria, that can impact on organ development of the fetus, as well as secreted factors being released. So you have placental dysfunction with oxidative stress, but you can also have secretion of factors going to the fetus. And for those in the preeclampsia world, we've been studying secreted factors from a placenta affecting mother's health, maternal health, for many years. There's been very little data on the factors released from affecting the fetus. And this can result in abnormal organ development and impaired function in adult health. So we've been looking at a placental-targeted treatment, and we're using mitochondrial antioxidant treatment in order to improve placental function to actually show proof of principle that developmental origins can affect adult health, and there could be treatment strategies. So why are we targeting the placenta? Well, anytime we treat the mom and or the fetus, you could have potential off-target effects. There hasn't been a new drug in pregnancy in decades because of potential negative impact on the fetus. So if we can create a mechanism to develop a placental-targeted treatment, we're only treating the placenta, then you hopefully would not have negative impact on the fetal development that you were not anticipating. So what we have is a mitochondrial antioxidant, MitoQ. Many of you might have heard about it. But we use a nanoparticle delivery system where it can get in the placenta and release the product of MitoQ. And this is able to do that because of its size and zeta potential. We can see that the nanoparticle mitochondrial antioxidant, MitoQ, gets into the placenta but does not go into the fetal brain and liver. But does this impact fetal development and later life cardiovascular health? So this is a model. You'll see it multiple times. It's the same model, but I just want to remind people what the model is. We have pregnant Sprague Dawley rats, and at the last third of pregnancy, they go into a hypoxic chamber. Gestational day 21 is when we study them, and the term is at gestational day 22 in these rats. We do the MitoQ injection prior to them going into hypoxia, so it is a prevention. It's more of a proof of principle. And the MitoQ does recycle, so we have constant antioxidant treatment throughout that time. And we study the placenta, and I'll just show you a few data sets on that due to time. And then we study the fetus, and then later life cardiovascular health. So from the placenta, what we showed is in the blue is the hypoxia. Hold your breath, you turn blue, so blue hypoxia. And from this, you can see that there was greater oxidative stress by superoxide that was prevented by MitoQ. And we studied both the male and female placenta because we do have litters, and they both have males and females in there. And we saw similar data with the female placenta. When we looked at the fetal cardiomyocytes, and this is just a gross indices, we used a stain that only stains when there's actually very low levels of oxygen. And what we saw was that there was a reduced cardiac oxygenation in the male fetuses, which we did not see in the female fetuses. And remember, these are coming from the same mother, the same dam. So there is sex differences right at the very beginning of life relative to fetal differences in sex. So we have prenatal hypoxia, oxidative stress, and we're now looking at impaired cardiomyocyte development. So the question we had was, could these placental-derived factors affect fetal cardiac development? And with this, what we did, same model, pregnant animals, last third of pregnancy, but now we're collecting the placenta, and this is in control, hypoxic, plus or minus mitoQ. And we cultured these placentas at an oxygen level that's appropriate for placentas, and we take the conditioned media and we exposed them to control sex-specific male and female cardiomyocytes. And what we showed, we combined the males and females here. So in this case, we did not see sex differences, but you can see for yourself if there was any. There's closed to the males, open to the females, is that prenatal hypoxia resulted in a reduction in mononuclear cardiomyocytes that was prevented by mitoQ, and a corresponding increase of binucleate cardiomyocytes, as you can see here. And what this is an accelerated maturation, and you're basically born with the number of cardiomyocytes you will have for life. So we're using the assumption that this will result in less capacity to have cardiomyocytes at the time of birth. And we looked at size, so we saw an increase of cardiomyocyte size in both the binucleated and mononucleated that was prevented by mitoQ. So we are affecting the fetus myocyte structure in these animals. And what is it that's in the, placental cultured conditioned media? Well, with colleagues, we had looked at neurons, so I'm more of a cardiovascular person, but they showed a correlation of microRNAs in fetal plasma and related this to transcripts in fetal organs. So we've been looking at the role of placental-derived circulating microRNAs in the fetal organ development. And we're looking at microRNA 210 as it relates to cardiovascular development, but that data is still to come. So the summary of the fetal work is that factors derived from hypoxic placenta does impair cardiomyocyte development in both males and females, maybe a little differently, and that treatment-targeted placenta is a possible intervention that could actually improve the fetal outcomes. But does this impact adult cardiovascular function? So back to our model again. We have our pregnant Sprague Dawley rats, last third of pregnancy with hypoxia, but now we're letting the offspring grow up, male and females, to 4 months of age, and then we give them a secondary insult, ischemic reperfusion, like a heart attack. And this is what the working system looks like. We hang the heart, first in Langendorf mode, switching it into working modes. These are hearts that actually have to work. And we look at this both in 4-month-old male and female animals. And our question was, does prenatal hypoxia increase the susceptibility to ischemic reperfusion injury? And what does mitoQ do? So the data that we have here is, you can see, this is the work, cardiac work, prior to ischemia, and all the groups look very similar. We give an ischemic insult, and it's not very long, 30 minutes for these hearts, and the controls do okay, but if you're born for a prenatal hypoxic environment, you do not have the capacity to handle this secondary insult. And you can see here that the percent recovery is significantly reduced, but I think most importantly, look at what happened when you have pre-treated the placenta. All we did was treat the dam and the placenta, and we were able to allow that by the time the offsprings are adults, that they have the capacity to recover from ischemic reperfusion. And you can see how tight the data is. Like, here's a lot of variability, but if they've had a better functioning placenta, you could see we're able to rescue that and be able to have reserve to handle a secondary insult. And this is true, so this is the same data, but now I'm comparing it to the females. The similar data, you can see the females weren't as affected by the ischemic reperfusion, but it was variable, and again, that mitoQ prevented that and allowed for all hearts to be able to recover from this secondary insult. So we're back to my figure again, where we have a suboptimal environment, placental dysfunction. We have shown that there's placental secretive factors and oxidative stress, and that there's a potential for placental targeted treatment. So if you look at this early intervention, this is great as we talk about the life course, complicated pregnancies. We are actually getting to the stage where we might be able to treat the placenta. There's other people around the world looking at placental treatments, not necessarily mitochondrial antioxidants, but I think we're getting there, and that will help the generation moving forward. But what about our generation here? All of us here. If we had been born from a complicated pregnancy, born too small, too early, from a mother who had preeclampsia, we're all at risk for this ischemic perfusion insult. So what's happening with the adult? How is it that, how did prenatal exposure affect adult, and what happens when the adults have intervention strategies? So this part, I'll just show you the data we have on endothelin. So why we focus on endothelin is that hypoxia is a regulator of endothelin. I'll tell you a little bit more about endothelin as it relates to the heart in a moment. But for fetal hypoxia, it's been shown that it increases pre-proendothelin levels in the fetal heart, increases binucleation and size, which is exactly what our data showed, just we didn't show it was endothelin. This was done by another group. But again, we showed that. And this is all in the fetal heart, but no one's ever questioned about the impact on the adult. How does this pathway affect the adult heart? So why endothelin? Why do we focus on that? Well, myocardial ischemia is associated with increased levels of endothelin. Endothelin acts through ETA and ETB receptors to increase infarct size, affects coronary artery function, and cardiac dysfunction. So endothelin is known to be one of the mechanisms involved in ischemic reperfusion. And selective blockade of ETA has improved recovery, has been shown to improve recovery from ischemic reperfusion. So we asked if this ETA receptor antagonist, a blockade of ETA, can enhance the susceptibility of, enhance the recovery of the susceptibility to ischemic reperfusion insult if they've been exposed to prenatal hypoxia. So the study design, same one. The dams are in the hypoxic environment. I'm not going to show you mitoQ until a few minutes, so this is just a hypoxic environment. 4-month-old, male and female. We always study both. And now we're looking at ETA receptor antagonists, which are actually in clinical trials. They're in clinical trials today, and they've shown to improve recovery, but they're with very variable results. And so really hasn't gone back past the clinical trial stage. And that's going to be important to remember. And then we add the ETA receptor antagonist in our isolated working heart system. And what we showed, I'm going to show you the females first, is that this is just with ETA receptor antagonist. Just focus on the prenatal hypoxia, because that's what we care about. We have prenatal hypoxia, lots of variability on recovery. But if you have the ETA receptor antagonist at the time of the working heart system, we were able to improve recovery. And again, the groups together so that all the hearts are actually able to recover. This is what's shocking to us, which we had shocked about. Here's the ETA receptor antagonist in helping the normal animals, control animals. This is what would have been in the literature, that ETA receptor antagonist can improve cardiac function. Look at what it did if you're born from a prenatal hypoxic environment. This drug, adult intervention drug, that's supposed to be good, if you're born from a prenatal hypoxia, in our animal model system, it had zero recovery capability to recover from ischemic perfusion. So the state by which you're born in can impact your adult intervention strategies. We did look at endothelin levels. They weren't different among all the groups. So endothelin goes up like it showed in the literature. It did not go up any further if you're born from prenatal hypoxia. So it's not about increased endothelin levels. And surprisingly, there was no change in ETA receptors. And in the females, there's a decrease in ETB receptors. So it's a downstream pathway. We think it's through PKC epsilon. I don't have time to show you that data today, but it is a downstream pathway. So in females, ETA receptor inhibition did improve cardiac recovery from ischemic perfusion. In males, and this is both in normoxic and prenatal hypoxia, in males, it could improve on the normal, but it resulted in no cardiac recovery after ischemic perfusion in prenatal hypoxic males. So understand the developmental influences. Prenatal history, we should be taking that right now. No one's ever asked me if I was born from a mother that had preeclampsia, and I think we should be taking that information. Also, sex differences, males and females, they need to be taken into consideration as we develop therapeutic strategies for adults. So, back to the mitocue. Does placental-targeted treatment prevent this perturbed adult male phenotype for cardiac therapeutic intervention? So we did a follow-up study, whole different cohort of animals, once again, very consistent. If it's in the presence of the ETA receptor antagonist, you did not get recovery. And treating the placenta did reverse on some, but not all, of the animals where the hearts were able to recover if you had a placental-targeted treatment. So placental-targeted treatment, for proof of principle, does help the heart for secondary insults. So our conclusions overall is that hopefully you appreciate that pregnancy complications increases susceptibility for offspring to chronic disease, including cardiovascular diseases. Placental-targeted treatment is possible, and it's the way of the future. Not quite there yet. It's important to understand prenatal history and sex differences to develop specific preventive and therapeutic strategies, including adult interventions. And this is where we're getting into the world of precision health and medicine. And this is where this area, not forgetting about prenatal history, is going to be critically important. So my final comments are developmental origins of adult cardiovascular disease. Yes, it exists. There's been extensive literature on that. We need to get it into the guidelines. Can the placenta be a therapeutic target? Yes. But really, we need to accurately identify who to treat. We don't really know when the fetus is developing an environment of prenatal hypoxia. You can assess that after the fetus is born. So we need to have technology development, and I know that's a lot of biomedical engineering people here, in order to measure in vivo oxygen delivery. We've been working with a photoacoustic system on that. Omics approaches for biomarkers, whether it be metabolomics, proteomics, transcriptomics. This will allow us to optimize interventions for precise and personalized treatments, and we always have to take into account sex differences. I didn't have time to show you today, but the impact of prenatal hypoxia affects different pathways as it relates to male and female hearts. So it's critically important to keep sex differences there. And with that, I'd like to thank all the people. This is the data I present today, but you can see Tammy and Roberto, who worked more on the preeclampsia projects, and you'll hear more about that. I just love all the people in our labs, and then our collaborators from the UK who helped us with the nanoparticle system. So with that, I'm happy to take questions. Thank you. I knew you would ask a question.
Thank you very much, Sandy. Very nice to see you here in Chile.
Wow.
Welcome to Chile.
Thank you.
So, a lot of questions, of course, about your work, but one of the questions that I wonder is how hypoxia modulate the division of the proliferation of mitochondria, because if you want to improve the system. So this is one question. And the second question is, I wonder whether the distribution of the mitocue is homogeneous across the placenta, or is some specific areas of the placenta that is focused on.
Yeah, great questions. So relative to the mitochondria, and we've looked at fusion and fission, and there are changes in MFN2 and all that. We haven't actually looked at the actual structure within the placenta for that mitochondria. So we have markers of changes in fusion and fission, and to tell you the truth, I'd have to look up exactly what that data is, but we have published in that. And also we did use Ouroboros for looking at mitochondrial differences. That we were using the reduced uterine placental perfusion rat model for that one. And we only saw changes in complex 4, and it was subtle. So we're not seeing, I think the placenta has an amazing capacity to adapt to its environment. We haven't done it in the prenatal hypoxic animals, but we will go back and do that, because we don't see that much differences in oxidative phosphorylation of the using OXPHOS, the Ouroboros on that. The distribution of MitoQ, we do know MitoQ is up, but we didn't look at the distribution. So we just measured it in totality, but not about the distribution. So that's actually a good question as well. Yeah, so I don't think MitoQ is going to be the answer for treating pregnant women. I think it helps us with that proof of principle that we can treat the placenta, find the right way to treat it for future. And then this is all prevention. We want to do the treatment after we already know that there's a complication within that pregnancy. So, yeah. And you might want to repeat all that in Spanish.
Yeah.
Espanol.
So last question. Have you ever tried to, because nowadays treatment with mitochondria for cardiac dysfunction or muscle dysfunction is already in place. So I wonder whether have you tried to treat the placenta with mitochondria?
Only the placenta, with
the whole mitochondria, trying to transfer mitochondria to
no,
them.
I haven't. We could try that, though.
We can chat together.
Yeah, let's talk. That's how collaborations happen.
Okay, thank you. And there, vamos a preguntas.
Well, I can talk to you individually, too. So.
Sí, más preguntas. Okay, so thank you very much.
Thank you, Tammy.
That was a great talk, Sandy. Thank you very much. Y ahora me cuesta el cambiar de español a inglés. Estoy confundiendo. Vamos a pasar entonces a la tercera conferencia. El doctor Wael Elderedi creo que tiene que cargar su presentación, ¿cierto? ¿O ya está? ¿Sí? ¿La puede colocar aquí en el computador para pasarla ya, por favor? Sí. Bueno, aprovechar entonces, mientras el profesor coloca su presentación en nuestra computador, aprovechar entonces de decir que esta es la tercera presentación de la mañana antes del café. Después viene el café, entonces, que vamos a estar 30 minutos afuera, solo aquí en la terraza. Y luego volveremos por otras 3 conferencias para luego ir al almuerzo, ¿ya? Y a las 3 de la tarde hay que volver para la siguiente jornada de exposiciones. Para el día de hoy, la jornada termina a las 6 de la tarde y luego mañana tendremos hasta mediodía. La jornada empieza nuevamente temprano, mañana empieza así a las 9 de la mañana. Y luego a las 10, alrededor de las 10:15, comienza la sesión de póster, que las presentaciones se llevarán a cabo en esta sala, pero luego tenemos que ir al frente, al edificio clínico, y en el patio central, abajo, será la sesión de pósters. Ahí todas las personas que van a exponer sus pósters van a encontrar números, yo les voy a mandar un correo, cada uno con su número, y ahí tendrán que colocar su póster mañana en la mañana. Luego además van a ser evaluados con 2 profesores cada uno y se premiará a los 2 mejores pósters. Para cerrar a mediodía más o menos el simposio premiando a los 2 mejores pósters con un cóctel. Bueno, vamos a ver cómo anda acá el doctor. ¿Puede seguir hablando, por supuesto? El día de hoy va a tener nubosidad parcial, nos espera una máxima de 21 grados. No. Estamos bastante bien en el tiempo. Esperemos que todas las presentaciones se mantengan bien en el tiempo para no atrasarnos. Como dije, es una jornada bastante larga, entonces para terminar a tiempo. Que cada expositor, ¿cierto?, respete los tiempos de exposición. ¿No tengo 2 horas entonces? No, por supuesto que no. Nos encantaría, pero no es así. Bien, voy a presentar entonces a nuestro siguiente expositor. La siguiente presentación es del doctor Wael Elderedi. Él es de casa. Él es PhD de la Escuela de Ingeniería Biomédica de la Universidad de Valparaíso. Él además es parte de nuestro centro de investigación en Meding y nos presentará hoy de la dinámica cerebral a la dinámica de la salud, una perspectiva ingenieril para la biomedicina. Dr. Wael Elderedi, he's a PhD from the School of Biomedical Engineering. He will be presenting today. Okay, so it's in Spanish. Como usted desee. ¿Sí? ¿Puedes, cómo se dice en español? Spanglish. 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 Ok. Gracias. Gracias.
Agradezco a Tamara la invitación y el hecho que cambió el programa. ¿Me escucha?
No. Es el canal.
Ya. No puedo bailar entonces. Bueno, repito, agradezco a Tamara la invitación y el hecho que cambió el programa para ajustarlo con mi calendario de hoy. Entonces hay un salto de tema. Obvio, yo no puedo repetir el trabajo bonito que presentaron los colegas visitantes, ni tampoco el nivel de detalle, porque voy a cambiar como tema. Me gustaría compartir con una idea, un concepto que llega de la ingeniería. Yo aplico mi trabajo en la neurociencia, nada que ver con el simposio o lo que hacen ustedes. Por lo tanto, lo dejé como a nivel más general. Los detalles técnicos, si les interesa, lo conversamos, lo hablamos. Hay cosas técnicas que yo creo que por el trabajo de mi laboratorio yo lo considero bonito, pero lo que quiero plantear es esa idea que la salud como sistema dinámico. Entonces lo voy a presentar como por el lado del estudio de neurociencia o del cerebro y ver cómo podemos generalizarlo por otros conceptos. Me gustaría, como mucho lo que dijo Sandra, ella presentó algunos grafos de trayectoria del desarrollo de la salud de la placenta y la consecuencia. Entonces, ese es el concepto que me gustaría presentar y la consecuencia técnica de esa idea de la trayectoria de la salud. Muy bien. Aquí estamos. Como dijo Tamara, yo pertenezco a la Escuela de Ingeniería Biomédica. Mi trabajo es como la frontera entre cosas muy de técnica, matemática, física. Nosotros estudiamos el cerebro como sistema físico y aplicamos reglas de la ingeniería para estudiar las oscilaciones cerebrales, las redes cerebrales, etc. Y eso es lo que me gustaría que generalizamos a la siguiente fase. Esa es una figura muy parecida a la que le presentó Sandra, en el sentido de que tenemos tiempo, la edad, el tiempo y una trayectoria de varias funciones cerebrales. Y pasa por algo muy parecido, o sea, como invertida de lo que presentó Sandra, como hay un desarrollo, una fase de desarrollo muy rápido, hay una mantención del performance, de la capacidad cognitiva, luego hay un declino. Y por la parte de los físicos, dicen hay puntos de inflexión que aquí pueden ser interesantes predecir para hacer algo. Por ejemplo, mantener esa línea más allá. O que si predecimos que esa curva va a declinar en una persona más rápido, hacemos algo. Entonces, esos puntos, cambios de estado, esa es la palabra que voy a usar mucho, ese cambio de estado puede ser interesante. El desafío principal es cómo predecimos ese tema. Entonces, un paso para atrás, ¿qué significa sistema dinámico? Para que estamos como al menos en la misma página. Sistema dinámico, algo que evolve en el tiempo y tiene un cambio en el tiempo en manera, la mayoría del tiempo, no lineal. Es decir, por eso hablamos de estados. Entonces, el caso de tal vez más cerca de ustedes, algo como el ritmo cardíaco. El ritmo cardíaco cambia en el tiempo, es un sistema dinámico en manera a veces no lineal. El nivel de glucosa en la sangre en nuestro caso la actividad eléctrica o la actividad cerebral, o la progresión de una infección, o sea, cómo vuelve la tasa de infección en el tiempo en un sistema dinámico. Para nosotros es que una manera de poner como modelos físicos de ese sistema dinámico nos permite aprenderlo, entenderlo. Más importante, por el lado de los ingenieros, piensan siempre en predecir y controlar. Eso es lo que voy a presentar de rápido. Sin meternos mucho en detalle, sistemas dinámicos tienen características. Y esas características, lo que vamos a presentar como forma de seguir ese sistema, entender ese sistema o controlarlo. No voy a meterme aquí. Si alguien quiere preguntarme de eso luego, lo hacemos. Me gustaría presentar como el tema en los sistemas biológicos. Sistemas dinámicos son sistemas dinámicos muy complejos. Voy a presentar un ejemplo mecánico súper simple para darle esa como ejemplo de la complejidad de ese tipo de sistemas. Vamos a tener dos péndulos, solo dos. El péndulo, la oscilación, la frecuencia de un péndulo se da por el largo del péndulo, nada más. Son un variable, un parámetro no más. Aquí tenemos, vamos a ver si va a funcionar. Ya. Y son dos coplados. El hecho de que tiene dos oscilaciones coplados genera una riqueza dinámica enorme. Si estamos hablando, imagina como, en el caso del cerebro, decimos que si uno nunca mide la activación de una célula, si solo se tiene la célula separada, pero el momento que conecta dos células, ya tiene sistema, ya tiene una red. Y aquí el caso de los dos péndulos, hasta que ni siquiera puede predecir a dónde va el sistema después. ¿Ya? Ocupan estados, hay estados casi discretos, o modos, vamos a decirlo así, modos discretos, pero es muy difícil predecirlo. Eso es lo que quiero transmitir. Un sistema dinámico, en el caso biológico, la interacción no son entre dos entidades, es mucho más. Entonces, ese es el espacio de lo que llaman atractores de esos dos péndulos. Entonces, esos son el tipo de estados que ocupan. Insisto, son dos cosas nomás. Ahora, generaliza eso a nivel de sistema que tiene 1000 o millones de componentes. Entonces, el sistema dinámico toma trayectoria en el tiempo, la figura, gracias a la figura que presentó Sandra, que muestra que ocupa estados o cambia o vuelve en el tiempo. En el caso del cerebro, esa es una muestra de lo que medimos, la observación. La observación, en el caso cerebral, esos son los nodos que medimos, que muestran así como cambios, saltos de estados. Esos saltos de estados corresponden a saltos de redes. En el caso de que pueden pensarlo a modos de operación. En el caso de nosotros hablamos de redes cerebrales o redes neuronales que cambian su configuración en el tiempo por la necesidad de las tareas o en el hecho que les voy a mostrar en el ejemplo ahora, cuando la persona no está haciendo nada, en estado de reposo. Esa evolución en el tiempo normal y natural tiene información que nos permite hacer predicciones sobre su estado cognitivo o incluso su estado de salud. Entonces, la idea, no vamos a tener tiempo para meternos mucho en eso, pero lo que hacemos nosotros es modular de dónde llega esa dinámica, qué genera esa riqueza dinámica en el cerebro y si es útil, que podemos hacer algo con eso. Eso es lo que vamos a mostrar. Esa es una gráfica también muy parecida al concepto que presentó Sandra. Cuando, en el caso de neurodegeneración, cuando una paciente presenta con síntomas, ya no hay nada que hacer, porque los cambios estructurales y funcionales en el cerebro partieron a veces 20 años antes. Entonces, la idea es, si tenemos algo que podemos... De hecho, Sandra usaba la palabra plasticidad, es lo que decimos. El sistema dinámico tiene forma de adaptarse para compensar un fallo. Entonces, no aparezca nada de síntomas. pero ya hay un cambio dinámico que ya marca que hay en marcha algo que va a ser la neurodegeneración o cualquier otra enfermedad. ¿Por qué? Porque los sistemas biológicos tienen una resiliencia, una forma de adaptación que permite que aguanta los cambios mucho más tiempo hasta que aparezcan los síntomas. Y cuando aparezcan los síntomas, perdona, pero que ya no hay nada que hacer. Entonces, el desafío tecnológico es, a esa medida, ver si había un cambio o hay un cambio que me permite decir que esa persona va a envejecer bien o va a desarrollar algo como Alzheimer's o PD o etc. Entonces, el desafío tecnológico para nosotros es aquí, detectar algo en su dinámica normal, incluso sin tareas, que me dice algo sobre lo que va a pasar luego. No necesito convencer a ustedes que el cerebro es de sistema dinámico, entonces voy a saltar eso, pero entretenido si queremos, a todos niveles en el cerebro, eso también como marca el cerebro como órgano un poco distinto, a cada nivel hay oscilaciones. Y esas oscilaciones tienen escalas, las escalas cambian, pero hay oscilaciones a todos los niveles. Nosotros usamos, la mayoría de nuestro trabajo usa EEG, pero el concepto no importa, cualquier serie de tiempo sirve. Aquí tengo un ejemplo del trabajo de Hannah Honkamp en Maastricht, que ya acabó de terminar su doctorado. Y el concepto es, la idea es tomar la serie de tiempo, la actividad cerebral que medimos en reposo, la persona no está haciendo nada, relajada, y hacer un tipo de análisis que nos permiten marcar los saltos de estados. El cerebro está saltando entre configuraciones de redes en manera espontánea y algo en esa característica de esa dinámica nos permite decir o marcar diferencia entre personas que escuchan voces o no. No son pacientes, no hay diagnosis aquí. Son personas que tienen la tendencia de escuchar voces más. Y sin hacer nada, hay suficiente información en esa dinámica que marca la diferencia entre esas personas. Y no, insisto, no son pacientes de nada. Y el trabajo de Hannah marca que en los tiempos que ocupa el cerebro en cada estado, lo que marca esa diferencia. La duración de cada estado es la trayectoria que está tomando. Está como, el cerebro está haciendo un camino, una trayectoria. Esa trayectoria, la forma que toma esa trayectoria, es lo que marca la diferencia. Otro ejemplo de trabajo de Alan Astudillo, que terminó su doctorado con nosotros aquí, que muestra lo mismo. En la dinámica en reposo, marca diferencia entre personas con Parkinson y controles de la misma edad. Y en lo mismo, las duraciones o el patrón de la trayectoria en el reposo marca esa diferencia. No solo entre los pacientes y los controles, pero también lo que benefician de una intervención cognitiva o no. En ese programa, lo implementaron en Alemania, dan una intervención casi tipo música. Le dan música de marcha alemana, un mes, se escuchan eso, esa facilita la marcha en Parkinson. Pero no todo el mundo beneficia de eso. Y lo interesante aquí que antes y después marca, después de un mes de esa intervención, en su actividad de reposo, muestras quién ganaron de esa intervención y quién no, sin hacer nada, solo por su dinámica. Otro ejemplo que marca diferencia entre personas mayores y jóvenes en base de su cambio de dinámica de oscilaciones. Si tomamos el espectro, yo me presenté con un espectro de EEG de rápido aquí, si compramos solo el espectro, el contenido de frecuencia en esa serie de tiempo no marca nada, no se ve nada. Solo en estudiar esa trayectoria donde sale la diferencia. Bueno, vuelvo a eso. Por tema que algunos de mis colegas aquí saben que es mi como hobby horse. En la biología, habla un ingeniero, ¿eh? En la biología es un campo empírico. no se deriva por teoría. Se piensan en un experimento, toman el experimento y luego hacemos la interpretación a posteriori. Interpretamos los datos que tenemos. Que es lo contrario que hacen los físicos. Los físicos no necesitan datos. Los físicos parten con la idea, con la teoría. Arman la ecuación y buscan cómo ese modelo, cómo esa ecuación explica el fenómeno que tenemos. Eso permite que hacen predicciones a veces mucho antes que tenemos la capacidad de tomar la observación. O sea, es famoso como había predicciones de Einstein que demoraron 40 años hasta que encontraron los datos. Entonces esa idea de pensar en una manera de acercar el concepto físico para desarrollar teorías nos va a permitir hacer mejor predicciones, en mi opinión. Entonces, es un intento de modelar ese fenómeno usando el sistema dinámico, una ecuación. Esa nos permite sacar parámetros y dice que qué controla ese fenómeno. Entonces, andando por el lado del control, nosotros partimos con la matemática, hacemos simulaciones, luego experimentamos. Eso es un experimento de nuestro ahora doctor Andrés Gómez, que recién terminó su doctorado. Como tratamos el cerebro como osciladores, como pendulum, queremos empujar ese sistema para que ocupa ciertos estados, favorece ciertos estados. En ese caso, Andrés usó sonidos, clics. Hizo clics antes de una tarea cognitiva que no tiene nada que ver con los clics, pero controlando la frecuencia por persona muestra que puede mejorar el desempeño de la tarea. Entonces, dirigir el sistema, darle ese metrónomo a frecuencia determinada, lo predecimos de antes, permite que las personas hacen la tarea mejor. Entonces, esa muestra que si mandamos ese metrónomo como irregular, como no beneficia nada, y que las personas ganan casi 5%, 7%, en sistemas cognitivos mucho, ganan eso solo con tener esa serie de clics de antes. El mismo concepto, vamos, no me gusta, ya está. Ese mismo concepto lo usamos con una pulsera que manda vibración. Vibración que es a la frecuencia que medimos, la frecuencia, le llamamos la frecuencia de resonancia del sistema somatosensorial. Entonces manda vibraciones y esa le llamamos como descanso virtual, permite a los trabajadores a altura. En Chile hay mucho trabajo, como saben ustedes, de minería de altura. Entonces esa fue una colaboración con Codelco, trabajadores que trabajan a 4.000 metros. 4.000 metros, y ellos no duermen a 4.000 metros. Entonces nunca llegan a nivel de aclimatización correcta. Entonces trabajan a 4.000 metros, pero duermen en los Andes a 1.000 metros, todos los días. Entonces la pulsera muestra que ellos que con esa estimulación táctil aguantan la altura mejor. Tienen mejor nivel de atención por la estimulación. Y la idea aquí que es la estimulación táctil controló el sistema para mantenerlo en un estado de alerta más. Entonces no saltaba afuera de ese estado deseable, que sean alertas a esa altura. ¿Me siguen? Y ese fue un trabajo en colaboración con nuestro colega Alejandro Einstein, ahora en la Santa María. Y el aparato existe, ya se venden. Hizo como un poco de trabajo para contextualizar lo que estoy hablando con el tema del simposio y lo que están hablando ustedes. En neurociencia está ahora de moda, digo de moda, pero por razones mecánicas muy interesantes, esa relación cuerpo-cerebro. Entonces, y en el modo de controlar la actividad cerebral se muestra que el patrón respiratorio o el ritmo cardíaco cambian la oscilación o los estados cerebrales. Entonces esa pulsera o los clics de André podemos convertirlo en una intervención autocontrol por controlar la respiración. Se puede llegar a un estado deseable, estado cerebral deseable, por controlar la respiración. Es un trabajo, un ejemplo que muestra, me impresionó porque por ver la sincronía entre la fase de la respiración y la fase de la oscilación cerebral. Lo presento como idea de conversar. Nosotros tenemos otros alumnos, colegas de aquí también, Sebastián Espinosa, que muestra que se puede controlar esa oscilación cerebral por la masticación. La masticación misma tiene un patrón que entrena la actividad cerebral para que sincroniza o favorece ciertos estados. Por ejemplo, la masticación muestra que con la masticación mejora la memoria de trabajo, el nivel de atención, etc. Entonces aquí el tema del ritmo cardíaco o el HRV o el patrón de respiración se puede usar como señales de control para modificar el estado cerebral. Creo que puedo parar aquí para que conversamos. Mira. Muchas gracias.
Muchas gracias, doctor Joel. Muchas gracias por la presentación. Abierto a preguntas de la audiencia.
Hola, muchas gracias. Mi pregunta va orientada a un poco los mecanismos, si es que se conocen o cómo los hipotetizan ustedes en cuanto a cómo se explica la modificación de las oscilaciones cerebrales con cierto tipo de actividades como pulsátiles con ritmos determinados, y eso cómo finalmente termina en una mejor performance cognitiva, por ejemplo. ¿Qué más o menos han indagado en ello? Eso, gracias.
Gracias por la pregunta, porque no hay excusa para decir más. Pensamos primero con la base. Tareas cognitivas necesitan recursos. Recursos significa una red funcional. El cerebro se configura para facilitar hacer esa tarea. Esa configuración funcional va a tener una huella oscilatoria, un modo... Tiene como, piensa en una guitarra. La guitarra tiene resonancia distinta de la resonancia de un violín o violoncello, ¿sí? Por la dimensión física del aparato o la materia. Hay algo muy parecido en las redes cerebrales. Las redes van a tener una huella espectral, una huella oscilatoria, que tiene que ver con la configuración. Si yo estimulo por los clics o por la vibración, si estimulo esa red por su frecuencia favorita, voy a favorecer ese estado. ¿Me explico? Entonces, eso es lo que en el paper de Andre le llamamos la triada cognitiva. Tarea, red, oscilación. Gary, tenía...
Entiendo. Gracias.
So I didn't understand a word, but I know the importance. I know the importance of dynamic measurements. Time is one of the most important variables, but the tools to look at that are really sparse.
Yes.
So I know you focused on EEG and other techniques where you get a continuous signal, but many things are not measurable across time. It's very, very difficult. So I think that's the involvement of biomedical engineering, is to come up with innovative ways to do that.
Yes. Thank you for the comment. I mean, I can show something very rapidly. I avoided talking about methods, kind of getting into the technicalities. But there is a figure here that could allow us to kind of talk about it. So you're right. We don't always measure things changing over time. I will extend this statement to say we actually hardly ever measure the direct phenomena in any case. We always measure a proxy of this, kind of an observation that comes from a hidden or a latent process. And our job is to infer the process. That's what we do from our experiments. So if we assume that down here I have the observation, whether it's EEG or fMRI or measurements of some blood indicator in time, I will say this is a continuous measurement that comes from a discrete process. The process underlying this is discrete. And I can form a model that generates this observation. I can experiment with the models until I get the best generation. Now I have a set of parameters that describe the process, the generative process. And that's basically what we try to do. That allows me to do this segmentation of the states and the duration and the trajectory, etc., at the level of the hidden variable or hidden state or the hidden process, if you like.
Another variable that we as physiologists often ignore is temperature. And temperature has a profound influence in changing the dynamics. I'm sure you're doing all these things.
No, I mean, we focus on EEG, but I mean, if somebody teaches me something about temperature modeling, I mean, the process of the modeling is easy because now we have the tools. We've spent the last 15 years thinking about new tools to kind of do this segmentation. So now we have the tools. We'll give you the sequence like this, but at the end, it's our colleagues who do the experiments who then do the interpretation. But you're right.
So I spent a lot of time teaching my students, re-educating them in thermodynamic principles. And hysteresis is one thing that is very interesting to me, and the work that goes into a system to explain hysteresis. I don't know if you look at this at all.
We look at hysteresis because as I said at the beginning, and my work, it kind of starts from the physics, mathematics, engineering to try to model the brain. So hysteresis is, do you understand the expression? Yeah. So hysteresis is very obvious in much of our cognitive and perceptual processes. If I give you a series of colors and ask you to press a button when you observe a change in the color, you will make a different decision whether I go from blue to red or from red to blue. That's the essence of do you agree? That's a reasonable explanation? So basically the brain uses predictions and the predictions sometimes dominate. So there's a whole area in brain science called predictive coding and the Bayesian brain where prior knowledge or prior expectations drive the perceptual process. We did a lot of work on placebo analgesia, where we showed that the expectation, when I give you a pill to say this will kill the pain, and somebody says, oh, it's less painful now. It's not a trick. It's not like a psychological trick or a social contract with the medic. It's actually a physiological response. Just the expectation of having reduced pain reduces the pain. So, Bernardo.
¿En español o en inglés?
O lo que quieres.
Well, in English, just to reinforce the discussion. I was thinking about the mathematics behind a potential prediction of long-term outcomes. And talking about dynamics, you know that in physicochemical state, you may find, for instance, a liquid that is below their solid point. And if you perturb that liquid, will start to solidify immediately. But that state is metastable state. Could be not that the case for predicting disease, because maybe it's not a continuous between health and disease, and maybe there's a discrete difference that can you address by mathematics. So therefore you should select different type of mathematics. I mean, not continuous, but discontinuous math.
It is As always, Bernardo asks very, very good questions. So it's a hard question and it's a hard question even at the level of the physics. Because if you have a dynamical system with phase transition, the boundary, the phase transition boundary is always very hard to study. It's actually a point where you can't really study. You study either points of the phase transition, because if there is discontinuity, there is no mathematics to help you there. So you always kind of try to bring yourself as close as possible to the discontinuity, but you can't study the discontinuity itself. It's like the Big Bang. We can study the point immediately after the Big Bang, but the point of the Big Bang is discontinuity. We can't get there. There is no mathematics to take us there. Your point about, we understand your point in terms of even disease progression is not necessarily a phase transition. Just the change in the state I insist on using the word trajectory. It's the path rather than the state, than the phase transition itself. And the three diagrams that Sandra had were very illustrative of this. You have different trajectories, and if you're able to predict where somebody will divert from the normal path to take something different, that's the point where you need to intervene. There is no disease there.
Thanks.
Muchas gracias, doctor Guarale.
Ya.
Y nosotros siempre tratamos de tener una presentación disruptiva y creo que esta fue completamente diferente a la que siempre hacemos. Así que muchas gracias.
Gracias por la invitación.
Me voy al café ahora y nos está esperando para
Yeah, exactly. All we've done, I actually
Ok, entonces estamos ya listos para empezar la segunda sección de presentaciones del simposio. Estamos un poquito pasados en el tiempo, pero vamos bien. Todo está bien, todo está bajo control. Ahora le toca el turno al doctor Rienzi Díaz Navarro. Él es médico, cardiólogo, ¿cierto? Director del Laboratorio de Fisiología Cardiovascular. Pertenece al Departamento de Medicina Interna de la Escuela de Medicina de acá de la Universidad de Valparaíso. Y, por supuesto, es un gran honor escucharlo porque además es el gestor, quien inició este simposio. Gracias a él tenemos un sexto simposio, pues cada año es el quien se encarga de que esta actividad sea única y sea para cada uno de ustedes, para la comunidad universitaria. Así que de verdad es una alegría contar cada año con el doctor Díaz. I'm going to switch to English just for our speakers. So now our next speaker is Dr. Rienzi Díaz. He's a cardiologist. He's the director of the Laboratory of Cardiovascular Physiology, also from the Department of Internal Medicine, from the School of Medicine at the University of Valparaíso. And as I said in Spanish, he is the one that actually is the leader of this symposium. Every year, Rienzi take care to make this symposium possible. So we are very proud of that, and it's an honor for me to introduce Dr. Rienzi Díaz. So please, Dr. Rienzi.
Muchas gracias, Tamara, por la presentación. No sé si merecía o inmerecía, pero en los próximos 30 minutos vamos a conversar sobre una condición que se llama miocardiopatía diabética en búsqueda de sus mecanismos celulares y moleculares. Bueno, la diabetes mellitus es una condición metabólica que tiene riesgos de ser una epidemia, porque el número de pacientes que viven con diabetes hoy en día es enorme, 537 millones según la Federación Internacional de Diabetes, y si uno lo mira país tras país, por ejemplo, nosotros tenemos una incidencia de un 10.8 que es prácticamente similar a la que existe en los Estados Unidos. Un poco más baja es Canadá, representada aquí por la doctora Sandy Davidge. Por lo tanto, es una situación, digamos, muy alarmante desde el punto de vista sanitario. Tiene un enorme impacto sanitario. Ahora, la diabetes mellitus es muy relevante porque se asocia a mucha patología cardíaca, fundamentalmente en la producción, ¿cierto?, de infarto agudo de miocardio, stroke e insuficiencia cardíaca, pero esa patología está relacionada fundamentalmente con el desarrollo de aterosclerosis, ¿cierto?, que es el causante, digamos, del infarto agudo de miocardio y del infarto cerebral. Sin embargo, los pacientes con diabetes mellitus también desarrollan una suerte de insuficiencia cardíaca en ausencia de patología coronaria o valvular o, digamos, enfermedad vascular periférica, o sea, no hay aterosclerosis, y que se denomina diabetes, miocardiopatía diabética, descrita por primera vez en el año 1972 por Rubler y colaboradores. Ahora, la miocardiopatía diabetes se caracteriza inicialmente en sus estados iniciales por disfunción diastólica, y eso es porque el fenómeno de la miocardiopatía diabética desde el punto de vista estructural se desarrolla hipertrofia miocárdica y además se produce depósito de fibrosis, o sea, las células, ¿cierto?, que mueren por este estado de hiperglicemia, es reemplazada por fibrosis y eso produce inicialmente un corazón que es fundamentalmente hipertrófico, pero no tiene problemas de contractilidad, y entonces esto uno lo denomina en clínica insuficiencia cardíaca con fracción de eyección preservada, es decir, la contracción o la fracción de eyección supera el 50%, pero luego esta condición progresa a un estado en el que hay una disminución de la función contráctil y es lo que se conoce clínicamente como insuficiencia cardíaca con fracción de eyección reducida. Ahora, los mecanismos de producción de esta condición no se conocen del todo. Sin duda, existe una interacción celular a nivel del miocardio, ¿cierto?, entre los cardiomiocitos y el resto de las células que forman parte del tejido cardíaco, fibroblastos, células inmunes, células endoteliales. Y como decía, lo primero que ocurre es que se empieza a producir hipertrofia, se empieza a producir fibrosis, pero no hay sintomatología. Y esta es una etapa importante, porque si uno tuviera la posibilidad de pesquisar esta patología a esta altura, sin duda podría, digamos, intervenir y evitar que el fenómeno se desarrolle en estas dos etapas. Ahora, los mecanismos que se conocen son que existe disfunción mitocondrial, esto produce, ¿cierto?, la generación de especies reactivas de oxígeno que son muy dañinas, ¿cierto?, para la vitalidad de las células, muerte por apoptosis y, como decía ya, hipertrofia cardíaca y fibrosis miocárdica. Entonces, pensando en la posibilidad de lograr identificar fenómenos causales en esta etapa, es que nos hizo, digamos, focalizar y generar un modelo, digamos, de miocardiopatía diabética y estudiar y pesquisar algún elemento que nos permita, digamos, ganar más conocimiento. Y, por otra parte, nos enfocamos en la sirtuina 1 fundamentalmente. Las sirtuinas son estas proteínas que son relevantes en la salud humana, en enfermedades como la obesidad, como la isquemia miocárdica y también en la diabetes mellitus tipo 2. Ahora, la sirtuina 1, uno de los miembros de esta familia, tiene una acción cardioprotectora, actúa, digamos, sobre el metabolismo de la glucosa, el metabolismo de los lípidos, la biogénesis mitocondrial, la autofagia y también la inflamación. Entonces, la sirtuina aparece como una posibilidad, ¿cierto?, de que sea una diana potencialmente, digamos, en el futuro, sobre la cual uno podría actuar y evitar, digamos, que esta condición progrese en el tiempo. Ahora, lo que nosotros hemos hecho entonces en nuestro laboratorio es tratar de identificar si existe relación entre sirtuina 1 y los cambios morfológicos que ya mencionaba, que se observan en la miocardiopatía diabética, especialmente fibrosis e hipertrofia, en un modelo murino de diabetes que lo hicimos, en nuestro caso, en ratas Prague-Dolly, pero solo machos. Entonces, nuestro modelo consiste en generar una diabetes mellitus experimental administrando streptozotocina en dosis de 65 mililitros intraperitoneal. Seguimos los animales y realizamos eutanasia a las 12 semanas y luego en otro grupo a las 16 semanas. Ahora, este modelo es desarrollado, ¿cierto?, y dirigido por la doctora Tamara Sáez y el doctor y Mayo, digamos, nuestro asistente, digamos, de investigación. Luego de la eutanasia, a las 12 o 16 semanas, lo que hacemos es un estudio, ¿cierto?, de la histología del páncreas. Y a nivel de corazón, lo que realizamos es evaluar la presencia de hipertrofia y o fibrosis, al mismo tiempo de estudiar la expresión de sirtuina a través de inmunohistoquímica. También aprovechamos este modelo de estudiar el riñón y estos son datos que va a presentar Pamela Benavides, que es una tesista que trabajó en nuestro laboratorio para lograr su grado de máster y que ahora es estudiante de doctorado. Bueno, estos son la primera información, digamos, luego de generar digamos, la diabetes experimental, chequeamos, ¿cierto?, la glicemia y el peso de los animales, y ustedes observan que claramente ya a las 12 semanas los animales desarrollan una hiperglicemia bastante importante, que ratifica, digamos, el hecho de que el uso de streptozotocina realmente genera diabetes experimental en los animales. El peso no tiene grandes diferencias entre los animales tratados, ¿cierto?, y los controles. Ahora, toda esta información, la información obtenida es producto del trabajo que hicieron estudiantes de tecnología médica que desarrollaron, digamos, también este proyecto, supervisados obviamente por Tamara y por Mario. Pamela Benavides, como decía, que obtuvo su grado de magíster y que ahora está realizando su doctorado, nos compartió, digamos, estas imágenes. Esto es el estudio del páncreas, digamos, en los animales a las 12 semanas y a las 16 semanas, y ustedes ven cómo hay una enorme diferencia, hay una destrucción prácticamente de la casi totalidad de los islotes de Langerhans. Aquí nos falta todavía, y eso es un propósito que tenemos con Tamara, de estudiar la expresión de insulina en estos remanentes, digamos, de islotes de Langerhans. Pero la diferencia del área es bastante significativa entre ratas tratadas, ¿cierto?, y los controles. Cuando se evaluó la existencia o no de hipertrofia, este es el método que se usó, se realizó, ¿cierto?, se estudió el coeficiente, ¿cierto?, entre la totalidad de los núcleos de las fibras miocárdicas, excluyendo obviamente los núcleos de otras células que forman parte del tejido cardíaco, dividido, ¿cierto?, por el área de la fibra miocárdica. Ahí se observa, digamos, que realmente hay, en comparación a los controles, la presencia de hipertrofia, de manera, digamos, significativa estadísticamente. Cuando uno mira la presencia de fibrosis, también hubo diferencias significativas entre los controles, ¿cierto?, y los animales tratados con streptozotocina. Esto es a las 12 semanas y esto a las 16 semanas. La fibrosis se observa fundamentalmente a nivel perivascular. El depósito de colágeno es fundamentalmente en esa área. Y esto no fue, digamos, no hubo diferencia significativa entre los controles, las ratas diabéticas a las 12 semanas, pero sí a las 16 semanas. Es un proceso que ocurre, digamos, mucho más tardíamente. También se evaluó el depósito, digamos, de lipofucsina, y ustedes observan, digamos, que también en relación a las 12 semanas y a las 16 semanas hay mayor cantidad de depósito de lipofucsina. Sin embargo, hubo diferencias significativas solo a las 16 semanas entre las ratas tratadas y los controles. Y en este diapositivo se muestra, digamos, la expresión de sirtuina 1 control, ¿cierto?, a las 12 y 16 semanas, y las ratas, digamos, diabéticas a las 12 y 16 semanas, y hay una significativa diferencia en la, digamos, en la expresión de esta proteína. Ahora, cuando uno relaciona, lo que planteaba previamente, ¿cierto?, es lo que nuestra intención fue relacionar los fenómenos, digamos, morfológicos que ocurren en la diabetes, en la miocardiopatía diabética, es decir, fibrosis e hipertrofia, y la expresión, digamos, de sirtuina, y ustedes observan que las correlaciones muestran eso. Hay una correlación aquí con un coeficiente bastante alto, en el sentido de que cuando hay hipertrofia, la intensidad de señal de la sirtuina es baja. Lo mismo ocurre en el caso de la fibrosis. Mientras mayor cantidad de fibrosis existe, hay una menor intensidad de señal de la sirtuina. Lo mismo ocurre también en el caso de la lipofuncina, aunque el coeficiente de correlación no es tan poderoso, digamos, como en el caso de la fibrosis y de la hipertrofia, pero existe también correlación. Lo otro que hicimos es evaluar si existía algún problema con el manejo del calcio en esta condición, y estudiamos entonces cerca 2A y fosfolambano, y en nuestro experimento no encontramos diferencias, digamos, en el manejo del calcio, digamos, a través de cerca y de fosfolambano. Luego de esto, y pensando también en que el fenómeno, digamos, de producción de especies reactivas de oxígeno tiene un rol, chequeamos, ¿no es cierto?, la presencia de estas moléculas, y efectivamente, si uno lo mira visualmente y uno compara, ¿cierto?, las ratas diabéticas a las 12 y a las 16 semanas, hay una clara diferencia desde el punto de vista visual. Lo hicimos con digamos, con este colorante, y realmente, si uno lo observa en la gráfica, no hay diferencia significativa, aunque hay una tendencia a las 16 semanas de que, lo hemos conversado con Tamara, y esto es claramente un problema probablemente de potencia, es decir, si tuviéramos un número mayor de animales, es probable que esta diferencia sea significativa. Por tanto, en conclusión, este estudio de alguna manera, ¿cierto?, valida nuestro modelo experimental de diabetes en el sentido de que es un buen modelo para estudiar cambios morfológicos en ratas diabéticas generadas, ¿cierto?, experimentalmente. Y por lo tanto nos ayuda, digamos, a entender más esta condición, digamos, propia, digamos, de la diabetes mellitus. Por otro lado, entrega evidencia de la que sirtuina 1 tiene un rol cardioprotector en la miocardiopatía diabética. Sugiere también que las especies reactivas de oxígeno están relacionados y probablemente tienen un cierto rol en la patogenia de esta condición. Y esto, digamos, obviamente nos estimula, digamos, a seguir estudiando esto. Y respecto de cerca y fosfolambano, digamos, como proteínas relacionadas con el manejo del calcio, en realidad necesitamos, digamos, estudios posteriores para entender mejor, digamos, este fenómeno. Y por último, estos resultados nos estimulan, ¿cierto?, para seguir realizando evaluaciones, especialmente el rol que la mitocondria tiene en la generación de esta patología. Termino agradeciendo, ¿cierto?, a nuestro team. Aquí estamos todos presentes. Muchas gracias.
Muchas gracias, doctor Gensi, por su presentación. Se abre entonces para preguntas de la audiencia. ¿Sí? ¿Una pregunta? Ah, sí, Pablo.
¿Se ha visto el cruce?
El micrófono aquí.
Gracias. En este estudio pudieron hacer algún cruce también en otra patología asociada, por ejemplo, la retinopatía diabética en las ratas que analizaron, si vieron aparte la otra parte de la fisiopatología de la diabetes o solo se enfocaron en la parte cardíaca.
No, tal como lo mencioné, no solo el corazón, sino que también nos enfocamos en la patología renal y por eso entonces hay información que va a ser presentada mañana en la exhibición de posters por Pamela Benavides, que, como decía, forma parte, digamos, del trabajo en este estudio, pero ella hizo la parte renal, con hallazgos bastante, digamos, interesantes también.
Me fijaba en las láminas Rienzi, tú presentabas el porcentaje de islotes, o sea, de células de Langerhans que sobrevivían. Eso, si tú lo proyectas en un posible target de tratamiento, por lo que hemos conversado previamente, ¿qué tipo de moléculas podrían estar previniendo a nivel de diario, a nivel nacional, ese tipo de patología? ¿Hay algún estudio que se haya hecho con quimiopreventivo, algo que esté en avance?
Bueno, obviamente todos los antioxidantes, digamos, tienen un rol, digamos, en esta condición, digamos, cardiometabólica. Resveratrol, por ejemplo, es una molécula, digamos, que se ha utilizado. Al mismo tiempo tú tienes una serie de, digamos, de trabajo en plantas medicinales, digamos, y yo creo que por ese lado, digamos, probablemente en el futuro vamos a tener fármacos, digamos, que puedan proteger, digamos, a estos pacientes.
Bueno, te lo preguntaba porque hay muchos estudiantes de magíster y obviamente este es un muy buen modelo para estudio, lo que tú planteas. Así que eso, muchas gracias por la respuesta. Gracias, Tamara.
Por la pregunta. Gracias.
Okay. So, Gary and
Thank you, Renzi. So your model probably models type 1 diabetes more than type 2. Is that correct? There have been criticisms of that particular
Yeah,
model.
I think that there is a lot of controversy today. And our model, I think that represents more type 2 diabetes than
so?
type 1, yeah.
Because the glucose transporters are involved. I'm just thinking out loud that with the increasing use of Ozempic, for example, that there might be some unseen cardiovascular effects.
Mm-hmm. Yeah, I agree.
¿Me escuchan? Ya. No trabajo, pero soy inmunólogo. De ese punto de vista, se mencionó entre algunos de los efectos del modelo la aparición de inflamación. Hay además fibrosis. Me pregunto si ustedes han hecho algún estudio histológico de marcadores inmunológicos, células y citoquinas y otros factores que podrían estar contribuyendo a la situación. Si no se ha hecho, yo creo que sería bueno complementarlo porque creo que es otro de las armas que tiene cualquier modelo biológico para explicar este tipo de cosas.
Exacto, no, tú tienes toda la razón, el doctor Povea, y por eso yo, en uno de los diapositivos, incorporé lo que tú señalas, porque realmente es para futuras, digamos, investigaciones, ¿no es cierto? Como tú señalas, probablemente existe una interacción aquí a nivel de corazón, ¿cierto? No solo, como decía, entre los cardiomiocitos y las células endoteliales, sino que también en las células, digamos, relacionadas con el sistema inmune. Y por lo tanto, claramente, eso probablemente lo vamos a incorporar como futuras investigaciones en nuestro modelo. Es un buen nicho, digamos, de investigación, sin duda.
Muchas gracias, doctor Rienzi. Mi pregunta era sobre las mismas proteínas citrulina. ¿Podrían ser un blanco terapéutico? ¿Bajo ciertas condiciones pueden aumentar? ¿Pueden incrementarse o disminuir? No sé. ¿Incluso con alguna terapia farmacológica?
Efectivamente, esa es la idea. Nosotros pensamos que probablemente citrulina 1 es un posible blanco terapéutico. De hecho, hay algunos estudios que han aparecido, digamos, mostrando esa vía, digamos, de terapia. Pero también aparecieron otras sirtuinas relacionadas fundamentalmente con la mitocondria, como es la sirtuina 3. Yo creo que eso también probablemente va a formar parte de nuestras futuras investigaciones. Exacto.
Muchas gracias.
De nada.
Bien, entonces ahora tenemos a nuestro siguiente expositor. Bueno, también es ya de la casa, conocido por todos nosotros, ¿cierto? Y querido por la Universidad de Valparaíso. Tenemos al doctor Jaime Riquelme, él también es PhD, del Departamento de Química Farmacológica y Toxicológica de la Facultad de Ciencias Químicas y Farmacéuticas de la Universidad de Chile. Y nos presentará estrategias cardioprotectoras más allá de los cardiomiocitos. So just for our international speakers, so now our next speakers is Dr. Jaime Riquelme. He's from the University of Chile, and he is going to talk about cardioprotection and beyond cardiomyocyte. Well, that's the title. Thank you.
Ok, muchas gracias. Si está bien, voy a presentar en inglés, considerando que tenemos audiencia que habla en inglés. All right, I'm going to switch to English now. Thank you. Gracias. So the title of this presentation is Cardioprotective Strategies Beyond Cardiomyocytes. I'm going to be talking about rather two cardioprotective strategies. But before that, as a small introduction, cardioprotection refers to all measures, strategies, treatments that can reduce myocardial damage in the context of ischemia reperfusion. But regarding myocardial infarction, while it's still one of the leading causes of death worldwide, we have to acknowledge that there has been a reduction in the mortality associated with myocardial infarction over the last 30 years, which means that we're doing a better job as humanity. Now we have statins, antiplatelets, beta blockers, and of course, changes in the lifestyle, which have significantly reduced mortality associated with myocardial infarction. However, while myocardial infarction is on the decline, heart failure is on the rise. And therefore, if the infarct size is reduced,
then the consequent heart failure will be less severe. And thus, there's still an unmet need to develop new cardioprotective strategies. I really like this slide because it's very simple and it explains the concept of cardioprotection. Myocardial infarction occurs as a consequence of ischemia reperfusion processes. If there is a prolonged ischemia with no reperfusion, then most of the tissue dies. You can see the TTC staining with the red staining means that it's viable, whereas the white staining means that it is infarcted. So we have this situation when, in the absence of reperfusion, then most of the tissue dies. And therefore, it is urgent to reestablish the blood flow into the ischemic myocardium. However, this process itself generates damage, and this paradox is known as reperfusion injury. Well, cardioprotection would be positioned here, where we can combine reperfusion with a cardioprotective strategy, which can be like ischemic preconditioning, treatment with drugs, etc. But I'd like to focus your attention on small extracellular vesicles, which are nano-sized structures that are spontaneously released from cells, which by virtually all cells in the body, and they can carry proteins, lipids, DNA, non-coding RNAs from one cell to another, and therefore these can be considered as a like a means of communication, intercommunication between cells. An important feature of extracellular vesicles is that the content of these vesicles depends on the physiological state of the cell, which means that if we have a cell in a pro-inflammatory state, then we will have pro-inflammatory markers released in these extracellular vesicles. That's why they're so attractive as potential biomarkers. But also, if these extracellular vesicles can carry protective signals, then they can be used as therapeutic agents. There was an early observation 10 years ago. This was done in the UK, where plasma extracellular vesicles from both human and rats could actually reduce the infarct size, both ex vivo and in vivo. But the plasma is it's a fluid that is very rich in different kinds of factors and components. So in order to clean this, we then focus on the endothelium as a potential source of cardioprotective extracellular vesicles. The endothelium is a central component of cardioprotective strategies. There are drugs that require the endothelium in order to exert cardioprotection, such as anesthetics, and they can release nitric oxide, and they can obviously also release small extracellular vesicles. So we characterize these extracellular vesicles by visualization using electron microscopy. We quantified and measured the size of these extracellular vesicles, which has to be approximately between 50 and 150 nanometers. It can vary, and express certain types of markers in the surface in order to assess that these are really extracellular vesicles. So we then tried an in vitro approach of hypoxia reoxygenation of adult rat cardiomyocytes. And you can see here that hypoxia reoxygenation increases cell death of these cardiomyocytes, but extracellular vesicles from HUVEC cells, which are endothelial cells, can actually reduce this cell death. We then confirm these results ex vivo in a later study, which show that these endothelial extracellular vesicles can actually reduce the infarct size as well. This made us think, we've been focusing on acute ischemia reperfusion, but we were wondering what else can these extracellular vesicles do? So we stopped focusing only on the heart, and we remember that the cardiovascular system is also composed of the vasculature, which has these different types of cells, like endothelial cells, this monolayer over here, and vascular smooth muscle cells. So there are many contexts in which these cells can be exposed to pathological stimuli, which can induce a dysfunction of these cells, such as the exposure to pro-inflammatory cytokines, which can impair the levels of enos, which is the enzyme that produces nitric oxide, and therefore regulate vascular tone. So we also have vascular smooth muscle cells, which normally have a contractile, fully differentiated phenotype, but upon pathological stimuli, these cells de-differentiate, and there is a phenotype switch from a contractile one to a synthetic phenotype, which has less contractile protein expression, increased migration, increased proliferation. So first, we tested these extracellular vesicles on endothelial senescence. Well, this is a cartoon showing normal endothelial cells. This would be a senescent endothelial cells, which can happen during aging, but also there can be premature senescence when these cells are exposed to pro-inflammatory cytokines or any other injury. So with a senescent cell, we have a bigger cell, and also which has stopped replicating and expresses these pro-inflammatory markers, and therefore it is in a pro-inflammatory state. These senescent cells have what is known as a senescence-associated secretory phenotype, where they release different kind of pro-inflammatory factors. So in here, we established our model of replicative senescence in Huvic cells, which was confirmed by increased beta-gal staining, and also the expression of P16 and P21, which are senescent markers, which are proteins associated with cell cycle arrest. And we also have a reduced expression of enos. Well, to treat these cells, we isolated and characterized extracellular vesicles from normal and non-senescent endothelial cells treated with or without interleukin-10. Interleukin-10 is a highly anti-inflammatory cytokine, and well, this is the standard characterization of extracellular vesicles. Here's the typical cup-shaped form, and we established that interleukin-10 did not alter the production or the size of these vesicles, and they also express CD81 and CD63, which are EV surface markers. However, when we measured the levels of IL-6 or the mRNA levels of P65, we observed that replicative senescence produces an increase in IL-6 and the mRNA levels of P65, but treatment with extracellular vesicles isolated from cells treated with or without IL-10 were unable to reduce these levels. We don't know yet what could be happening, but we do speculate that senescent cells are highly damaged and possibly less responsive. So we tested this in normal endothelial cells exposed to TNF-alpha, which is a known pro-inflammatory cytokine, which reduces the expression of enos. But in here, we were able to see a preventive effect with our extracellular vesicles. That means that if we pre-treat these cells with EVs 30 minutes before administering TNF-alpha, we do see preservation of the protein levels of enos. But what about vascular smooth muscle cells? As I mentioned earlier, vascular smooth muscle cells can undergo this phenotype switch from contractile to synthetic phenotype. And one of the features is that these cells are highly migratory. So we treated cells with platelet-derived growth factor, which is a known inductor of the phenotype switch, which promoted migration of these cells. This is a wound healing assay. And interestingly, our extracellular vesicles seem to prevent the effects of PDGF. Moreover, PDGF treatment reduced the protein levels of contractile proteins such as alpha SMA, SM22, and calponin, which was prevented by treatment with extracellular vesicles isolated from normal endothelial cells. That was the first cardioprotective strategy, and now I'm going to briefly address the second one. Well, our focus currently is the angiotensin-converting enzyme 2, which is a known cardioprotective enzyme. I'm talking about the counter-regulatory renin-angiotensin system. As you all know, this is the classical renin-angiotensin system where you get like angiotensinogen. Renin transforms this into angiotensin 1, and AC, angiotensin converting enzyme, which is the drug target of AC inhibitors, produces angiotensin 2 from angiotensin 1. And angiotensin 2 has a highly vasoconstrictive properties. However, there's this other system that has counter-regulatory functions, and AC2 is an important enzyme of this other branch of the RAS system. So AC2 can produce angiotensin 1-9 from angiotensin 1 and can also produce angiotensin 1-7 from angiotensin 2. Both of these peptides, angiotensin 1-9 and angiotensin 1-7, are highly protective in ischemia reperfusion. They're vasodilatory peptides, so they have anti-hypertensive and anti-hypertrophic properties. And, well, first of all, this was not performed by us, but this is the literature showing just one of the multiple studies showing the importance of AC2 in myocardial infarction. So if we have a deletion of AC2, then this can lead to higher mortality and adverse cardiac remodeling post-myocardial infarction. But moreover, we established a few years ago that treatment with angiotensin 1-9 can actually reduce the infarct size, and if we use an antagonist of the AT2 receptor, which is activated by angiotensin 1-9, this effect is lost. And so AC2 is a protective enzyme, particularly because it generates these peptides. But how can we control this enzyme? So there is this drug called imidazine acetate, which is a drug currently used in veterinary medicine, not currently used in humans, but there are many studies showing that this drug is actually an activator of AC2. So we treated endothelial cells with this DICE drug with different concentrations at 24 hours, and it seems to increase the levels of AC2 in a concentration-dependent manner. So we then, again, tried this model of TNF-alpha, where this cytokine decreases the protein levels of eNOS, but this seems to be prevented by pre-treatment with DICE at 2 different concentrations, 1 and 10 micromolar. Now, regarding vascular smooth muscle cells, we can see again that PDGF stimulates migration of vascular smooth muscle cells, but then this effect seems to be prevented by the administration of DICE, the activator of AC2. And accordingly, the expression of contractile proteins, again, is reduced by administration of PDGF, which is inducing the phenotype switch, but administration of this AC2 activator at 2 different concentrations seems to prevent the loss of these proteins. So, in order to finish this, I just wanted to link these 2 strategies. So this is another isolation and characterization of extracellular vesicles. Here you can see the typical cup-shaped form of these EVs. Here you can see the surface markers which are present in the cells. This is the cell lysate, but also present in EVs, except for GM130, which is negative control and therefore should not be there. But interestingly, we also have CD81, which this was determined by an ELISA assay, but also these extracellular vesicles can carry AC2, can transport this enzyme. Now everything becomes full circle when we still have preliminary data, but we treated isolated mice hearts and subjected them to global ischemia reperfusion, and again showed that these extracellular vesicles can protect the myocardium, but this effect seems to be lost when we use an inhibitor of AC2. This does not mean that the only reason why EVs are protecting is because of AC2. We're just saying that it may be a part of this cardioprotective effect, and we wanted to explore more chronic effects of these cardioprotective strategies, not just proving that it can reduce myocardial infarct size in an acute setting, but it can also be considered as a preventive strategy, such as statins, such as beta blockers. Of course, we are a long way from the clinical arena, but we like fundamental science. So for the moment, we can say that endothelial extracellular vesicles can protect the myocardium from ischemia reperfusion injury. These EVs can also prevent the loss of enos induced by TNF-alpha in endothelial cells, and can also prevent the phenotype switch of vascular smooth muscle cells induced by PDGF. And on the other hand, pharmacological activation of AC2 can prevent the loss of enos induced by TNF-alpha, prevent the phenotype switch of vascular smooth muscle cells induced by PDGF, and lastly, mediate at least part of the cardioprotective effect of endothelial EVs in ischemia reperfusion injury. This obviously has raised the provocative idea of what we can do with this. We're currently trying to overexpress AC2 in these extracellular vesicles to see if we can achieve further protection. But the results of that will be presented at the next symposium next year. So I'd just like to thank my team, which is a wonderful group of people, and none of this would happen if it wasn't for them. And also my collaborators, some of them are here, I have many more. And that's it. Thank you very much.
Muchas gracias, Jaime. Thank you very much, Jaime, for your presentation. It was great. Preguntas, questions? Okay, uno.
That was a great talk. So we've looked at extracellular vesicles in response to TNF-alpha. So, and we see a change in their content, both the number and content. Do you have any evidence along those lines?
Well, we have published a paper showing that if you treat endothelial cells with TNF-alpha, well, TNF-alpha is going to induce all the pro-inflammatory changes. It doesn't seem to affect the morphology or production of EVs, at least with 10 nanograms per mil. But interestingly, these EVs cease to protect. When they come from pro-inflammatory cells, they are unable to reduce the infarct size. That's all we know, but yes.
Hi, thanks for the presentation. About endothelial cells, you have looked at different endothelial cell types because endothelial cells are not similar across the life score and also within the body. So have you tried to look at pulmonary endothelial cells because most of the angiotensin is converted by the endothelial cells in the lungs. So maybe you should, instead of increase the expression, just use the right type of endothelial cells to produce your response.
That's a great suggestion, actually. I never thought of it. Yeah, it's a very good idea. Thank you very much. Yes, regarding the endothelial cells that we're using, yes, HUVEC cells are always exposed to criticism because they are from umbilical vein, and I understand that this may be far from what we're doing. I do have to say that there are multiple studies, not just by our group, but multiple studies showing that these cells can actually produce protective EVs. But we're definitely thinking about switching to other, like closer to the myocardium. So there are these myocardial endothelial cells, but it is a cell line, which would be closer to what we're thinking. So we could definitely change. But it doesn't mean that HUVEC EVs are worthless. They're actually shown quite a lot of protection.
No, I mean, from the physiological point of view, maybe also can open interesting stuff because the heart and the lungs are quite close, and all this blood that goes out, the heart goes back by passing through the lungs. So maybe if you simulate production, you can imagine just with using aerosols, you can protect someone from a cardiac.
That's a very interesting idea. Thank you very much.
So thank you very much also for the presentation. I'm going to defend HUVEC cells. But the idea is that, so there is a technique called symbiosis in which you connected a young mice with a older mice, and then the young mice transfer, the molecules or any stuff that rejuvenates the oldest mice. So in this model, you are using HUVEC cells, which is fetal cells, and perhaps it's the reason why you saw that protective effect, because it's perhaps most closest to the stemless cells, and therefore can improve the function of your adult cells. So this is one of another point of view of the same data. But the question was about regarding the combination of the human now with the mice cells. So, I know that there is myself having published the idea, to using extracellular vesicle from human, but treating cells from animal. So, in this case, I wonder, have you, controlled the idea that you are using human extracellular vesicles from the mice to treat the mice?
That's a great question. First of all, go HUVECs. And secondly, yes, we've really been focusing on actually seeing an effect. But now we obviously have to get serious about it, and we have to start working on compatibility and other stuff. I really mean that we are going to switch endothelial cells to working something closer to the heart and the species that we're working with currently. But yes, this is definitely a point to consider.
Okay, so thank you very much. Muchas gracias. Okay. Okay, so perfect. So, ahora podemos pasar a nuestra siguiente y final expositora de la jornada de la mañana, que también estoy muy contenta de presentar, porque es de casa, es de la Universidad de Valparaíso, de nuestra Escuela de Medicina, de Campus San Felipe. Ella es la doctora Alejandra Espinosa, que nos va a presentar efectos de compuestos bioactivos derivados de desechos vegetales contra alteraciones en la enfermedad hepática grasa asociada a disfunción metabólica. So, just for our international speakers, so she is Dr. Alejandra Espinosa. She's a professor here at the University of Valparaíso, but she's also from the School of Medicine, but at Campus San Felipe. So she will be presenting us bioactive compounds derived from vegetal wastes in the management of metabolic dysfunction associated steatotic liver disease.
Gracias, primero que todo, gracias a todos los asistentes y a Tamara por invitarme. Les quiero hablar un poco de una serie de experimentos que hemos estado realizando en el Campus San Felipe, asociados a un proyecto junto al Centro de Estudios Regionales de Alimentos Saludables de Valparaíso. Y vamos a partir hablando acerca de qué es el muscle. Como aparece acá, tal vez es un término relativamente nuevo, pero yo creo que la mayoría de ustedes lo conocen como enfermedad hepática alcohólica, no alcohólica del hígado graso. Entonces, este nombre cambió recientemente porque se ha visto que la etiología de la enfermedad tiene principalmente un origen cardiometabólico y además no se puede descartar que el daño progrese en función del consumo también de etanol. Por lo tanto, partimos desde la base de que una ganancia excesiva de peso puede generar una serie de alteraciones a nivel metabólico en tejidos blancos relacionados con la homeostasis de la glucosa, como el tejido adiposo, el músculo esquelético, y todo esto nos va a llevar a que a nivel sérico encontremos un aumento en los ácidos grasos libres, hiperglicemias prolongadas y también una predisposición al desarrollo de la diabetes tipo 2. Cuando tenemos una oferta importante de estos nutrientes que no son metabolizados debido probablemente a una resistencia a la insulina que se encarga de hacer que todos estos nutrientes vayan al anabolismo del celular, todo este aumento de ácidos grasos libres, por ejemplo, pueden llegar al hígado y generar este grado de esteatosis, que si esto progresa en el tiempo, puede pasar a una esteatohepatitis y finalmente a cirrosis hepática, y esto puede llevar también a cáncer. Por lo tanto, existen una serie de estrategias dentro de las principales, serían algunos fármacos y cambios en los estilos de vida, pero también podemos pensar en utilizar los llamados compuestos bioactivos que provienen de generalmente plantas, y en este caso yo les voy a hablar un poco de desechos de la industria que son de fuentes vegetales. Y un compuesto bioactivo podríamos decir que corresponde a un constituyente de la dieta, pero que no se considera un alimento esencial para las funciones vitales del organismo, pero que sí se ha visto que puede tener efectos beneficiosos para la salud. En esta revisión aparecen, es un mapa de calor donde nos muestra diferentes marcadores de salud metabólica y acá diferentes compuestos bioactivos que se ha visto que tienen beneficios contra, por ejemplo, salud hepática, o sea, en beneficia la salud hepática. Y ahí podemos destacar, por ejemplo, la curcumina, el resveratrol, que ya lo escuché por acá, y, por ejemplo, el café. De hecho, ya está sumamente claro que consumir alrededor de 3 tazas de café al día ayuda bastante a disminuir la progresión de esta esteatosis hepática. ¿Y qué tienen estos compuestos bioactivos? Muchos tienen en común el hecho de que contienen grandes cantidades de polifenoles. Los polifenoles, por ejemplo, se han caracterizado y se han clasificado, por ejemplo, en las flavonoles, los ácidos hidroxicinámicos, etc. Y como ustedes pueden reconocer en esta tabla, aquí tenemos, por ejemplo, los berries, el café nuevamente, manzanas, etc. ¿Cómo funciona un antioxidante? Porque nosotros siempre escuchamos hablar del término, pero probablemente muchos de nosotros no sepamos cómo nos protege frente al daño. Entonces, si nosotros estamos en presencia de un agente radicalario, como un radical libre, esto significa que simplemente es una molécula que tiene electrones desapareados. ¿Y dónde va a ir a encontrar ese electrón que le falta? Generalmente en moléculas de nuestro propio organismo, y de esa forma se genera el daño. Si pensamos, por ejemplo, en membranas biológicas, se puede generar daño relacionado con lipoperoxidación. Entonces, un oxidante lo que hace es ceder este electrón que le falta a la molécula y de esa forma neutralizarlo. Existen varios vegetales, frutas con alto contenido de polifenoles y también se han estudiado bastante, pero la industria genera también muchos desechos, los cuales se van generalmente a compost y no se están utilizando. Y si nosotros tratamos de investigar el contenido y la cantidad de polifenoles que tienen estos desechos, podemos ver que se pueden utilizar también como productos bioactivos. Aquí aparecen enumerados una serie de desechos, por ejemplo, de las hojas de los olivos que generan el aceite de oliva. Tenemos también desechos de la industria que procesa mango. Y les dejo ese último artículo que fue el que publicamos acerca de los efectos de las hojas de chía, es decir, de la planta, porque nosotros todos sabemos que consumir semillas de chía contiene una serie de precursores para después generar EPA-DHA, pero nadie había estudiado las hojas que se desechan. Y acá les muestro un resultado de ese artículo donde podemos ver una histología hepática, control, una histología de ratones que fueron alimentados con una dieta alta en grasa, que ya en 2 meses genera esteatosis hepática. Eso se puede evidenciar por la gran cantidad de gotas lipídicas que puede aparecer en la histología. Y a estos animales los tratamos con 2 cepas diferentes de chía, con extractos alcohólicos de las hojas, y logramos obtener una reducción en el grado de esteatosis y también en los niveles de lipoperoxidación. En rojo acá podemos ver el colorante body C11, que se une a lípidos neutros, y de esa forma podemos ver el contenido de grasas, pero cuando cambiamos la longitud de onda de excitación de esta sonda, podemos detectar niveles de lipoperoxidación en verde. Entonces, en A tenemos la condición de ratones alimentados con dieta alta en grasa, y en B el efecto del extracto de la chía blanca, y en C el efecto del extracto de la chía negra. Y después que cuantificamos, logramos evidenciar que había disminuido el grado de lipoperoxidación de las gotas lipídicas. Los resultados que les voy a presentar son resultados preliminares de un proyecto regional que fue adjudicado por el grupo CREAS y en el cual yo soy la investigadora principal, y estamos evaluando cuál es el efecto del bagazo cervecero en la recuperación del hígado una vez que se ha dañado debido a una dieta alta en grasa. Entonces, contarles que el bagazo cervecero es lo que queda de todo el proceso de fabricación de la cerveza, y actualmente se usa como compost también, pero si se rescata y se somete a una serie de cambios para secado y tratando de tener temperaturas óptimas que protejan el bagazo, podemos tener una mezcla importante que contiene alta fibra dietaria y un importante contenido de diferentes tipos de polifenoles. Principalmente ácido ferúlico, que ya se ha descrito en la literatura, que tiene muchas ventajas a diferentes niveles y principalmente como una molécula antioxidante. Pero también el bagazo cervecero tiene grandes cantidades de arabinoxilanos que se ha visto que protegen mucho a nivel intestinal, cambiando la microbiota de estos animales. El protocolo que nosotros hemos utilizado para tratar de evaluar cómo se comportan los animales que consumen bagazo cervecero es el siguiente. Trabajamos con los ratones de la cepa C57 Black, los cuales son alimentados por 8 semanas con una dieta alta en grasa, con un 60% de grasa en total, y de esa forma ya a las 2 semanas generan resistencia a la insulina, obesidad, aumento del tejido adiposo y estatosis hepática. Luego, estos animales fueron divididos en un grupo que consumió dieta control, otro grupo permaneció con la dieta alta en grasa, otro grupo incluimos 25% de bagazo cervecero a la dieta y el último un 50% para ver si existía algún efecto de dosis y medimos una serie de parámetros relacionados con metabolismo básico. Los pesos de los animales antes y después del tratamiento se pueden observar acá, donde podemos ver en la segunda barra que los ratones que seguían consumiendo High Fat Diet siguieron aumentando de peso y era lo óptimo. Pero los que consumieron bagazo, sobre todo el de 50%, su peso disminuyó de manera significativa. El consumo de alimento de estos animales no fue diferente en los 3 primeros grupos, pero sí observamos que el que consumía High Fat Diet más 50% de bagazo consumió mucho más alimento, lo que fue bien sorprendente, pero si uno lo piensa también, si uno está a dieta y come lechugas, tiene que comer muchas más lechugas y frutas para tratar de seguir más o menos consumiendo el mismo tipo de cantidad de calorías. El peso final, entonces, está representado acá, donde el grupo High Fat Diet muestra que sigue aumentando de peso en el tiempo. Luego que culminamos los experimentos y terminamos la eutanasia, medimos grasa visceral. Pueden ver aquí que el High Fat Diet respecto al control aumentó mucho su grasa visceral y que con la dieta con 50% de bagazo hubo una disminución de este peso. El colesterol, los resultados fueron similares en el colesterol plasmático y los triglicéridos no variaron de manera considerable, y esto es lógico porque en el fondo la dieta alta en grasa lo que produce es aumentar principalmente el colesterol. Cuando nosotros consumimos dietas que son ricas en fructosa, por ejemplo, esperaríamos triglicéridos elevados. En este gráfico tenemos las curvas de tolerancia a la glucosa después del tratamiento, en el cual el grupo High Fat Diet presentó obviamente los valores más elevados. Acá está el área bajo la curva que deriva de este gráfico. Y también podemos observar que tanto con un 25% de bagazo como con un 50% se obtienen resultados importantes de disminución del área bajo la curva. Cuando medimos los niveles de insulina plasmática, logramos ver que el grupo High Fat Diet tiene niveles de insulina mucho mayores que los que siguieron con la dieta control, y esto era esperable y corrobora lo que ya hemos descrito en este modelo. Y los niveles de insulina bajaron bastante con el consumo del 25% de bagazo y el de 50%. Este es el aspecto de los hígados cuando posterior al momento de la eutanasia, y ustedes pueden ver que los que siguieron con dieta control, macroscópicamente se ve un hígado relativamente saludable. En cambio, el High Fat Diet es un hígado de mayor tamaño y de un aspecto más esteatótico, y cuando se trabajó con las dos concentraciones de bagazo, el aspecto del hígado era mucho mejor. Este es el peso del hígado y podemos ver que la dieta con 50% de bagazo mejoró bastante el peso del hígado. Medimos también las clásicas transaminasas, que son marcadores de daño hepático, y podemos ver que tanto la ALAT como el ASAT aumentaron, solamente ALAT aumenta en High Fat Diet, no tanto así ASAT en High Fat Diet, pero sí los tratamientos con bagazo lograron una disminución significativa de la actividad de esta transaminasa. La razón entre ambas transaminasas es un marcador de esteatosis hepática. Cuando tenemos esta razón cercana a 2, nos indica que el hígado está infiltrado con grasa. Y si al hacer esta relación logramos ver que las diferencias fueron bastante importantes cuando los animales estaban tratados tanto con el 25 como con el 50% de bagazo cervecero. Finalmente, mostrarles estas histologías donde cuantificamos el grado de esteatosis, por una parte de micro y por otra parte de macroesteatosis, y las sumamos, y aquí podemos ver el gráfico que representa el estudio de estas histologías, donde podemos ver que la disminución que generaron ambas dietas suplementadas con bagazo fue bastante importante respecto a la dieta High Fat Diet, que si ustedes pueden ver ahí, la esteatosis hepática se ve de manera evidente. Esta es una máscara que nos muestra de manera más clara cómo está la infiltración grasa en el hígado. Hicimos un score también, que esto es importante tenerlo en cuenta, que el score para humanos en esteatosis hepática no nos sirve para trabajar con animales, así que les dejo ahí también una revisión donde aparece la forma en cual se evalúa la esteatosis en los modelos murinos, ¿ya? Y bueno, vimos que el High Fat Diet tiene un score de 2 respecto a los otros dos que llegó solo score de 1. Entonces, como conclusiones hasta el momento, tenemos que reemplazar un 25% de la High Fat Diet con bagazo cervecero. Es capaz de reducir el peso total de los animales, los niveles de colesterol, de insulina y esteatosis hepática similar a la dieta control. Y reemplazando el 50%, ahí tenemos cambios mucho más evidentes también en el peso hepático, el colesterol, la insulina, las transaminasas y el grado de esteatosis hepática. Este es el equipo de CREAS. Ya aquí el proyecto lo lidera la doctora Lida Fuentes junto con Carmen Soto, y sus investigadores contribuyeron también a generar los protocolos y caracterizar el bagazo cervecero. Este es el equipo de San Felipe, donde tenemos acá a nuestro técnico, que es Bruno, el profesor Roberto Villalobos, que debería estar también presente en este simposio, y estudiantes de medicina del campus San Felipe que nos están ayudando con las mediciones. Eso quería mostrarles. Muchas gracias.
Por la presentación. ¿Algunas preguntas, preguntas para la doctora Alejandra? ¿Sí? Ok.
Muchas gracias. Muy interesante la presentación. Una consulta sobre lo bonito que tienen en los resultados es que ya con el 25 no tiene efectos fisiológicos. Si uno lo quisiese traspasar al humano, ¿cuál sería el nivel de intensidad de la dieta que ustedes elegirían?
Gracias por la pregunta. Imaginémonos que, por ejemplo, nos comemos todos los días 4 Big Mac con doble porción de hamburguesa, ¿cierto? Pensando que tiene un 60% de grasa. Si comemos 4, pero decimos ya, ahora quiero bajar de peso, y en vez de comer 4 me como 3 Big Mac, y uno es reemplazado por una galleta de bagazo, correspondería aproximadamente a estos resultados con el 25%. Yo trato como de explicarlo así, porque en el fondo, claro, uno podría pensar que, obvio, si como reemplazo la grasa por otro alimento saludable, obvio que voy a bajar de peso, pero es que acá lo interesante es que esos resultados llegan a ser comparables con la dieta control, es decir, como si yo cambiara esas 4 hamburguesas por comida de menos calorías, ¿me entiendes?
Thank you. That was a wonderful talk. My question is just curiosity. In the 50% beer, whatever it was, the food intake went up substantially, but you didn't see any changes in body weight. Were you surprised by those results, and any thoughts on that?
Yes, it was surprise. Yes, and for this reason, we think that is amazing result because you can compare the bagasse beer with a super food because it's better than the control. And I think that is because there is a lot of components, bioactive components, maybe like polyphenols and the arabinoxylans. And for this reason, maybe bagasse can change the microbiota for one part, and for another, the metabolism of the mice for the high content of polyphenols. Maybe this is the reason, and we need to make a lot of different measures after that. For example, antioxidant capacity, a lot of gene expression related with stress, oxidative stress, something like that. Yes.
Hola, hola. Respecto de el avance de la investigación hacia el ensayo clínico, todavía no hay avances en ese aspecto. Podríamos esperar, o quizá hay otros estudios que hayan evaluado, quizá no el bagazo necesariamente, pero sí algún modelo similar o algún tratamiento similar en humanos. Se esperaría que los efectos en humanos fuera muy similar a lo que observan en el modelo animal. En base a los parámetros que vemos, no se saben.
No se sabe. El bagazo no es peligroso. De hecho, yo lo he comido. Es como una galleta. Por lo tanto, pienso que no sería riesgoso llegar a diseñar un pequeño piloto con humanos. Pero necesitábamos evaluar primero qué ocurre con la salud hepática, con efectos mucho más concretos que puedan verse en un modelo in vivo, para demostrar que realmente tiene razón de ser seguir estudiándolo como compuesto bioactivo, porque podría ser solo la teoría. Pero aún no hay nada y probablemente en un próximo proyecto lo diseñemos algo así.
Súper, gracias.
Bueno, doctora Alejandra Espinosa, tiene un hermoso trabajo, además ella de la casa, de la Universidad de Valparaíso, de nuestro orgulloso de todo su trabajo, que es muy bonito, y además es mujer, certificamos aquí de la universidad, así que muchas gracias, Alejandra, por haber venido y participar.
Gracias a ti.
Okay, so we have finished for the morning. Now it's a lunch break. Hemos terminado por la mañana, ahora tenemos receso de almuerzo y volvemos a las 3 de la tarde, ¿sí? A las 3 en punto. 3 o'clock. We have to be at 3 o'clock. It's my presentation at 3 o'clock. Okay. Estamos entonces a tiempo, estamos de hecho 2 minutos tarde, así que vamos a partir. Les agradezco entonces por volver a la sesión de la tarde. Ahora en la sesión de la tarde tenemos 5 exposiciones. Se dividirá en 2 bloques, primero 3 exposiciones, luego tenemos un café a las 16:30 hasta las 5 y luego de 5 a 6, que finaliza el simposio por el día de hoy. Bueno, y ahora tenemos las primeras 3 exposiciones. ¿Vengo yo primero? Después viene la doctora Samantha Thomas de la Universidad de Valparaíso y luego viene el doctor Carlos Escudero de la Universidad del Biobío. Mi nombre es Tamara Sáez, doctora de la acá trabajando acá en la Universidad de Valparaíso. Voy a pasar ahora al inglés para mi presentación. So I'm going to switch to English because I'm going to do my presentation in English for Gary and also for Sandy. So thank you for coming back to our afternoon session. I'm going to talk about premenopause and diabetes as an early evidence of cardiac damage. This is going to be a kind of short presentation, and I want to show you a preliminary work of our grant that we got last year. So I'm lucky because Rienzi already talked about diabetes mellitus, so I don't have to go over that, but just to remind you that diabetes mellitus is a hyperglycemic condition that it actually has severe consequences on health, and this is due because there is an impairment in the insulin activity that impairs glucose metabolisms. There are 3 types, gestational type 2 and type 1 diabetes, but diabetes type 2 it's more than around the 90% of total cases. Diabetes is a global problem. There is the diabetes mellitus. It's around 10% of total cases of diabetes, and this is happening all over the world, like in most of the country, especially when we have problems with obesity, you can also find increased problems with diabetes type 2. So 10%, it's a huge number, yeah? And in Chile, actually, we are around 11%. Also, worldwide, and also in Chile, we found sex differences. While worldwide, you can find sometimes in some places, there are the same amount of people, women and men, that they have diabetes, that it doesn't matter if it can be type 2 or type 1, all combined. In countries like Chile, we have more women that they are diabetic than men. The thing is that in Chile, for example, here in our country, if you go, for example, outside, ask your mom, ask your aunt, your sister, and then you ask, which do you think is the first cause of morbidity here or mortality here in Chile? And then everybody's going to tell you about breast cancer or kind of similar. But actually in Chile, women in Chile, they are diabetic. And one of the first causes of death for women in Chile is cardiovascular disease related to diabetes. Yeah? So the thing is that Chilean women, we are not aware of our cardiovascular risk. Chilean women, they are obese and they are diabetic in a very young age. So seeing now in this window from 2016 to 2017, in Chile, there are more women than men that they are diabetics. And this is a very important study that it was done in Denmark population, that it shows here in women than in men, the risk to develop cardiovascular disease over the year. So this is age. So here in women, you see, for example, when it is controlled general population, right? So they have here development of cardiovascular disease. But when they have diabetes, in this case is type 2 diabetes, then you can see that, for example, at 50 years old, the women now already have at least one cardiovascular complications, cardiovascular disease. So this is 10 years earlier than the rest of the women that don't have diabetes. In the men, it's a bit earlier, but it's around the same. It's like kind of around 10. But the problem with this is that 50, it's a window that most of the women go into menopause. And they are being diabetic prior this age. So when they go to the physician or ask for a glycemia test, they are already diabetic and they are already at risk to suffer cardiovascular event. So when will we have a window for prevention of these women? That's a question that we are trying to answer here, because we are losing people that they don't go to the doctor. They go to the doctor for breast testing, for other kind of tests, but they usually don't go for asking for cardiovascular health until the menopause or after that. The thing is that they are at risk when they are diabetic at a very young age, as you can see in this graph, right? The thing is that, so then diabetic women are more likely to develop cardiovascular disease compared to with diabetic men in other studies. And even these complications associated with diabetes are even more exacerbated in women. One of the main complications in diabetic patients is diabetic cardiomyopathy, as Rienzi already told us. It's a complication of the myocardium and is characterized by left ventricular hypertrophy and diastolic dysfunction. The pathophysiology is complex and is not well understood, as you can see here in this photo here. That's what we know is that it's hyperglycemia, insulin resistant. There are many others associated, and altered calcium handling, for example, in the cardiomyocyte, and oxidative stress, inflammation. What we can see first is diastolic dysfunction, but then there are several processes around cardiac hypertrophy, fibrosis, and others start getting into systolic dysfunction, and then they have heart failure when there is too late, and finally diabetic patients die from cardiovascular disease, because that's the main cause of death of diabetic patients. Diabetic cardiomyopathy, these complications, is greater in women than in men. So we can have men that they are diabetic, and we can have women, but the characteristic of how the development of this complication progresses in women than in men is always worse in women than in men. So here, for example, if we have female heart, so when they have diabetic cardiomyopathy, we can have exacerbated cardiac hypertrophy. We have first diastolic dysfunction, and then we go to systolic dysfunction. And then female heart with this with diabetes can also go to ischemic heart diseases, like another like atherosclerosis, nuclear dysfunction, etc. So my main message to now for you is, if you are young, if you're at risk to develop diabetes, please take care of your heart and your cardiovascular health, because we as women, we are thought to be protected by our hormones, but diabetes is our first enemy. We don't want the glycemia to go high. It's our main enemy. So this is something that we have to take into consideration, especially for physicians or medical students that are here, to take sex differences into consideration. So what I'm going to show you now is a preliminary work. This is part of my grant, national grant. So it's called Cardiovascular Disease and Diabetes Mellitus, a female study. So our first objective is to assess diabetic cardiomyopathy associated characteristic and cardiac cell function in young and premenopausal diabetic and not diabetic female rats. I'm going to show you now some part of these objectives. Not ready to show you cardiac cell function. I was being hopeful to have that for today, but unfortunately, I'm not that cool. But I'm just going to show you part of the experiment. This experimental design And I had to be very grateful because I have people in the lab that are helping me with this. I cannot be here showing you this data without Mario, Vanya, and Matthias. These 3 people are the best for me. Thank you very much for doing the experiments for me for today. So Vanya and Matthias, they were doing this to the rats. They were injecting rats with streptozotocin to cause increased glycemia in the rats. These are 4 months old rats, so they are young adult females rats. They were injected with streptozotocin, and we also have controls that they have vehicle. We followed them up for around 14 weeks, some of them, around 14 weeks. And after that, we sacrificed them. But prior to the sacrifice, we actually did echocardiography to all the rats. Then some of them, we did actually heart extraction for ion optics analysis. This was to do contractile function and calcium signaling. That's something that we hope that we can show you tomorrow in one of our posters that Mario will be presenting tomorrow. And we also did actually a DHE assay for reactive oxygen species in cardiac tissue. So first thing is that, okay, so we measure glycemia. So as you can see for 14 weeks, here is in white line, here is control, and then you see streptozotocin. Look at this. This is very interesting because I remember that one of the questions that Gary was talking about if the model that we have is diabetes type 2 or type 1. It's mainly used for type 2 diabetes, right? I think that most of us, we know that. But we haven't published this yet. But when you inject rats with streptozotocin, and then we do injected rats with insulin because they do need insulin, otherwise they die easily, you are actually able to revert the condition. So we think, and that is something that we want to test with Riancy, that depending on the dose of streptozotocin that you use, you can still have some remaining cells or beta cells and pancreas that they are able to produce some insulin that they can allow to the cells to survive and produce some insulin. That's something that we have to try. But anyways, they are mainly type 1, right, diabetes. So this is a window. See, the variation here is very high, but then they behave as a diabetes. Here is the summary. So it's different. They are hyperglycemic. About a mean body weight, they lost weight. And actually, you can see how they are losing weight during the whole process. You have to take care of them. They do need insulin. We treat them with insulin every 2 days. We inject them with insulin. They drink a lot of water as well, right? And then we weigh the hearts. So we compared here with the body weight, and we didn't see differences between groups. We also compared with the tibia length, and we didn't see that difference as well. Like probably we also have a small n number. But then we did the cardiometrics assessed by echocardiography, and I had to be honest, I didn't do that. It was this. It was this person, Dr. Gensidias. We are learning from him. He's teaching us. We are using an echograph. And we are looking here at the short axis of the heart. And then we analyze the diameters of diastole and the systoles of the hearts. And then we calculate the different parameters like volumes in the end volume in diastole and systole and systolic volume and stroke and injection fraction. So I'm going to show you that data now. So regarding the left ventricle diameter, because we were thinking about morphological changes caused by the treatment, and in diastole here, you can see the diameter of the left ventricle and you see how the left ventricle is increased compared to the control. And when it's have systole, we also have increased diameter in the cystotocin group compared to the control. So then we were like, okay, let's continue now. So we evaluated the volume. So stroke volume here, we found no difference in stroke volume between groups. And when we have diabetic rats comparing the end diastolic volume, we found they do have more volume. So when we have hearts that they have more blood volume, right, before they can eject the blood to the body. And then when we evaluated the end systolic volume here, so the volume that remains in the heart after ejection is greater here in the diabetic hearts as well. So we did then calculated the ejection fraction. We found that diabetic rats, they have reduced ejection fraction, and actually they have reduced shortening fraction as well. So what does mean? We have bigger hearts in the diabetic rats. They are dilated more, so they have more volume. They can eject more blood, but actually they don't because they don't have the force. So when they eject the blood to the body, they are not able to eject everything, so it remains a lot of blood in the heart, so they basically have heart failure. This is very important for us because we basically follow males under the same treatment in the prior study that Rienzi was showing you in the morning. And in that model, we didn't do echoes, but we did all histological imaging and those things. And it was very hard to find some changes associated to cardiomyopathy. But here in women, everything looks more severe. So it's something that is related to literature. We think that diabetes accelerate or exacerbate the cardiac damage. It's more pronounced in females than in men. And we'll do the frozen cardiac tissue sections here. This is staining for reactive oxygen species, specifically superoxide. This is red. It's like that because I thought that it was going to be quite hard to see, but now it looks like too much. Sorry for that. Yeah. So now here we compare controls versus cystotocin, and then you can easily see here, right, in this image, and then the summary graph, that there is increased ROS levels in this tissue. So conclusions, functional cardiac alterations suggest heart failure with reduced ejection fraction caused by hypoglycemia in these premenopausal female rats. These findings support the study of potential therapeutic targets to mitigate oxidative stress and its contribution to cardiac damage in premenopausal diabetic females. In these grants, we also have perimenopausal rats that they are 9-month-olds that they are going to be follow up for also another 14 weeks. And we expect that maybe it's going to be more severe or maybe going to be the same, but what we hope, what we are happy or not happy with this is that even when the rats are young, they do develop heart failure when they are diabetic. I think that's the most important message that I wanted to show you today. So thank you very much one more time to Dr. Rienzi Diaz, right, for everything, and Mario and Vania, those are our research assistants. Thank you very much, guys, for everything in the lab. And master students, Edison, Sofia, and also Matthias for all the efforts. Pamela, she's a PhD student. And Franco and Adolfo, they are medical students. They are helping us in the lab as well. And also funding agency and our center meeting. And you, of course. Thank you very much. happy to take any question para preguntas. So, okay. 1, 2.
I won the fight.
Okay.
That was wonderful. Thank you. And thank you for getting the messaging out about the female heart. It's very, very important. I was curious about the model, because this is because you give insulin every other day, but you still have hyperglycemia. So just curious of, are you trying to get to a steady, help me out with your model of the yin-yang of insulin and the hyperglycemia that you see?
That's a good question. Yeah, we are trying to keep them steady. We don't want them to get a normal glycemic. They have to be hyperglycemia, right? Because we want them diabetics. So we actually inject them with a very few units of insulin. So then we have a scale that we use. So when we test the glycemia, we use that scale to see how much high it is, and then how much units of insulin we have to give to the rats in terms to keep the rats alive, let's say, because otherwise they're going to die. You know, there's going to be a hyperglycemic shock. So we don't want that.
Thank you.
Thank you.
Again, a very nice presentation.
Thank you.
Can you, these are anesthetized rats, is that right?
These are Sprague-Dawley rats.
But they're anesthetized?
Yes, and it's high isoflurane.
Okay. Can you systematically change venous return so you can change the filling pressure? Because to get at contractility.
Not now. Not right now.
Okay.
Not for now. Yeah.
Because we do that with Millar catheters, where we can measure pressure volume. And if you could do that, the end-diastolic volume measurements would give you contractility.
Yeah, that would be great. Yeah, that would be great. We can do that at the Mayo Clinic, though, right? Okay. Thank you. ¿Alguna otra pregunta? Okay.
Muchas gracias, Tamara.
Gracias.
I try to speak English.
Okay.
Okay. Have you tried to measure the level of the insulin after the tolerance with glucose to try to demonstrate is the diabetes number 1 or diabetes number 2 involved?
No, we haven't, but it's something that we have been thinking about, because we are also going to test the insulin production in the pancreatic island. So, yeah, that's a very interesting thing. Thank you. Okay, I think that we are okay like that. Okay, ¿estamos bien con eso? Y ahora vamos a pasar al siguiente expositor. Muchas gracias. Okay. Ok, entonces ahora es el turno de la doctora Samantha Thomas Valdés. Ella es profesora de nuestra universidad, específicamente de la Escuela de Nutrición y Dietética de la Facultad de Farmacia. También estamos muy contentos de que ella pueda contar que nosotros podamos contar con ella este año, porque el año pasado no pudo, entonces estamos felices de escucharla. Su línea de investigación también es en desórdenes metabólicos, así que se alinea bastante bien con lo que es nuestro simposio, así que estamos felices de tenerla acá. Bienvenida, Samantha. So she is Dr. Samantha Thomas Valdés. She is a professor at the nutrition school here at the Faculty of Pharmacy at the University of Valparaíso.
Hola, buenas tardes. Un gusto estar aquí con ustedes. Lamento haber preparado mi presentación en español. Yo no sabía que tenía que preparar en inglés en realidad. Espero que logren acompañar. Yo voy a hablar en español porque Yo soy brasileña, entonces ya hice el switch para el español y hacer más un switch para el inglés, ustedes van a entender que me va a costar un poquitito, ¿ya? Bueno, yo soy nutricionista de formación, ¿ya? Y trabajo con polifenoles, ¿ya? Nosotros allá en la Escuela de Nutrición y Dietética, que queda aquí en Playa Ancha, trabajamos con polifenoles de frutos nativos y formulación de alimentos funcionales en contexto de obesidad. Entonces, adapté un poco el título de la charla, que era Uso de polifenoles en la prevención de desórdenes metabólicas en contexto de obesidad, porque serão modelos de obesidad que vamos a estar hablando hoy día. Yo podría traer aquí para ustedes muchos datos de obesidad. Todos sabemos que la obesidad es una pandemia, es un problema a nivel mundial, pero preferí traer datos chilenos que fueron publicados en las últimas 2 semanas, ¿ya? Que es justamente el mapa nutricional de la JUNAEB, resultados comparativos de 2023 y 2024, que salió en las últimas 2 semanas. Esos datos son muy relevantes de las escuelas públicas de Chile, ¿cierto? En donde se verificó que hubo un aumento de un 2,8% de exceso de peso, ya sobrepeso, obesidad, en un rango etario de muy baja edad, entre 4 y 5 años, ¿ya? Porque eso nos preocupa, obviamente nos preocupa porque son los niños que van a adquirir, ¿no es cierto?, toda la alimentación durante la vida. Esa etapa es sumamente importante para hábitos de vida y eso puede gatillar ahí el aumento de alteraciones metabólicas importantes a lo largo de la vida, ¿ya? Também se ha visto acá que houve um aumento de 0,6% em obesidade entre esses niños e niñas chilenas, ¿ya? Recordar, aqui é a fase onde eles vão adquirir seus hábitos de por vida, ¿ya? Também é importante recordar que agora, fines de enero de 2025, há um novo consenso para o diagnóstico da obesidade. ¿Por qué traigo eso para ustedes? Todavía no fue traducido para el español, ya todavía no estamos utilizando acá en Chile, pero eso es súper importante porque vamos a dividir entre obesidad preclínica y la clínica. ¿Cuál es la diferencia básicamente en eso? Que la obesidad clínica es donde ya hay alteraciones metabólicas importantes de algún órgano o tejido, y ahí es sumamente importante verificar medidas bioquímicas, ¿ya? Alteración de perfil lipídico, alteración, resistência à insulina, entre outros, vão ser elementos que vão estar entregando esse diagnóstico de obesidade, já onde já há um comprometimento de um órgano específico. Essa nova forma de realizar o diagnóstico vai utilizar o IMC, circunferência de cintura, o mais provável que seja circunferência de cintura, e esses parâmetros bioquímicos, quando estão alterados, vão indicar a obesidade clínica. De los 18 critérios clínicos utilizados para adultos, 6 são relacionados com o risco cardiovascular. ¿Ya? Entonces, claramente ahí la enfermedad cardiovascular tiene un rol súper importante y el control metabólico de esas personas también es sumamente relevante. ¿Ya? Entonces, aquí vamos a tener, siempre calcular primero el IMC y una medida antropométrica adicional, donde vamos a identificar no obesidad o sí con obesidad y ahí finalmente verificar si es obesidad preclínica o clínica. Les muestro isso porque isso é o mais provável que seja implementado, foi um consenso bem importante. ¿Ya? ¿Por qué es importante la obesidad? Bueno, la obesidad es un estado de inflamación crónica de bajo grado que va a generar una serie de alteraciones de manera muy silenciosa, ¿ya? Que va a gatillar una disfunción endotelial importante y eso altera la funcionalidad de una serie de tejidos, ¿ya? Aquí vemos que también tiene mucha relación con lo que es la microbiota intestinal. ¿Por qué les digo eso? Porque a alimentação, os polifenoles, fibra dietética, etc., têm um efeito diretamente hacia a diversidade da microbiota intestinal. E se ha visto que, tras alterar essa microbiota intestinal, eu posso predisponer as pessoas a generar enfermidades durante todo o ciclo vital. La microbiota y la salud humana es algo que es muy estudiado y tiene relación con una serie de elementos, sean metabólicos, existe el estudio de enfermedades cardiovasculares, a nível cerebral, de tejido pulmonar, etc. ¿Ya? Entonces, se ha visto que ao alterar essa microbiota naturalmente que está no intestino humano, eu posso predispor a uma série de alterações metabólicas e patologias. Essa diversidade microbiana é aumentada, ¿no es cierto?, desde que temos o feto hasta mais ou menos os 3 anos de idade, e durante a vida adulta já não tem muita alteração de por si, ¿ya? Reduzindo sua diversidade já quando somos mais adultos maiores. E que elementos são importantes para que vão determinar essa microbiota intestinal? Muitos. São muitos elementos hereditários, etc. Sin embargo, a alimentação é sumamente importante. Não somente para a pessoa, sino que também a alimentação materna, lo que a madre consume, isso vai determinar como vai ser a microbiota intestinal de esses niños, e essa alimentação vai prover de nutrientes, mas também fitoquímicos. E aí é onde nos interessa lo que são os polifenóis. Esses fitoquímicos, basicamente, são elementos que conferem defesa às plantas. Quanto maior estresse ambiental, maior concentração de fitoquímicos. Quais são os fitoquímicos mais famosos? São terpenos, são polifenóis, são alcaloides, que finalmente, quanto maior estresse ambiental, maior vai ser a síntese desses para proteger as plantas. Chile é um país muito estressado, se nós vamos ver desde o ponto de vista climático. Temos a Cordillera de los Andes, temos o deserto, a Antártida, temos condições muito adversas. Temos um tremendo hoyo na capa de ozono. Todo isso induz um estresse tremendo a las plantas, acá em Chile. E que faz a planta para defender-se? Fitoquímicos. Então, é super importante valorar o que se produz acá, porque são, de verdade, alimentos únicos e que, obviamente, podem generar benefícios à saúde humana. Então, Chile, ¿no es cierto?, tem essas condições climáticas bastante extremas. Respeito a esses fitoquímicos, a nós nos interessa maioritariamente os polifenóis, que estão ampliamente distribuídos em los alimentos. Aqui sale muito chiquitito, pero lo que está aqui em rojo são puro hidroxilos. Qual é a graça disso? Todo o que são hidroxilos podem donar eletrões e, por lo tanto, se temos espécies radicalares, vamos lograr reduzir o estresse oxidativo. É uma das principais funções aí de los polifenóis. E estão distribuídos em todos os alimentos de origem vegetal. Sin embargo, nós não temos enzimas metabólicas capazes de degradar todo isso, porque são moléculas bastante grandes, não podem ser absorvidas assim. Quanto nós logramos absorver dessas moléculas? Se temos sorte, 10%. Então, quem hace de verdade a pega do processo de metabolização desses compostos é a microbiota intestinal. Outra coisa importante, os polifenóis não estão dissueltos, não estão sueltos no alimento. Os polifenóis estão enlaçados à fibra dietética, e maioritariamente estão também enlaçados a lo que são açúcares não digeridos. São bubócidos, rafinócidos, são moléculas sumamente grandes que nós não temos enzimas capazes de digerir, pero sim a microbiota intestinal. Então, se ha dicho que os polifenóis poderiam ser uma espécie de prebióticos, porque resistem a todo o processo de digestão e chegam praticamente intactos ao cólon para ser metabolizados por la microbiota intestinal, formando os ácidos graxos de cadena corta e mantendo um pH intestinal apropriado para bactérias benéficas, aumentando a produção de moco e diminuindo a permeabilidade intestinal. Com tudo isso, eu estaria diminuindo, não é certo, essa inflamação de baixo grado crônica que nós vemos em todas as patologias crônicas. Pero por que então estudar esses polifenóis? Se ha visto que temos, aqui sale muito chiquitito, muito pequeno, pero há algumas cepas muito específicas de bactérias que são responsáveis por metabolizar algum tipo de polifenol. Então, se nós não temos essas bactérias, nós não somos capazes de metabolizar esses polifenóis e, por lo tanto, não vamos generar esse benefício ao nosso organismo. Então, é sumamente importante ter uma dieta variada e se aportar em polifenóis para justamente lograr essa diversidade microbiana apropriada. E aí, onde chega a frutilla blanca, que é onde eu quero chegar com vocês, é o alimento que nós temos trabalhado por muitos anos, ¿ya? A frutilla blanca é um fruto nativo chileno. Se nós consumimos hoje em dia frutilla, não, fresa, não sei como, aqui em Chile se diz frutilla, é graças a esta frutilla chilena, ¿ya? Que foi levada ao Palácio de Versalhes por os anos de 1700 e algo, e aí, de forma espontânea, se cruzou allá nos Palácios de Versalhes com a fragaria virginiana e formou o que é a fragaria por ananás, que é o que consumimos hoje em dia. ¿Ya? Qual é a diferença? Quais são as características? A frutilla, essa fragaria chiloensis, que é a frutilla blanca que nós trabalhamos, ¿ya? Ela é grande, blanca e muito blanda. Esse é o problema, por isso não se pode ser comercializada a larga escala, a largas distâncias, porque é muito blanda. Mientras que a fragaria virginiana é muito chiquitita e muito roja. Então, ao cruzar-se, quedou com o formato e o sabor da frutilla chilena e com o color da fragaria virginiana. ¿Ya? Onde encontramos isso? Isso é uma plantação de frutilla blanca no sul de Chile, em Contulmo. ¿Ya? Nós logramos encontrar allá e se vende comercialmente em dezembro. ¿Ya? Qual é a graça disso? Que polifenóis têm vários, ¿ya? E o que nos interessa são estes, ¿ya? Tem polifenóis que são de estruturas bastante grandes e isso nós não podemos digerir, ¿ya? Pero sim nossa microbiota intestinal. Nós hemos quantificado os polifenóis, ajudamos a caracterizá-los, ¿ya? Temos taninos hidrolisáveis, distintos tipos de flavonoides, etc. E aí o contenido é ao redor de 39 miligramas de contenido fenólico total por cada 100 gramas de fruto seco, fruto fresco. Começamos com essa excursão na frutilla blanca, já, sendo procedimentos de digestão in vitro, já. Para quem não conhece, procedimentos de digestão in vitro, uno hace um extrato, pode ser da forma que uno decida, e submete a distintos procedimentos de digestão, utilizando enzimas digestivas e pHs digestivos, para verificar se se mantêm os componentes e mantém a atividade. O que nós vimos é que, tras comparar esse extrato que nós hicimos de frutilla blanca com diferentes enzimas digestivas, nosso extrato era mais potente que a carbosa, que é um fármaco referente ao inibir a alfa-glucosidase. Então, pensamos, bueno, quizá poderia servir em vivo. Então, nós hicimos um pequeno estudo clínico muito chiquitito com 10 estudantes universitários sedentários que não tinham nenhuma patologia, não eram obesos, já eram só os sedentários. E hicimos uma intervenção. Primeiro, no tempo zero, esses estudantes consumiram 150 gramas de pão branco, já? E nós evaluamos glicemia e uma série de parâmetros, entre eles insulina e glicemia em os tempos de 0 a 120. Esses mesmos estudantes que deram 2 semanas em washout, voltaram e fizeram outra toma de muestra quando consumiram essa mesma quantidade de pão com uma taça de arándano. ¿Ya? Aí utilizamos o arándano porque o arándano era o que tínhamos disponível comercialmente. Com uma taça de arándano, evaluamos exatamente o mesmo. E depois, eles consumiram por 6 dias essa tacita de arándano todos os dias. ¿Ya? E voltaram ao laboratório no dia 7, sem consumir o arándano, consumiram só o pão. E aí nós tomamos muestra de sangue nesse período. E o que nós obtuvimos? Que o consumo agudo logrou reduzir de forma significativa a glucosa basal e a curva glicêmica também houve uma redução sumamente importante e significativa disso em los distintos tempos, já? E a área abaixo da curva também foi inferior. Para a insulina encontramos diferença somente no ponto em minuto 30, já? E aqui também a insulina basal foi um pouquinho maior para o consumo agudo. Então, o que nós vimos in vitro com a frutilla blanca, nós utilizando polifenóis, um alimento rico em polifenol como o arándano, poderíamos estar reproduzindo. E basicamente por quê? Bueno, quando nós consumimos um alimento que é fonte de hidrato de carbono, quando não consumimos com polifenóis, aumenta a liberação desses hidratos de carbono. Já? E isso prontamente absorvido. Sin embargo, cuando nosotros consumimos un alimento, que es fuente de hidrato de carbono, juntamente, en conjunto con un alimento fuente de polifenol, los polifenoles van a reducir la formación, la quebra de ese alimento y también la disponibilidad de esas enzimas digestivas y, por lo tanto, van a disminuir la absorción efectiva. Por lo tanto, yo voy a lograr hacer un control metabólico más efectivo, ¿no es cierto?, de esas personas si yo entrego junto con la comida, con esa fuente de hidrato de carbono, esos polifenoles. Bueno, pero aí nosotros también queríamos ver otras cosas, ¿ya? Queríamos ver qué pasa en un contexto de obesidad en un modelo animal, ¿ya? Considerando aquí, estábamos buscando estudiar el eje intestino-hígado, ¿ya? Y ver si efectivamente en un modelo de obesidad yo podría generar mejoras metabólicas en los animales. Aquí, quando temos a dieta alta em grasa, essa dieta alta em grasa, como eu les mencionei, altera a microbiota intestinal, ¿no es cierto? Aumenta esta permeabilidade e, por lo tanto, vai generar uma inflamação de baixo grado a nível sistêmico e que pode alterar distintos órgãos, como, por exemplo, o hígado, ¿ya? E dentro do hígado vai aumentar a resistência à insulina, vai aumentar a inflamação e vai aumentar a acumulação de partículas de grasa acá, ¿ya? Nossa hipótese é que suplementando esses animais com frutilla blanca, eu melhoro a microbiota intestinal. Vou lograr reduzir esta permeabilidade, reduzir a inflamação sistêmica e melhorar a saúde hepática. Veamos como nos foi. Hicimos um extrato, já um extrato etanólico, 80% etanol, 20% água, já um extrato de frutilla blanca. E os animais, a mitad de los animales, les dimos dieta alta em grasa por 12 semanas. 12 semanas é adequado para induzir obesidade e todas as outras alterações que vocês podem imaginar. Os animais de verdade quedam metabolicamente muito alterados, produzem esteatoses, produzem muitas alterações. Nós hicimos outros experimentos com 8 semanas. 8 semanas não alteram tanto, especialmente não altera a nível intrahepático. Já para 12 semanas, de verdade, os animais quedam bastante com um fenotipo de obesidade. Já? E animais do grupo control. Los high fat, la mitad recibiu por 4 semanas suplementação com frutilla blanca e os controles também, por 4 semanas. Já? Al dia pós-natal, 50 foram eutanasiados, recoletamos tejidos e heces, sangue, etc. O que nós vimos acá... O que passou? ¿Qué pasó? ¿Qué pasó acá? Pucha, bueno, acá, aquí lo que yo quería mostrar, ese gráfico del peso corporal. El peso corporal, finalmente, la frutilla blanca no impactó el peso corporal. Ya era eso que yo quería mostrar, que la frutilla blanca, los dieta control había una curva de peso más o menos por acá y de dieta high fat la curva era bien más arriba, aumentaron de peso y la frutilla no impactó en el peso corporal de los animales, ¿ya? Y el consumo de la dieta fue lo mismo, también evaluamos el consumo porque a lo mejor el peso se debiera al consumo, ¿no es cierto? Fue igual entre los grupos, no hubo diferencia. Acá, esse era o resultado interessante que queria mostrar, que antes já há diferença significativa entre os grupos controle e high fat, e aqui o que logrou, ao suplementar os animais com frutilla blanca, os animais high fat, já houve uma redução da glicemia basal. Nós hicimos o teste de tolerância à glucosa, já, mas não houve diferença. A única diferença que tivemos foi na glicemia basal. Nós hicimos a composição por 16S de la diversidade da microbiota intestinal e tampouco hemos tenido resultados já de lo que esperávamos. Se vocês veem esses pontitos acá, são os animais alto em grasa suplementado com frutilla blanca, que são muito parecidos, já. E acá, os animais control e control com frutilla blanca, que são muy distintos unos de los otros, a pesar de que esos son más dispersos, no hubo una diferencia significativa. Lo más probable es que los estudios suplementan, cuando suplementan con polifenol y suplementan con 8 semanas, ahí ya empiezan a entregar resultados significativos y cambian la microbiota, ¿ya? Pero nosotros evaluamos distintos tipos de vías metabólicas que podrían estar alteradas en esos animales y vimos que al comparar los animales alto en grasa con el alto en grasa suplementado con frutilla blanca, hubieron varias rutas metabólicas que estaban, hubo diferencia significativa, entre ellos la señalización del AMP y la secreción de insulina por acá, ¿ya? Entonces, eso podría, de alguna manera, el tema de la secreción de insulina, ayudar a explicar lo que pasó con la glicemia basal, pero nosotros no medimos insulina, así que no podemos afirmar esto, ¿ya? Pero quiero llamar la atención por la señalización del AMP, porque después vamos a ver que eso podría lograr explicar algunas alteraciones a nivel hepático. Respecto a la... Ay, no salió otra vez. Yo tengo el PDF, a lo mejor sería... Yo tengo el PDF también de la presentación, porque no va a salir, ¿no? A ver. Ven, no está. Ve, mira. Tengo el PDF, yo le envié. ¿Ya? Sí, por favor, porque si no, no van a ver ningún... No, yo me envié los dos, por si acaso. Mira, no sale nada. No, es que está horrible, si no va a crecer nada, yo voy solo a hablar. Sí, es que nosotros antes vimos y pasaba, pero... Ahí. Ahí. Ahí aparece todo, ya. Menú. Menú, ahí. Ver. Ahí.
Ver pantalla, modo pantalla completa. Arriba. Ahí.
Ya. Ahí sí. Ah, bien. Eso yo quería mostrar. Antes, ya eso del peso, ya. Acá son el control y control frutilla y high fat frutilla. Claramente la frutilla no tuvo influencia sobre el peso corporal, ya. Acá. Nosotros hicimos un experimento ex vivo de permeabilidad intestinal con un fluoróforo Destran, ¿ya? Que es una cinética por 3 horas, donde se hace pequeños saquitos, ¿ya? Uno pone dentro de ese saquito un fluoróforo. Entonces, cuanto más rápido sale ese fluoróforo para el medio, significa que tiene mayor permeabilidad intestinal en el tiempo, ¿ya? Que nosotros vimos acá en el ilium, bueno, los resultados no son tan relevantes porque para nosotros lo importante es high fat frutilla, y después de 3 horas en el tiempo, claro, los animales que fueron suplementados con high fat frutilla lograron mantener esa permeabilidad reducida, más reducida en el tiempo que el grupo que era high fat. Estamos haciendo análisis complementarios de PCR para cuantificar proteínas de unión estrecha para verificar qué pasó acá, qué tipo de proteína podría haberse expresado más. También hicimos un panel de citoquinas séricos para ver justamente lo que pasa con el perfil inflamatorio de sus animales, ¿ya? Hubo un aumento de la IL-10 en el grupo high fat suplementado con frutilla, hubo una reducción de la IL-2, una reducción de MIP-1A, una reducción del TNF-alfa y también una reducción de IL-6. ¿Ya? Entonces, efectivamente, esos compuestos que les mostraba antes, esos polifenoles que son gigantes, ya tienen un efecto antioxidante importante. Nosotros también cuantificamos en heces del ciego, ¿ya? Los principales ácidos grasos de cadena corta, ¿ya? Recordar que cuando esos polifenoles son metabolizados, y esos azúcares no digeridos son metabolizados, ¿ya? Ellos son capaces de sintetizar, la bacteria intestinal es capaz de metabolizar y sintetizar ácidos grasos de cadena corta. Los principales, el ácido acético, propiónico y butirato, ¿ya? Y propionato, y butírico. Si ustedes ven aquí, si vamos a comparar el high fat frutilla, ustedes van a decir, hoy aumentó un montón. Es obvio que aumentó un montón, porque esa dieta alta en grasa es 60% grasa. ¿Ya? Es mucha grasa y no hay casi nada de fibra, son animales que reciben menos fibra. ¿Ya? Cuando nosotros entregamos esta frutilla blanca, la frutilla blanca presenta muchos azúcares no digeridos y que finalmente van a actuar como sustrato energético para esa microbiota intestinal. ¿Ya? Entonces, hubo un tremendo aumento, si ustedes ven, casi el doble de lo que tenía de ácido acético, también para el propionato y también para el butirato, cuando comparamos con los animales que son altos en grasa. Entonces, y respecto a la salud hepática, ¿qué podríamos esperar? Como ya les dije, no hubieron diferencias significativas en la microbiota intestinal, en las bacterias intestinales, ¿ya? Pero sí esos ácidos grasos, esos polifenoles aportan en azúcares fermentables y ellos también son fermentados a nivel de colon, aumentando la producción de esos ácidos grasos de cadena corta. Se sabe que esos ácidos grasos de cadena corta son muy chiquititos, ¿ya? El acetato es 1 carbono, el butirato son 2 carbonos, el propionato son 3, entonces son muy pequeños y son capaces de permear distintos tipos de células y distintos tipos de órganos, ¿ya? Y se ha visto que a nivel hepático puede mejorar, aumentar la beta-oxidación, disminuir la lipogénesis de nuevo, etc. ¿Ya? Disminuir la inflamación, por lo tanto va a disminuir la esteatosis hepática, entre otros parámetros. Entonces, veamos lo que encontramos. Aquí, con la ayuda del profesor, del doctor Sebastián San Martín, ya va a haber un póster sobre eso, así que solamente les traigo un resumen ya de lo que hicimos con Sebastián. Aquí tenemos los animales, histología hepática de animales control tratado, high fat y high fat tratado. Se ve claramente una disminución de acúmulo de grasa, esas son las gotículas de grasa ya intrahepático. Visualmente uno logra ver y también cuando cuantificamos el área, hubo una reducción muy importante de área grasa absoluta de ese tejido. Cuando vemos fatores de transcripción hepático, hubieron muchas mejorías. Aquí es un resumen de lo que los polifenoles podrían hacer, ¿ya? A partir de la ruta MPK, estimulando esa ruta, va a aumentar el PPAR alfa y, por lo tanto, mejora toda la biogénesis de la mitocondria, aumentando la beta-oxidación. Y fue lo que nosotros vimos. ¿Ya? Hubo un aumento del PPAR alfa en los animales high fat con suplementación de frutilla blanca. También lo que los polifenoles pueden hacer, pueden inhibir el BP1C, que justamente aumenta todas las enzimas metabólicas relacionadas con lipogénesis. De nuevo, eso vimos que hubo una reducción de ese marcador. No tuvimos ningún cambio en SIRT1, pero también hubo una reducción de ese otro marcador que está relacionado con el metabolismo energético, más bien con hidrato de carbono, pero también se relaciona con la lipogénesis de nuevo intrahepática. Por lo tanto, la frutilla blanca estaría actuando ahí en diferentes dianas para mejorar la salud hepática. En resumen, la frutilla blanca en la microbiota intestinal nosotros no vimos resultados significativos, pero sugerimos que la suplementación debe ser por mayor tiempo. Parece que podría ayudar el control glicémico, pero eso solamente se ha visto en glicemia basal, pero los datos que tenemos con humano podrían avalar eso. Aumenta la producción de ácidos grasos de cadena corta en un contexto de obesidad. Podría tener un efecto ahí la permeabilidad intestinal. Nosotros estamos elucidando qué tipo de proteína de unión estrecha podría estar más expresada. Interfiere en el acúmulo lipídico, disminuye el acúmulo lipídico intrahepático y también mejora el perfil inflamatorio. Todos estos resultados fueron gracias a una serie de financiamientos previos, ya que tenemos que agradecer obviamente fondos irregulares de inicio y proyectos también internos aquí en la UV. Muchas gracias.
Muchas gracias, Samantha. Excelente presentación. De verdad, muchas gracias. ¿Preguntas? Any questions for Dr. Samantha? ¿Preguntas?
Muchas gracias por la presentación. Me quedé, creo que nos mostraste qué pasaba después en el tratamiento del pan y que le ponías arándano. ¿Qué pasaba después de los 7 días que comían arándano? Y entonces me quedé con la curiosidad nomás que si veías algo.
Está en el paper, yo traje solo lo que fue significativo. Hubo un efecto de aumentar la secreción de insulina, quizás por algún tipo de efecto incretina, ¿ya? Porque también una serie de estudios ha visto que el consumo de polifenoles, especialmente antocianinas, que es lo que tiene el arándano, ¿ya? Aumenta la síntesis y la expresión de GLP-1. Entonces podría ser por ahí. Pero eso fue hecho durante pandemia. Y nosotros teníamos muestras séricas y nos perdimos. Así que no pudimos hacer GLP-1. Pensamos que es y ahora tenemos que replicar el estudio. Sí, en contexto de obesidad. Igual nosotros replicamos ese estudio en una formulación de alimento funcional para personas obesas, ¿ya? Con un proyecto Lánzate de Paula Acevedo y Viviana Valero, ¿ya? Y nosotros vimos resultados muy parecidos también.
Gracias. Y también otra consulta. ¿Es posible que también la fibra, porque al comer junto con los arándanos también haya afectado, ¿no es cierto?
Sí.
No solo los polifenoles.
Sí, no, es todo el alimento. Sí. Nosotros hablamos que en realidad es súper difícil sacar los polifenoles de la fibra porque ellos van juntos, ¿ya? Pero ¿cuál es la gracia de los polifenoles? Van a aumentar la actividad antioxidante por su molécula, que hay muchos hidroxilos en su estructura. ¿Ya? Y además van a tener más sustrato para ser metabolizado por la microbiota intestinal. No es solamente la fibra, sino que ellos también.
Vale, muchas gracias.
¿Una otra pregunta? Sí.
Hola. Consulta, no sé si lo mencionó, solo me lo perdí. ¿O no? El tema es que había una alteración en AMP cíclico en algunos de los efectos que eran mencionados. ¿Cuáles serían las implicancias eventuales de esa alteración en AMP cíclico y a lo mejor en qué tejidos?
Bueno, nosotros no cuantificamos AMP cíclico propiamente tal, ¿ya? Pero creemos que podría mejorar todo lo que es el tema de la beta-oxidación a nivel hepático.
Gracias por la presentación, de verdad, súper bonito, muy interesante. En uno de los trabajos que tú mostraste, dijiste que la frutilla blanca cambiaba la glucosa basal, pero no había cambio en el peso corporal de los animales. Lo encuentro súper interesante. O sea, ¿Cómo crees tú que actúa entonces la frutilla? ¿Y por qué crees tú que no hay cambio en el peso? ¿Qué pasa ahí? O sea,
no vimos cambio en el peso. Lo que nosotros pensamos es que el consumo agudo de polifenol, junto con una fuente de hidrato de carbono, ¿ya? Podría disminuir la actividad de la enzima propiamente tal, la enzima digestiva que nosotros tenemos, ¿ya? Y eso reduce la absorción efectiva de macronutrientes, que es lo que va a aportar la energía, ¿ya? Pero en nuestro modelo lo que pasa es que una dieta alta en grasa por 12 semanas es mucho. Y es harto. Entonces, igual para recuperar esos animales, el periodo de intervención tiene que ser mucho mayor. Y de hecho, nosotros seguimos con esos animales entregando la dieta alta en grasa. Entonces, para ver algún tipo de cambio, tiene que ser algo prolongado, ¿ya? Para mejoras metabólicas, yo diría consumir hidrato de carbono, una fuente con un polifenol, algo agudo, ¿ya? Pero para que sea algo de peso corporal es crónico. Nosotros no vamos ver, ¿cierto?, de un único consumo. Entonces, por eso es importante el consumo periódico y frecuente y ojalá junto con comidas.
¿Tiene evaluado la actividad como a nivel cardiovascular estos
No,
animalitos?
no, debería. Ahí podemos cooperar.
¿Alguna otra pregunta para la doctora? Muchas gracias entonces por la presentación. Que entonces tenemos ahora la última presentación antes del café. Entonces vamos a dar paso entonces al doctor Carlos Escudero Orozco. Él es profesor en la Universidad del Biobío. Él es además el director del Laboratorio de Fisiología Vascular de dicha universidad y nos presentará hoy evidencias preclínicas de alteraciones cerebrovasculares en madre e hijos con preeclampsia. So now, let me introduce you Dr. Carlos Escudero. He is from the University of Biobío, that is in the south of Chile, and he is going to present us placenta brain communication in women and offspring exposed to preeclampsia. Thank you very much for being with us today.
So, thank you very much, Tamara, for this invitation to be part of this symposium. Congratulations for organizing this meeting. So I'm going to talk about this concept of placenta-brain communication in a setting of preeclampsia. So this lecture has two parts. So one part is regarding the placenta-brain communication at the maternal side, and the other part is about the placenta-brain communication by the fetal side. So I'm going to, I have to make a disclaimer because you are not going to see so much data, but instead you are going to see much graph and cartoons in order to challenge you and, engage the conversation about these concepts. So at the beginning, I want to tell thank you to all of these people in the lab. So especially Yesenia, Felipe, Hermes, Stephanie, and Belen, who has been working in this project, both at the maternal side and also at the fetal side, and also the national and international collaboration that has been, very well supporting for us in order to move this kind of investigation forward. So I'm going to talk about preeclampsia. So for people who are not aware about preeclampsia, so this is a pregnancy condition characterized by high blood pressure, and different organ damage. So this alteration occurs after 20 weeks of pregnancy, and this is the leading causes of maternal morbidity and mortality, especially in lower and middle income countries. So basically, so you can see here, this is an old data, but hasn't changed too much, saying that preeclampsia is one of the leading causes, or hypertension during pregnancy is one of the leading causes of maternal mortality. So one of the things that I want to emphasize here at this very first slide is that most of the maternal morbidity associated with this condition, hypertension in pregnancy, is actually related with brain complications.
So when we talk about brain complications, so we are talking about this series of different entities. The presentation doesn't help me to emphasize all of these entities, but you can see that there is many entities that affect the brain. So basically, one of these, for instance, so one of these is a eclamptic fit. So basically, woman has a complication that ended in an eclamptic fit. Or even other women actually present stroke, for instance. So this is, as I mentioned, the leading causes of maternal mortality. Depending on the statistics, so about 40 to 70% of women who died due to preeclampsia is because this alteration in the brain. So, but not only that, but a woman who survived preeclampsia actually have higher risk also to develop a brain complication later in life. So, for instance, women who survive preeclampsia has 3-4 higher risk to develop dementia. So, there is another part of this slide here is included several other entities that has been associated with preeclampsia in the long term. So the conclusion of this imaging is that complication in the brain in women who experience preeclampsia are deadly at the acute phase, but also at the woman who survive preeclampsia has an increased risk to develop these conditions. So the sad part about this is that we don't know exactly what are the underlying mechanisms associated with these complications. So basically, so we need to do more about, basic science in order to better understand what happened behind these mechanisms. So, but one of the commonalities between short-term complication and long-term complications is actually the damage of the brain blood vessels. So in my laboratory, we are working in blood vessels, basically, and we know that the brain and the blood vessels are highly specialized. So let me introduce a little bit more one of the specialties that has these blood vessels. So I'm sure that you have heard about the blood-brain barrier. So this is a barrier that protects the brain against any potential damaging elements. So this is a structure, a very complex structure associated with different cell layers and different chemicals and protein characteristics. But one of the first line of protective layer of this blood-brain barrier is the endothelial cells. So here you have 4 characteristics of these endothelial cells that allow them to function as a barrier. So let me just review a little bit about these characteristics. So one is the expression of high expression of a family of proteins that form a glue between these 2 different cells. So this is called tight junction proteins. So basically, there is a family of tight junction proteins, and we are going to talk about a little bit more about one of them that is called Claudin 5. So another characteristic is that they have 1,000 of different proteins expression that allow them to limit the interchange between the bloodstream and the brain parenchyma. So also they have low transvesicular transport. That means that high molecular weight structures doesn't cross normally the endothelial cells. And finally, they doesn't express adhesion molecules that block or limits the interaction between leukocytes and endothelial cells. So as you can imagine, and study all of these mechanisms in human is quite difficult. So that means that we need more, that we need models in order to understand what happened in this barrier. So as I mentioned, I'm going to talk about Claudin 5, which is a tight junction protein. So one of the interesting things about Claudin 5 is the fact that endothelial cells express 600 times levels of this Claudin 5 compared with the another endothelial cells in the rest of the body. So that means that they actually is highly expressed. And the second idea that I want to mention about Claudin 5 is that if you knock down the expression of Claudin 5, the animal actually die because of the impairment of the function of the blood-brain barrier. So this is just to highlight how important is Claudin 5 in the barrier. And we are interested in which factors are involved in this alteration of the blood-brain barrier. So this is the model that we set up in the lab. So this is a basic model in which we have two compartments, the upper compartment and the lower compartment, and they are divided for monolayer cells in which we are using, so this is the novelty of the model, because we are using human microvascular endothelial cells. So this is an endothelial cells that actually came from a woman who actually has a seizure. So basically, in terms of the model, that means that we have perhaps the most perfect model in order to mimic what happened in the blood-brain barrier in women. So when the monolayer is healthy, so we have a higher resistance between these two, higher electrical resistance between these two compartments. So basically, we can measure the electrical resistance, and any drop in the electrical resistance means that the monolayer is unhealthy or is disrupted. And also, we put it in the upper compartment, we put it a high molecular weight fluorescent dye, so that normally doesn't cross this monolayer, but when the monolayer is impaired, we can detect this fluorescent dye in the lower compartment. So basically, during the presentation, you are going to see these two parameters, the electrical resistance, a drop in the electrical resistance, and also an enhancement of the permeability. So what we did at the beginning was to use plasma from women who had preeclampsia, and we put it, this plasma in this model. So you can see the plasma from women with preeclampsia reduce the electrical resistance and enhance the permeability. So that means that basically something in the plasma has the potential to impair, the blood-brain barrier, at least in vitro. So this similar experiment has been shown before in using different models, using a combination between plasma from women with preeclampsia and rat brain blood vessels. So basically, this study confirmed the idea that something in the plasma is capable to impair the barrier. So, but the Grial sign, or what's the name? Well, and the key question in our field is what exactly is in the plasma that are capable to disrupt this barrier. So one of the things that we have in study is the connection between the placenta and this alteration in the blood-brain barrier. So let me just introduce a little bit one of the concepts that was introduced in the morning about extracellular vesicles. So this here is the placenta. So the placenta is connected with the maternal uterus, and the placenta is continually releasing factors to the maternal circulation. So among these factors, we know that it's releasing extracellular vesicles. So these extracellular vesicles are tiny cell fragments. You see here, we are interested in the small extracellular vesicles, and these vesicles has, within the cargo, has nucleic acids and also proteins that allow them to function as communicating molecules between those two distant organs. In this case, the placenta and the blood-brain barrier. So one of the ideas is that the placenta, extracellular vesicles, is releasing this cargo to the circulation, and once it's released into the cargo and reach the recipient cells, they can actually release the content and modify the function of the recipient cell. So in our case, there was no information in the literature saying that the extracellular vesicles coming from the placenta actually had the capacity to reach the blood-brain barrier. So in order to answer that question, we needed a model. So basically, what we did at the beginning was to take a placenta, a human placenta, culture the placenta in two conditions, one normoxia and one hypoxia, and using this conditional media, we isolate extracellular vesicles. So the techniques about how we isolate, we can discuss during the Q&A session. But basically, we isolate extracellular vesicles, small extracellular vesicles from this conditional media, and we put that in our in vitro system. So you see here now extracellular vesicles coming from from placenta culturing hypoxia, decrease the electrical resistance and enhance the permeability. So basically, this was a proof of concept that the placental extracellular vesicles are able to disrupt the blood-brain barrier. But of course, we needed to prove this in vivo. So basically, what we did is injected the extracellular vesicles in pregnant mice, female mice, and we leave the extracellular vesicles circulate for 24 hours in the mice system, and then we injected to the mice one molecule called Evans blue. So Evans blue reacts with the albumin. So albumin is a macromolecule that doesn't cross the blood-brain barrier, but when the blood-brain barrier is impaired, can be found in the brain parenchyma. So basically, what you see here is the mice brain that received extracellular vesicle from hypoxia. You see here there are more blue staining in the brain compared with the controls that received extracellular vesicles from normoxia. So that means that basically the extracellular vesicles are capable to impair in vivo, in this case, the blood-brain barrier. So this paper was published in 2021. So then what has been done so far in order to understand the mechanism? So basically, we now know that the placenta is capable to release the extracellular vesicles and reach the blood-brain barrier. I didn't present any data, but the paper is also indicated that we can block this impairment in the blood-brain barrier using magnesium sulfate, that is the drug of election in order to prevent seizures in women who had preeclampsia. So as I was saying, after this paper, so this is just recently accepted in this journal, this evidence that we published. So we repeated again our experimental setting in which we injected placental extracellular vesicles derived from this hypoxic condition in our mice model, and we now follow the expression, or follow the extracellular vesicles within the animal system. And our idea was to identify whether these placental material are capable to reach actually the blood-brain barrier. And why was important that question is because we are injected human material in our animal system. So basically what would be possible to happen is that the extracellular vesicles can enhance the inflammation in the animal. So basically the inflammatory system can actually impair the blood-brain barrier and not directly the extracellular vesicles. So this is the reason why we decided to analyze and follow the vesicles inside the animal. So what we did in this experiment that was done by Hermes, so we identified the extracellular vesicles in the brain, and we are able to identify the extracellular vesicles within the brain endothelial cells. But not only that what happened in endothelial cells, in the brain endothelial cells, the expression of Claudin 5 was decreased. So that means that the cells are, separated and allow them to enter any material that are in the circulation. So basically, what happened is that the extracellular vesicles were capable to cross the blood-brain barrier and found into the brain parenchyma. And what happened in the animal was we detected brain edema and also cognitive decline. So if you are interested, this paper was elected as a editor choice in the ATBB journal. So it's free. You can download. So please download and comment. This is one of the information that we have in that paper. So in green, you see the extracellular vesicles that was preloaded with a fluorescent dye and was injected into this mice system. So I don't know if you can see some of the green staining here inside the blood vessel, and this blood vessel, this is a brain blood vessel, and is in red because they express Claudin 5. So basically, is the expression of Claudin 5 here. So you can see some of the green is inside the vessel, but some of the green staining is outside of the brain blood vessel. And you can see here, actually, if you see the expression of Claudin 5 seems to be decreased in this particular area, and there is accumulation of the material, let's say the extracellular vesicles. So another conclusion that is important to this experiment is that these extracellular vesicles seems not randomly, located. Seems to be that they are accumulated in some kind of cells that we don't know exactly which cells are, but seems to me that they are kind of astrocytes, or they kind of even neurons could be one of the targets. So this is one of the things that we are now trying to address in the lab. So this is animal studies. So what happened in human? So one of the things that we haven't done in a collaboration with Manu Mati's group in Oxford, so they use this technology in which they have a system to identify placental extracellular vesicles in lower concentration and also in a very specific manner. So that means that this system has the capacity to identify with high effectiveness the level of placental-derived extracellular vesicles in any single fluid. So because we are interested in the blood-brain barrier, so we were capable to extract some cerebrospinal fluid from women who had normal pregnancy, preeclampsia, and also from non-pregnant women. So I'm using this technique in which we have the capacity to identify lower quantity of placental-derived extracellular vesicles. So we asked whether we were able to identify this extracellular vesicle in women who had preeclampsia in the CSF. So basically, what happened here is that this is the limit of detection of the system. So this is no pregnant CSF, and this is the pregnant CSF. As you can see, there is no any signal, detectable signal in our system in which we can see if the CSF has these placental-derived extracellular vesicles. So, but this is normal pregnancy. So what happened in preeclampsia, so our hypothesis was that if the extracellular vesicles from the placenta are through into the system, perhaps we can detect in the CSF. But this is the conclusion of our last study. So basically, none of them, no preeclampsia, no eclampsia, or even if we divide it in early onset preeclampsia, I should mention that early onset preeclampsia is the most severe entity in preeclampsia, but none of them were capable to identify the expression of these placental-derived extracellular vesicles. So connecting these two ideas, so what we think is happening is that the extracellular vesicles are capable to cross the blood-brain barrier, but be stuck in any kind of cells within the brain. So this is just actually a hypothesis. So the question that we are want to answer in this grant is mechanistically how extracellular vesicles are capable to disrupt the blood-brain barrier, how they can decrease the level of Claudin 5, and we are interested in different entities that nowadays are part of some of the projects that we are running in the lab. But also, what would be the consequences for this model to have placental material inside the brain? So this is one of the questions that we want to answer. What would be the underlying mechanism of this alteration that we saw? And what would be the consequences for a woman who had preeclampsia? And one of the things that actually is interesting, I didn't present it to you, but this permeability of the placental extracellular vesicles are also detectable in normal pregnancy. So we think that perhaps this mechanism is actually a physiological one that has the potential to generate this adaptation that occur in the brain, in the maternal brain during pregnancy. So this is just hypothesis, but we are trying to answer that question. Okay, so Gursofat, so the idea is that now we are talking about placenta-brain communication at the maternal side. So, but the idea is that if the placenta is releasing factors to the maternal side, so basically it's easy to guess that perhaps some material actually is releasing now to the fetuses, and then if it's capable to reach the maternal brain, why not to have the potential to reach the fetal brain? So this is the question that we want to answer, and there is a kind of frame, epidemiological frame for that question, because children who has been born from women who had preeclampsia have higher risk to have neurocognitive development alterations. So basically, that is an epidemiological observation, but nobody knows exactly the underlying mechanism. So with that in mind, so there is some information in the literature that indicate that this paper was published in 2016, in which they included 10 children for women who were born from women who had preeclampsia, 5 boys and 5 girls, and compared them with normal pregnancy ones. And they found different alteration in the brains, in the connection, in the volumes. But one of the things that was important to us was the idea that the blood flow in the parietal lobe and the occipital lobe was decreased in children who had been born from women who had preeclampsia. So we tried to replicate that, and we used our animal model. In this was a paper published years ago. But the idea that we induce a preeclamptic-like syndrome in mice, and we analyzed the brain circulation in the fetuses. I mean, in the offspring, not necessarily the fetuses, because we used neonatal pups. So you can see here, this is the brain perfusion. This is the basal brain perfusion. You can see the red staining is indicator of how well is the brain is the perfusion in this tissue. So you see there is a reduction in the perfusion in the animals coming from the preeclamptic model. So from the vascular point of view, if you have a reduction in the blood perfusion, that could mean many things, like, for instance, a vasoconstriction of the blood vessels, or if the blood vessel doesn't exceed at all, I mean, there is a reduction in the formation of the blood vessels, or even there is an impairment in the blood-brain barrier that allows brain edema that make a congestion of the brain parenchyma. So we decided to investigate what happened with the formation of the brain blood vessels in our system. So this is the paper that we published in this year. So this is the brain cortex in the control mice. So you can see here the brain blood vessels nicely. This is a network of the blood vessels in the brain cortex in the controls. But here is the animal coming from a preeclamptic light syndrome. So we used 3 different models of preeclampsia. This is one of them. We also used the alteration, the reduction of the blood perfusion in the placenta, and also a genetic model. All of the 3 models basically showing the same. So a reduction in the number of blood vessels in the brain cortex. So I don't have time to explain all of the details about this paper, but basically what happened is that in our system we saw that there is a reduction in the vascular endothelial growth factor, which is a main regulator of angiogenesis in any tissue. So we found that there is a reduction in VEGF, a reduction in the activation of the receptor that is associated with angiogenesis, that's called KDR. And this alteration is associated with an alteration in the F-actin polymerization that leads to impairment in the capacity of cell migration. And because cell migration is highly important in the brain angiogenesis, because as you can imagine, we don't have space to proliferate any single cells. So basically the angiogenesis process occurs due to cell migration. So there is a reduction in the cell migration capacity, and that impairment in the cell migration leads to reduced angiogenesis. So this is the human studies. So if the angiogenesis was reduced, so we have the capacity to include children who had been died because of different conditions, and we separate them in those who died because of preeclampsia and those who died due to other conditions. So basically, you have here the baby's brains in which you have more alteration in the blood vessels inside the parenchyma, but there is less impairment of this blood vessel alteration in the babies who died actually because of preeclampsia. So I know that I'm running now. So this is the question that we are trying to deal in the lab. What is the sex-dependent alteration in this brain angiogenesis process, and whether this is brain sex-dependent alteration in the brain perfusion or in the BBB alterations? So mechanistically, how the placenta is actually capable to decrease the angiogenesis and the blood function of the brain in the babies, and also what, again, would be the long-term consequences of this alteration in the angiogenesis in the brain. So let me just finish with this slide, because we haven't heard about the communication between organs. So the placenta has higher content of blood vessels. And the blood vessels in the placenta is directly connected with the circulatory system in the baby. So basically, if the endothelial cells that are, covering the inside of blood vessels are releasing factors to the fetal circulation, those factors actually may have the potential to decrease the angiogenesis in the brain. So with that in mind, we used Hubeck conditional media from normal pregnancy and from preeclampsia, and we used this conditional media to put into the brain endothelial cells. And what happened is that you see here, so the formation of these philopodia that are able for the cells to migrate was reduced in the cells that were exposed to conditional media coming from the preeclamptic endothelium. So at the end, I hope to convince you that there is a placenta-brain communication to the maternal side, But also this placenta-brain communication may also impair the function of the brain blood vessels in the baby. So thank you very much.
Thank you very much for your great presentation. Now I would like to open for questions. Absolutely, Sandra, please. I knew.
That's excellent work. Really enjoy the work you're doing. Going back to the extracellular vesicles, we had a normoxia and hypoxia, and you put it into mice. Have you done that where you've taken normoxia and preeclampsia EVs and put it back into mice to look at your Evans blue, for instance?
Yeah, we haven't done that in the mice, but we haven't done that in the in vitro system. So we collected extracellular vesicles from the plasma from women who had preeclampsia, and we put it in our in vitro system, and we saw the same. So basically, an impairment in the blood-brain barrier parameters that I mentioned. But it's interesting. I take advantage of your question because the extracellular vesicles that are circulating are coming from different sources, not only from the placenta. So one of the questions that we want to address in this kind of experiments is the placenta-brain axis. So this is why I presented just the data.
Yeah, I'm going to ask a question because I don't know.
Yep.
What's the turnover rate of endothelial cells, and are they polarized? And finally, the pseudopodia that you show are much like the neurites and how they grow. It's dependent on actin polymerization, which is calcium mediated.
Okay, so let me just understood what was the question. Was the
All dependent on migration.
Yeah. So first of all, about the specialization of the endothelial cells and the turnover of endothelial cells. So this is one of the open questions in the literature, especially in the blood-brain barrier, because we don't know how long this endothelial cell stay in the as a barrier, and we don't know how they actually recover after one damage. So this is short answer. We don't know exactly what is the turnover of the endothelial cells. Of course, we know in other endothelial cells, but especially in the blood-brain barrier, we don't know. And the second part was about the polymerization and the polymerization and the formation of these philopodia. So what we have found so far is that there is a alteration in the polymerization. This is a gross alteration because we have the capacity to measure F-actin, as a whole, and also we measure the enzymes that are involved in the polymerization and depolymerization, like a coffulin or the complex R2 and 3. And what we found is that the complex are decreasing the protein level of this complex R2 and 3 and the coffulin, and there is an association with some changes in the F-actin, parameters, let's say the length of the width of the F-actin. But we don't know, because our laboratory is not specialized in molecular biology itself, but we know that there is gross changes in the F-actin.
We use a saying called LifeAct.
Yeah.
To look at the actual polymerization of F-actin.
Okay, very nice.
And you could do that in real time, I think.
That would be great. There is something that we are learning right now.
Thank you. ¿Questions? ¿No? ¿Preguntas al doctor Escudero? ¿No? Bueno, él también nos va a acompañar mañana, así que ahí van empezando algunas preguntas, porque también va a estar y le podemos preguntar también.
Okay.
Muchas gracias.
Thank you very much. Muchas gracias.
Now it's a break time, then, español. Ahora podemos ir al café y volvemos para las últimas dos exposiciones, ¿sí? Vuelvan. Ok, entonces ya estamos en la última parte del día de hoy, nuestro simposio. Estamos llegando a las últimas 2 presentaciones, pero no por eso menos importante. Estamos expectantes a estas 2 presentaciones y la primera de ellas es por el doctor Bernardo Krause Leighton. Él es profesor de del Instituto de Ciencias de la Salud de la Universidad de O'Higgins, así que nos acompaña desde la 6ª región. Nos presentará hoy intervenciones basadas en la epigenética contra la disfunción vascular fetal resultante de la hipoxia crónica. So let me introduce you, Dr. Bernardo Krause. He's from the Universidad de O'Higgins, from the Health Science Institute. And he will be presenting to you epigenetic-based interventions against fetal vascular dysfunction resulting from chronic hypoxia. Thank you, Bernardo, for being with us today.
So thank you to Tamara and Dr. Diaz for inviting me to this meeting, which is a very nice and comprehensive meeting about health sciences. And also, I'm very glad to be representing my university because it's one of the youngest public universities in Chile, but also we have here one of the main public university of Chile, as is Valparaíso University. So I will talk about the origins of vascular dysfunction due to chronic fetal hypoxia. And as you heard before from a presentation by Dr. Escudero and David in the morning, early stages of development are very important for later health. And in this area, also one of the main stimuli that is related with an altered vascular function in the long term and also altered cardiometabolic function is being exposed to hypoxia during fetal development. And just I give that address because I will go immediately to other part of a presentation that used to be avoided or are passed very fast. So I would like to share with you what had been a research question. And considering my area, this is the programming of vascular function since fetal growth, we wonder whether many years ago, what was the best or suitable experimental model to address endothelial programming resulting from impaired fetal growth condition in humans. And in this regard, we were focused on to select the in vitro, ex vivo, and in vivo experimental model for that. Also, we have a work on what are the epigenetic mechanisms that contribute to changes in endothelial function associated with this altered fetal development. And finally, would be the last part of my talk about is there any contribution of epigenetic mechanism? Could this mechanism used as therapeutic tools against the changes that are originated during early development and impact vascular function in the long term? So concerning the models, we discussed a little bit in the morning about which endothelial cell could be suitable for address, for instance, arterial dysfunction. And we and others have demonstrated that umbilical artery endothelial cells has an arterial phenotype because not all the vessels are equally in function, but also at molecular levels. And in this regard, arterial identity is early fixed during development and remains almost stable until death. And so we provide a comprehensive evidence concerning that umbilical artery endothelial cells has a differential expression of very important signaling pathways like HIF signaling pathways, the pathway that responds to hypoxia, fluid shear stress, and other pathways compared with HUVEC, which are commonly used for addressing endothelial function. But also, by using an animal model, we have able to compare how impaired fetal growth in black, in this case, induce a change in some important genes like enos, and these changes is comparable when we look at the aorta endothelial cells, femoral artery endothelial cell, and umbilical artery endothelial cells, showing that addressing question in the umbilical artery endothelial cell is addressing, in some extent, question in the arterial vascular bed of the fetus. Also about a good model for addressing early impact of altered fetal development is the guinea pigs. The guinea pigs share a lot of characteristics with human gestation in terms of placental, insulin, cardiac maturation, brain maturation, structural and biochemical maturation in lungs, also glucocorticoids and dependency during maturation. And we have also been able to produce a model of fetal growth restriction in guinea pigs that allow us to follow up the growth by Doppler measurement and ultrasound measurement that result in a comparable features that are observed in human pregnancy. Finally, also we have been interested in to isolate the effects of maternal physiology on the fetal development by using the chicken embryo model, because in this case we can isolate from the placenta and the fetus and address, for instance, the direct effect of hypoxia on fetal development, but also because chicken has a comparable cardiac and cardiovascular time frame of maturation during or previous to birth in comparison with other rodents. And finally, just to make a brief comment about what are some of the genetic mechanisms that are currently focused. We are working now in microRNAs. MicroRNAs interference, small RNAs produced are encoded in our genome, and they are able to modulate the expression of several genes, and also they have been implicated in several cardiovascular processes like regulation of cardiac remodeling, inflammation, and response to pathological and vascular stimuli, can be used as biomarkers, can be used as target for drugs, and is of special interest for us has been microRNA 21-5P, because we have studied at transcriptional level being implicated in the difference between white and cubic, the umbilical arteries and umbilical veins, endothelial cells, also in the response to hypoxia and fetal growth restriction in both cell types. So the second question that we will address now is, are the epigenetic mechanisms contributing? And I will give just a brief review of about our results, but we are not the only group that have shown this. So indeed, we are a small part of a big picture. But as I previously showed, well, fetal growth restriction here in black is associated with a reduced activation of endothelial nitric oxide synthase, the enzyme involved in vascular relaxation. And surprisingly, this decreased activation is accompanied by increased expression of the protein and of the RNA encoding for this protein. And this result comes from cell exposed to culture conditions. So this cell has been isolated from human umbilical cords at birth and maintained at least for 2 or 3 weeks, and they still have a differential expression and activation of this. That suggests that these cells are programmed in the sense that they can control at long term the expression of enos in a different way relative to control endothelial cells. And to test this hypothesis, we treat these cells, these FGR cells, with an silencer of the DMT1, a protein involved in copying the methylation pattern after each replication. So the idea behind this experiment was to try to erase in artificial conditions the epigenetic pattern imposed by pregnancies affected by fetal growth restriction. And as you can see here, here is the expression of the FGR in control conditions. Here is the expression with a scramble silencer RNA, and here is in the presence of the silencers of DMT1. So when we block or reduce the activity of DMT1, we are able to recover the expression of enos. And I will not show the data, but this is more specific for some genes. Not all the genes respond in the same way, but it was very interesting to see that was occurring for enos. And indeed, also, we have able to determine that this increased expression of enos is accompanied by, especially with a reduction on the DNA methylation level in the core promoter, and a site which is related with SMP3 binding, which control the basal expression of enos, but also with an increased levels of histone modifications that leads to an increased open accessibility of the chromatin in some site that responds to shear stress. As I mentioned before, we also demonstrated previously in guinea pigs, in this case, that the fetal growth restriction in black induced an increased expression of enos transcript either in the aorta, femoral, or umbilical arteries. And when we treat those dams during gestation with an antioxidant, we are able to prevent that increase in enos expression in both genes. And in this case, you may see that black bar highlighted there in the promoter region of gene encoding for enos, in this case in the guinea pigs. And you will see that in all the hypoxic one, there was a decreased levels of DNA methylation in that site, which, as we saw in the case of human, is also comparable. I mean, an increased expression of the messenger RNA and a decreased level of DNA methylation. And as we hope, or we're waiting for, the methylation levels in those animals treated with N-acetylcysteine, the antioxidant, was preventing the decrease in DNA methylation and also, as we say, the effect on RNA expression. So we could, as well, that's occurring because fetal growth restriction occurring by the mother can do that, but we address the same question in the chicken embryo, and in this case, we directly expose the embryos to hypoxia and directly treat the embryos with N-acetylcysteine. And we again, in this case, in the chicken aorta, we observe an increase in the expression of enos in this model, and a reversion of that increase when we treat the embryos with an acetylcysteine. And similarly, we saw before, the DNA methylation was decreased in the promoter of hypoxic animal expressing more enos, and this effect was partially reversed by an acetyl treatment. And here you will find that, again, we have been able to describe the structure and binding site of different species NOS3 gene promoter, in this case for the chicken embryo. And again, we find that in those sites that are in the proximal position to the transcription start site, we have a down regulation of DNA methylation. So finally, we want to know if these epigenetic mechanisms could be used to address this cardiovascular dysfunction. And we look at many microRNAs, but I will just show one of those that showed some significance since the beginning of our results, and that was microRNA 21-5P. In contrast to many microRNAs, microRNA 21-5P has its own promoter. Indeed, it's encoded between in the exons of another genes called TMM49. And interestingly, the methylation pattern of the microRNA 21 promoter is characterized by low levels or low numbers of CPGs. So we found that in the fetal reconstruction, in this case, again in human placenta, there's a substantial reduction in microRNA 21-5P expression, and it was accompanied by increased levels of DNA methylation in this promoter. Interestingly, when we expose control cells to hypoxia, to the different types of hypoxia, we observe that microRNA 21 is downregulated in response to hypoxia. And we previously described this response, but we confirm again that when we expose these cells to hypoxia, enos expression is upregulated. And we look at other microRNA that have been previously described as very important in regulating endothelial function, and we did not observe any response to the decreased levels, decreased oxygen levels. But also we use a gene that has been previously described as being controlled by microRNA 21. Which is DDH1, which also contribute to enos synthesis. And we observe, similar to enos, that an increase in DDH1 at different time of hypoxia. So if we plot these responses, we will observe that DDH1 and enos, in blue, follow an upregulation in response to hypoxia. Meanwhile, microRNA 5P follow downregulation. So we speculate that maybe there is a functional relationship between those genes. And indeed, we treat some cells exposed to 6 hours of hypoxia with microRNA 21-5P, and we maintain it with this treatment. We maintained the levels of microRNA 5P, and by maintaining this level of microRNA 21, we observed that there was a downregulation of enos and DDH1. And this downregulation was due to a decreased transcript stability for both genes. And indeed, when we treat the cells with microRNA 21, we observe a complete downregulation in basal condition and a complete abolishment of the enos-induced expression by hypoxia, and also at the level of DDH1, demonstrated that microRNA 21-5P targets enos transcript. So this was just in one cell type, so we want to know if we can use microRNA 21, which is downregulated by fetal hypoxia, to treat cardiac dysfunction. In this case, we start with an in vitro model using neonatal rat cardiomyocyte. As you may remember from my slide about organ maturation, the mouse and rat heart maturate after birth. So when we took these cells, we are just getting immature cardiac cells, and so it will be similar to have mid-gestation cardiac cells. So we took these cells and exposed them to either hypoxia or normoxia in a basal condition or stimulated with microRNA 21-5P. And in this cell, we studied the cell viability and performed long-read nanopore sequencing to make a transcriptional profiling. And it's not very evident here, but maybe here you will see that when we perform the tunnel staining, cells in hypoxia has more positive nuclei compared with the other three conditions, especially when hypoxia treated with microRNA 5P. And this is the merge, showing that there we have nucleus, but most positive nucleus was in the hypoxic group, as is summarized in this plot. So then, deriving the data from the RNA-seq, we observed here a plot the top 100 differentially expressed genes, either downregulated or upregulated. And you can see in blue those that are downregulated. And here you have in the first column, you have the hypoxic group. And when we compare the second column, which is the hypoxic group treated with microRNA 21, you will see that most of the, for instance, the upregulation were counterbalanced or counteracted by the microRNA 5P. Indeed, in some cases, we have downregulation, or in this case, when some genes were downregulated by the hypoxia, we have upregulation by the presence of microRNA 21. And if you look here, you will see that there's so many. What are the main KEK pathways? I mean, the main pathways that are enriched by hypoxia, and you will see that some of them are related with fluid shear stress, with adrenergic signaling, and hypertrophy or ferroptosis, and arrhythmogenic signaling. And all those enriched pathways by hypoxia were absent when we look at those cells treated with microRNA 21. Similarly, when we look at those different other pathways that had representation in different cells, in different genes that were differentially expressed. But looking closer to the target of microRNA 21, here are all the targets that we found in our libraries. And you may see that in this case, in the upper row, you will see that it's a hypoxia cells and the hypoxic cells treated with microRNA 21. And again, we observed that the counteractive effects of microRNA 21 was also operating at a specific level regarding regarding its target. So its target were regulated indeed by microRNA 21. And also when we look at the pathway and the genes that were differentially expressed but was targeted by microRNA 21, we again see that there's those related with cardiac dysfunction were differentially regulated. Moreover, despite that the number of genes targeted by microRNA 21 are small compared with the total number of genes differentially expressed, all those genes are surrounded by a red cycle. All those genes have a functional relationship with many other genes that were differentially expressed. So independently if all the genes were regulated by microRNA 21, those has a functional significance. But all this data is just in vitro. So the question is, if we use microRNA 21 5P in vivo, has any effect? So again, we use the chicken embryo model. This is a representation about the protocol. So we have 4 groups, 2 groups of normoxia and 2 groups of hypoxia. And part of the hypoxia-normoxia group received a treatment with 1 microgram of microRNA 21 every 48 hours since day 13 to day 15. That means from the mid of pregnancy and so on in comparable time with humans and mammals. And by the end of this day 19, we extract samples and assess cardiac function ex vivo by a Langendorf perfusion. So here are the effects of hypoxia, as we observed in our previous study with N-acetylcysteine. Hypoxia reduced the body weight of these embryos, and the treatment with the agomir, I mean the synthetic microRNA, reversed partially this effect. And also markers of altered fetal growth, which is like the brain weight to body weight ratio, that is increased in the hypoxic group, but this effect is reverted by the treatment with the microRNA. And when we look at the cardiac function, we may observe that the hypoxic group has an increase in left ventricle end diastolic pressure, an effect that is prevented by the treatment with the microRNA. Similarly, in the mean relaxation time, also we observe a decreased response to carbachol in the hypoxic group, which is recovered by the treatment with the synthetic microRNA. And also has been previously demonstrated, and we confirm here, that the exposure to chronic fetal hypoxia induces an increase in the sympathetic dominance in terms of high rate, and that effect is reverted by the treatment with the synthetic RNA. So in conclusion, we may say that ENOS expression is tightly regulated by epigenetic mechanism at level of pre- and post-transcriptional level, and microRNA are potential candidates for treating the cardiovascular effect of fetal hypoxia. So my acknowledgement and thanks to my lab colleagues, my national collaborators, international, and the funding sources. So thank you very much.
Thank you very much for your presentation. It was great. So now it's open for questions. Preguntas para el Dr. Bernardo Kraus.
Todos tienen sueño.
Thank you. That was wonderful work. Really love it. I'm a little confused about the ENOS expression and the chicken and the egg, right? So when you have hypoxia and it decreases MIR21 and ENOS goes up, is ENOS good or bad? And now you want to use miRNA 21 to treat, but can you help me understand what the pathology is of ENOS expression in hypoxia, that it goes up? Is it being compensatory or is it a pathological?
That is, I mean, that question it's very good because I have to argue with my colleagues to about to do the experiment, because most of the people said that, well, more ENOS is better vascular health. But if you look at all the data related with chronic fetal hypoxia, you will find that at the end of gestation, you have increased ENOS expression. For instance, in the lungs, all the people that look at cardiovascular function in the lungs, in femoral arteries, and so on. This is one point. So maybe it's not that good. The other interesting part is that most of the treatment that has been used, for instance, melatonin, N-acetylcysteine, vitamin C, in all those models, you may find that ENOS expression is upregulated by hypoxia, but the treatment downregulates ENOS expression. But endothelial function is recovered. So my hypothesis is that increased ENOS expression in condition of chronic fetal hypoxia is mainly related with ENOS uncoupling. So maybe having more ENOS just will result in more in uncoupled ENOS rather than better relaxation. So for that reason, I was thinking on that. I mean, well, also there's many other studies from pioneer studies by Leslie Mayat in the 90s showing that placenta from preeclampsia has increased nitrosative stress. So, well, maybe it's not necessarily more nitric oxide. But also there could be an additional or alternative vasodilator mechanism. You know, ADGF, we have also published that hydrogen sulfide-dependent relaxation is enhanced when you treat embryos with N-acetylcysteine. So maybe to rescue the vascular function in chronic fetal condition, maybe are not ENOS-dependent and could be dependent on other stuff. But I would like to highlight that maybe that only occur in chronic hypoxia, because I don't know if it will happen in other conditions. We get restored oxygen delivery to the fetus. Maybe if we restore the oxygen delivery to the fetus, we could use nitric oxide again as a relaxing factor.
Thank you.
¿Alguna otra pregunta para la clase? Nada bien. Okay, so I do have some questions. Yeah, my question was also about like inos and coupling, but I was also wondering about inos in your model. So if I don't know, I think that sometimes inos also goes up in these conditions, and have you look at that or?
I haven't, but there's a couple of papers from Lorem Thompson group that worked with fetal hypoxia in guinea pigs, and they showed that there's oxidative stress including nitrotensive stress, and part of that was due to increased inos expression in the placenta and heart. So definitely could be part also involved in this case. I don't know if microRNA is targeting some inos related genes, maybe DDH1, because DDH1 is a gene that is a protein that degrades endogenous nitric oxide synthase inhibitor. So maybe it could be on that way. And also microRNA regulates, microRNA 21 regulates some inflammatory mediators. So probably may involve also inos.
Thank you very much. I had some questions about where did you get those eggs? But we can talk about that later. Because I was thinking
Yeah, but not in the supermarket.
For sure. Thank you very much, Dr. Carlson. Ok, nuestro siguiente y último y final expositor es el doctor Javier Palacios. Él es profesor de la carrera de Química y Farmacia de la Facultad de Ciencias de la Salud de la Universidad Arturo Prat del Estado de Chile. Entonces viene del norte, viene de lejos, nos acompaña, así que estamos felices, muy contentos de que pueda venir acá con nosotros. Y él le presentará efectos hipotensivos y antihipertensivos de extractos de biomoléculas bioactivas de plantas medicinales del norte de Chile. So now we are very glad to introduce you to Dr. Javier Palacios. He is a professor at the Department of Chemistry and Pharmacy in the Faculty of Health Science from the University of Arturo Prat del Estado de Chile, from very north in Chile. So it's a kind of far away from here. So we are happy that he is coming to our symposium. We are very happy to have the opportunity to listen to you one more time, Javier. So thank you very much.
Muchas gracias. Quería primero agradecer al simposio, a la organización, al doctor Rienzi Díez, como la profesora o doctora Tamara Sáez, por la presentación. En la primera diapositiva, que sería la del título, esa, justo. Sí, como me decían, vengo del norte y les voy a presentar un poco el trabajo que hemos hecho con un extractos del norte de plantas medicinales que se suelen usar como medicina tradicional. Déjame ver si veo. Gracias. Cuando uno trabaja con productos naturales, cuando trabajas con productos naturales, primero lo que hacemos nosotros es seleccionar las plantas en función de lo que dice la medicina tradicional, lo que usa la gente, las comunidades originarias. A partir de ahí comenzamos entonces a interesarnos en esa planta. La planta que les voy a mostrar se llama la chachacoma, que iremos presentando. Una vez que uno selecciona la planta, nos preocupamos de identificar sus metabolitos, aislarlos como metabolitos si somos capaces, e incluso hemos hecho semisíntesis química a partir de esos metabolitos. De la planta, como les decía, que voy a hablar, es una planta que la gente la usa en las comunidades del altiplano, en los Andes, como para el tratamiento del mal de altura. Ese es el origen de esta planta. La planta es un arbusto no muy grande, unos 50 centímetros de altura, y como se comercializa en los mercados es, como ven ahí, unas ramas. Se encuentra, como digo, en el norte de Chile, en las 3 primeras provincias o primeras regiones, y también se encuentra en toda Argentina, en la zona del norte, en Jujuy, Cajamarca, etcétera, San Juan. Es una planta que crece en altura, unos 3.600 metros de altura. Está sometida, como también decía la profesora Alejandra Espinosa, tenemos la gracia de, en Chile, ser sometida a condiciones extremas de radiación, de sequedad, siendo el desierto, el norte de Chile, el más árido del mundo, etcétera. Y en este caso, la recolección de esta planta, que el nombre científico es Senecio nutans, es cerca de San Pedro de Atacama, que es un típico. Este es el paisaje que se ve, un volcán, el volcán Licancabur, y aquí podrían imaginarse que de ahí se sacan esta planta, este arbusto. Como la medicina tradicional, como las personas lo utilizan, es normalmente como una infusión, como ven aquí, en la que con agua caliente, una cierta cantidad de la planta, 1 litro de agua, etcétera, se deja reposar y al final se termina haciendo una infusión. También se ha hecho, o lo hacen, mezclándola con etanol y en estas condiciones que indico ahí. Nosotros, en las técnicas que utilizamos, mezclamos la química, la extracción clásica de química, a partir del extracto, que es la molienda de toda la planta, no distinguimos entre partes aéreas, etcétera, toda la planta se muele, se coloca en una bolsa de algodón, en etanol, y ahí se deja unos 72 horas hasta que el líquido, que es el alcohol, termina oscureciéndose por la extracción que se va obteniendo. Después, con un rotavapor se liofiliza y se extrae todo el alcohol, con lo cual no va a quedar, si uno hace experimentos después en tejido, no va a quedar nada de alcohol presente. Y los metabolitos que se pueden extraer son muy numerosos. Aquí aparece, por ejemplo, un ejemplo de cromatograma, donde el número de metabolitos son unos 51 compuestos que tiene la planta, unos en mayor cantidad, otros en menos cantidad. Esto no llama la atención, las plantas suelen tener una cantidad enorme de productos. Y estas son las familias que tiene, en este caso, esta chachacoma o Senecio nutans, donde destaca las acetofenonas, que estas se obtienen fácilmente, se cristalizan fácilmente, están en un porcentaje muy grande de la planta. El rendimiento suele ser alrededor de un 19%, o sea, se tienen grandes cantidades, y son moléculas, como ven, relativamente simples, como derivados de acetofenona o benzofurano. Tiene otros compuestos que ahí se describen. Entonces, nosotros nos hemos centrado en estos metabolitos de la planta. Estos son los que hemos aislado. Voy a destacar el compuesto E y el compuesto G, que es el que voy a comentarles. El efecto que tiene el extracto hidroalcohólico de la planta chachacoma es un efecto hipotensor en un animal anestesiado al que le inyectamos en distintas concentraciones, miligramos por kilogramo, 5, 10, 20 y 40 miligramos por kilogramo de peso corporal, consigue disminuir la presión arterial. Entonces, eso nos interesó. Esto es un modelo de ratón, en este caso, anestesiado. No, perdón, esto es rata también, en el que vemos que a la concentración de 10 miligramos por kilogramo ya conseguimos disminuir la presión arterial media y, sin embargo, la frecuencia cardíaca se ve menos alterada. Hemos hecho experimentos de Langendorf, de corazón aislado, y los efectos que tiene la contractilidad es disminuir a la concentración de 100 microgramos por ml. Si hacemos experimentos de aurícula aislada, que lo hemos hecho también en rata, vemos que disminuye la frecuencia cardíaca al colocar el extracto, y aquí está el resumen de la información. Con 300 microgramos por ml hay una disminución de la frecuencia. Entonces, en resumen, hasta aquí tenemos que el extracto disminuye la frecuencia cardíaca, disminuye también la contractilidad cardíaca, y todo eso explicaría una disminución de la presión arterial que tuviera. Ahora, la pregunta sobre el corazón en cardiomiocitos aislados, ¿cuál podría ser el efecto del extracto? Entonces, también se han hecho estos experimentos, y estos son los resultados. En la longitud del sarcómero, esta es la condición basal, en negro, y en rojo aparece cuando se perfunde con el extracto que es senesio-nutans, una disminución de la longitud del sarcómero, que después de lavar, perfundir, se consigue recuperar la longitud del sarcómero, como se ve acá. Y esto iba asociado a los transientes de calcio, nuevamente el basal, y cuando tú lo perfundes con el extracto hay una disminución del calcio, de los transientes, que intentan luego del lavado recuperarse, pero no llegan a hacer la recuperación completa. También se hicieron con la herramienta de la cafeína. La cafeína serviría para estudiar el contenido total de calcio en el sarcómero, en el retículo sarcomérico, y los resultados fueron que pareciera que el extracto lo que está haciendo es impidiendo que sea recaptada el calcio por este retículo sarcoplásmico, con lo cual el calcio aumentaría en el citosol, favoreciendo a la activación del intercambiador sodio-calcio, que es el NSX. Y con eso conseguiríamos posiblemente una disminución de la contractilidad cardíaca que se observaba. Entonces, en resumen, teníamos ahora que el extracto produce una disminución de la frecuencia cardíaca, una disminución de la contractilidad cardíaca, y eso podría explicar una disminución de la presión arterial en modelo hipotenso e hipotensivo que se observaba. En este modelo es de ratón hipertenso, de forma transitoria, al que se le va a perfundir o se le va a generar hipertensión con angiotensina 2. Lo que se observa en las primeras dos barritas es un animal normotenso, está anestesiado, un ratón, y se ve que el extracto consigue disminuir la presión arterial. Y cuando le hacemos perfundir angiotensina, aumentamos la presión arterial, pero el tratamiento de la planta, el extracto, con la angiotensina 2, conseguimos disminuir esta presión arterial. Y losartán sería nuestro control de referencia. Con la frecuencia cardíaca veíamos también un efecto en animales transitoriamente hipertensos, una disminución, y en animal normotenso también hay disminución de la frecuencia cardíaca. Ahora voy a pasar un poco a explicar una técnica que es bastante clásica desde el punto de vista de la fisiología, que es la reactiva vascular. Usamos un miógrafo se me pasan rápido. El miógrafo es este equipo. La gracia que tiene es que tiene 4 bañitos. En cada bañito tú puedes colocar, en este caso, un vaso sanguíneo, un segmento de vaso sanguíneo, y el computador te registra esa información. Esta es otra técnica o similar de reactiva vascular, es en baño de órganos. Ahí pueden ver el tejido, el anillo, cómo se coloca. Y estos son los resultados. La gracia que tiene de esto es que es súper reproducible, las curvas, son bastante gemelas, podríamos decir, unas con otras, con lo cual la técnica es bastante robusta. Aquí nuevamente vemos más claro que en 2 anillos seguidos del mismo animal, 2 tejidos vasculares del mismo animal, conseguimos respuestas muy similares, ¿no? Entonces es fácil sacar mucha información. Esto en el tiempo es un experimento largo, de horas. Nos preguntábamos cuál es el efecto del extracto a nivel vascular periférico. Ya les he contado un poco a nivel del corazón, qué es lo que hace también sobre la presión arterial. Aquí se observa que tenemos, estos son aortas de ratas a las que las hemos preincubado con el extracto en distintas concentraciones, y se observa que la fenilefrina, que es un agonista vasoconstrictor, según la concentración que colocaste de la planta, va reduciéndose esa contracción. Lo otro interesante de esta planta es que el efecto, aunque es dependiente del endotelio, aquí mostramos el efecto del extracto, y esta curva representa con endotelio y la línea discontinua sin endotelio, igual sin endotelio es capaz de relajar. Entonces podría ser una herramienta muy interesante. Es cierto que consigue relajar a concentraciones altas, en este caso del extracto, microgramos por ml, que 3 equivale a unos 1000 miligramos, o 1000 microgramos, 1 miligramo por ml, 1 miligramo, pero ya con endotelio tienes efectos con 100, con 10, etcétera, microgramos por ml, independientemente, insisto, del endotelio. Lo otro clásico que uno ve cuando trabaja con las plantas es que normalmente el extracto suele ser más potente que los metabolitos aislados. Estas curvas, estos paneles C y D representan dos metabolitos que son fáciles de obtener, el compuesto E y el compuesto G, a partir del extracto hidroalcohólico. Y todo nos indica eso, ¿no? Esto y otros experimentos que hemos hecho, que el extracto tiene una mayor potencia, quizás los metabolitos juntos actúan de forma sinérgica. ¿Qué más hemos hecho? Hemos hecho para intentar, por ejemplo, este metabolito es uno de los que se obtiene mayor cantidad en la planta, tiene un efecto vasodilatador que ya hemos visto, importante, y lo hemos estado estudiando a nivel de corazón, que le voy a mostrar ahora, a nivel de presión arterial. Hemos hecho una modificación química que se trata de transformarlo, el metabolito, este grupo cetona, carbonilo, en una oxima, y la gracia de las oximas es que liberan óxido nítrico. Cuando tú las perfundes con oxígeno, se produce la reacción química que va a romper este enlace liberando oxígeno. Liberando óxido nítrico, que es un vasodilatador importante. Entonces sería una forma de potenciar un metabolito en la planta, su acción. Estos son datos de calcio sobre, en este caso, la oxima, con la herramienta de la cafeína. En rojo aparece el efecto del producto, que es la oxima, disminuye el calcio citosólico. No me voy a detener más en esta diapositiva. Después, ¿qué hemos hecho con la oxima? Con este experimento mostramos que la oxima que representa este SG4 es más potente que el metabolito del que venía, que es la línea verde, ya que la línea azul consigue reducir más la contracción generada previamente por fenilefrina. Primero generamos contracción con fenilefrina y después le agregamos la sustancia. Perdón, no, lo he dicho mal. Primero preincubas con el compuesto, en este caso con la oxima o con el metabolito, y después generamos la contracción con fenilefrina. Y ahí vemos cómo las curvas se desplazan. En este caso, la curva con oxima se contrajo menos que la que tenía el compuesto en la planta versus nuestro control. Esto lo quisimos repetir en un animal anestesiado para medirle la presión arterial. Entonces, ¿qué hicimos? Pues estimular contracción, aumentar la presión arterial con fenilefrina, aquí tenemos el control, y luego repetimos el experimento, pero antes le agregamos la oxima, como ven aquí. Y se ve claramente una disminución de esa presión arterial que está cuantificada aquí, y también incluso una disminución de la frecuencia cardíaca. No sabemos, ya, eso sería por un lado. No sabemos qué ocurre todavía en el corazón a nivel cardíaco. Otra idea interesante es esta de estudiar dentro de este mismo compuesto, que es esta oxima, de la que estoy hablándoles, cuál es la participación de los grupos funcionales que están alrededor de ella y ver una relación estructura-función. Entonces, por un ensayo relativamente simple de reactividad vascular, donde tú mides la contracción del anillo aórtico, ¿qué se observa? Si estamos, nuestra oxima sería esta, la línea roja. La respuesta de la línea roja es relaja, porque disminuye la curva, pero una relajación sostenida en el tiempo. Ahora, si nos fijamos un poco en la molécula, que es esta, la que pongo con color rojo, y la comparas con esta otra primera molécula, que también es una oxima, pero le hemos sacado todo este grupo que está alrededor del anillo de benceno. No tiene grupo hidroxilo, ni tampoco tiene cadena carbonada, solamente esto. Tienes una tremenda relajación y muy rápida, pero hay un efecto rebote que no dura en el tiempo. Entonces, claramente nos sirve para entender un poco el rol que va a jugar el OH o la cadena carbonada. Repetimos ese experimento, pero con una molécula al que solo tiene el grupo OH, hidroxilo, en el anillo de benceno, y el resultado es la línea negra. Desaparece el efecto relajante que se veía en la línea verde. Claramente este grupo hidroxilo está desactivando de alguna manera la ruptura de liberación del óxido nítrico a partir de este enlace de la oxima. Pero si después colocas la cadena carbonada, que sí que tiene el metabolito que se encuentra en la planta, obtenemos entonces la línea roja con su relajación sostenida en el tiempo. E hicimos otra transformación para ver la importancia de esa cadena carbonada, formando un grupo al hilo, y nuevamente nos da la línea azul, que es similar a la roja, relajante perfectamente. Entonces, con esto es una manera fácil de analizar su composición química, estructura, función. Estos son experimentos que estamos haciendo con colaboración de aquí del profesor doctor Rienzi Díaz y la profesora doctora Tamara, sobre cuál será el efecto, cuál será el efecto en los cardiomiocitos de esta oxima, que es como el siguiente paso para engancharlo con los datos anteriores. Y por último, lo que quisiera mostrarles es que existen otros extractos, curiosa, que tienen un efecto. A ver, esta planta es otra distinta, es Carophyllum longifolium. Es una planta, es un árbol que se encuentra en la Amazonía, en el Brasil. Lo curioso es que una concentración muy baja, que aquí no la van a ver, pero de 1 microgramo por ml, produce una tremenda relajación. Los datos que les he mostrado antes del extracto de la chachacoma, la relajación se produce con seguridad a los 100 microgramos por ml. Sin embargo, esta después tiene un efecto rebote muy claro. Y si hacemos el cálculo, cuantificamos, tiene un efecto de curva. Entonces, esto se ha visto en extractos y en fármacos, este efecto bifásico, en el que se caracteriza porque a ciertas concentraciones bajas podríamos decir que tiene un efecto beneficioso, pero a concentraciones altas tiene un efecto no beneficioso, sino negativo, dañino. Entonces, es otra información que uno saca cuando trabaja con los extractos. Bueno, antes de pasar a los agradecimientos, ¿cuáles son los mensajes que tenía yo que anotar como conclusión? Bueno, por un lado, que el efecto del extracto en sí mismo muchas veces es mucho más potente que el efecto de los metabolitos aislados. Después, la gracia de este extracto es que tiene un efecto independiente del endotelio. Con endotelio también produce relajación. Y lo otro es que las modificaciones químicas que se pueden realizar, como la obtención de una oxima, podemos conseguir potenciar el efecto metabólico. Y aquí los agradecimientos a los distintos colaboradores, estudiantes, distintas universidades, Antofagasta, etc. Bueno, muchas gracias.
Muchas gracias al doctor Palacio. Está abierto ahora para preguntas. Any question? Por favor. Doctor Escudero, ahí el micrófono, por favor.
Muchas gracias por la presentación. Quería preguntar sobre, me llamó la atención que la planta se utiliza para la enfermedad de altura, pero la idea es, ¿hay algún efecto sobre la vasculatura o el cerebro? O ¿cómo afectaría, ¿no es cierto?, estos cambios que ves a nivel cardiovascular? ¿Cómo se relacionan con la enfermedad de la altura, básicamente?
Claro, la verdad es que esa parte todavía no la hemos nosotros investigado, pero en colaboración con el Instituto de Altura, la idea es explorarla. Ahora, en resumidas cuentas, ¿qué hemos visto? Hemos visto que tiene un efecto a nivel de la vasculatura periférica, produce vasodilatación. A nivel cardíaco, disminuye la contractilidad cardíaca del corazón. También afecta a la frecuencia cardíaca, parece en menor medida, disminuyendo la frecuencia cardíaca. Entonces, da la impresión que la demanda de oxígeno que requieran los tejidos pudiera ser menor, con todas esas modificaciones que puede producir la planta. Entonces, bueno, a nivel cerebral, supongo que será similar, pero bueno, queda por estudiar, no se ha estudiado.
¿Una otra pregunta para el doctor Palacios? Bueno, también el doctor nos acompañará mañana en los postres. Me imagino que ahora ya estamos cansados por la hora, así que ya podemos hablar con él mañana también. Así que muchas gracias. Muchas gracias. Entonces, antes ya de terminar el simposio, bueno, quisiera dejarlos invitados entonces para mañana a las 9 de la mañana aquí, en este salón, en esta sala, donde entonces vamos a tener las dos últimas presentaciones del doctor Gary Sick y la doctora Sandra David hasta las 10. Luego tenemos que ir al frente, al R3, donde será la exposición de pósters. Ya, ahí recuerden, ahí van a estar los números. Yo voy a enviar un correo anunciando a qué expositor corresponde cada póster. Luego recuerden que se va a premiar a los 2 mejores pósters y además tenemos el cóctel del final. Bueno, además quisiera agradecer a todos ustedes porque hasta esta final de simposio espero hayan disfrutado cada una de las charlas como ustedes lo hicieron y tener la oportunidad de mañana poder conversar con un poquito de ustedes, de los que asistentes, de saber de dónde son, carreras, cosas así, porque veo varias carreras nuevas acá, así que muchas gracias por venir al simposio. And now I'd like to thank to Gary and Sandy for staying with us the whole day. I know that it's been quite hard because I've been one of the person in the audience that I couldn't understand any word because I couldn't speak English at all, and everybody was talking in English, and I was like super lost, and now I know that probably was hard for you. So thank you for staying with us, and I hope you enjoyed today all our conferences. Or learn Spanish, yeah, you have 2 options. Okay, thank you and good night. See you tomorrow.